ts, he, a, he, 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 e, he, ts, he.
Screen on a Mac. How do you enter full screen on a Mac? Anyone know?
Click the green circle.
There we go. All right. So let's see here. All right. Give me just 1 second. If you can mute the mic for 1 minute here. Let's see. Alrighty. Welcome everybody to JuliaCon 2024. For all of our in-person attendees, our speakers, sponsors, volunteers, and organizers, welcome to the giant Philips Stadium. And for all our online attendees who are hopefully viewing right now, welcome to the YouTube stream, and we hope you enjoy the streams and interact with the community online as much as possible throughout the conference. I'd also like to start by mentioning sort of the time to first grasp problem that we have behind us. So this was not the plan, but unfortunately, we're in a football stadium, and football takes precedence. So please bear with us while we try to deal with the monster truck arena behind us, and we'll try and ameliorate sort of the issues that have arisen from this as best as possible. So I really appreciate your patience there, and we'll sort of move on with the best part of the program, which is the talks. But first, I'd like to thank our generous sponsors. We have our diamond sponsor, as always, Julia Hub, our platinum sponsor, ASML, our silver sponsors, Eston Automation, Cognibotics, Sue Technologies, and Relational AI. Our bronze sponsors, Boeing, Pumas AI, and as always, Jeffrey Sarnoff. Our copper sponsor, Better Hand Financial Technologies. Our long list of amazing startup sponsors, EvoVest, G2I Computing, Genie, Great Lakes Consulting, IENAI Space, Unitary Fund, Jolin, and Jahan. And we also have some amazing supporting partners. TUE, if you were at the workshops yesterday, I hope they went wonderfully. And that's thanks to the generous support of the University of Eindhoven. Lazy Dynamics, Version Bay, and Ferris Systems. And of course, I'd also like to thank our gracious hosts for accommodating us in Eindhoven, and for Eindhoven itself, accommodating our record-breaking JuliaCon this year. Speaking of record-breaking, we have over 300 speakers, which is a crazy number of speakers. Not everybody is in attendance today, to be clear. I think we, between 1.5 times and 2 times the number of people on Friday, and we have over 700 attendees on Thursday, including PyData, who is joining us as a sort of sub-conference. So please be welcoming to them when they're here tomorrow. This is also the second JuliaCon Global in Europe. The last one got canceled, unfortunately, in 2020, for reasons we're all aware of. And it's the 11th Global JuliaCon since the very beginning. We also have 50-plus volunteers, which is way more than we had last year. I think last year we had 12, something like that. So huge shout out to our volunteers. Please give them kudos whenever you see them, because that's a really big deal. The volunteers are here to help ensure you have a fantastic conference. Please, any questions you have for them, find an orange badge for volunteers or a red badge for organizers. Volunteers often may not be able to answer all of your questions, but they will be able to find an organizer to answer your question. Finally, we have a bit of a schedule for today. At 9 a.m., which is 5 minutes ago, we have the State of Julia. It's earlier than normal, so it's the first talk this year. And then we have a little Q&A session after State of Julia for about 20 minutes. So hopefully everybody is looking forward to that. We have 50 minutes of sponsor talks from our wonderful sponsors. And then we have parallel tracks for an hour and a half to 2 hours-ish. There are breaks throughout the day. It's not mandatory to attend the breaks, but they are sort of strewn throughout the day. Occasionally, the reason I say it's not mandatory is occasionally there are talks that extend through the breaks, especially things like birds of a feather sessions. After that, we have a lunch here at the stadium provided at 12:30 p.m. That's an hour and a half. And then we start tracks again at 2 p.m., along with 2 mini symposia, scientific data and aerospace. And then in the evening, after a break, 2 breaks actually, there's another one right before the keynote. There's a keynote by the wonderful Dr. Michael Herbst and Dr. Rachel Kirkin on chemistry toolkits in Julia. So please, everybody, attend that and listen to our wonderful keynote for the afternoon. Following that, we have a poster session with snacks and drinks for purchase, to be clear. Purchased from the stadium. There's obviously a lot of food at a stadium, so we're going to take advantage of that. But food is not provided for that event. Just real quick, I'm sure nobody can really see anything on there, but we have 4 floors. We actually have 5 floors because we start counting. We're zero-based in Europe, apparently. So there's a 0th floor, and that's where registration is. Hopefully, you've all visited registration. That will be up all day. You can ask a volunteer there for information at any time. We then have the first floor with a couple rooms in it. I think there are 4 rooms on that floor for talks. The second floor, which is where you all entered, there are no talks on that floor, but it's just sort of the entryway into the main stage here. To be clear, there will be main stage talks all day as well during the parallel tracks. On the third floor, there is one room with talks. I believe it is on that end of the building. I could be totally wrong. It could be on the other end. But there's also our wonderful sponsor booths and food and drinks during the day, so during the breaks and then also for lunch. And then finally, there is a 4th floor. I believe there are 2 talk rooms on the 4th floor. There are several stairwells, so hopefully everybody can make it through to the floors easily, and there should be elevators also for those who need it. So that's the first bit of logistics out of the way, and I'm going to move really fast here because I'm starting to cut into State of Julia time. On Thursday, just to announce, we have a diversity dinner and discussion. That was a ticketed event. You should have been able to purchase tickets when you bought your JuliaCon ticket. That's Thursday at 6:30 p.m. There will also be food and drinks available for purchase with the PyData folks as well outside of that event. The event is a panel session followed by group discussions amongst members of the community, and it's hosted by the wonderful Julia Gender Inclusive team. So please, if you have your ticket, be sure to attend that and listen to our great speakers and have a great panel discussion. Finally, I have to mention, not finally, excuse me. I have to mention JuliaCon proceedings. We have a peer-reviewed proceedings for this conference. If you presented here, you can submit your work, and it's similar to JOS, the Journal of Open Source Software, I believe, where all reviews happen on GitHub, and should hopefully be smooth for a lot of people who have presented their packages here today. So please check that out, proceedings.juliacon.org. And then I have a couple more slides here. We have a call for hosts. Next year's JuliaCon is not set in stone yet. In fact, we don't really have any strong plans quite yet, maybe more by the end of the week. But if you are interested in hosting JuliaCon at your where you live, where you work, please let us know. That can be a JuliaCon local, or it can be the global annual JuliaCon that we have every year around this time of year. Potential hosts for the global should express interest by the end of July, and we will assist you as much as we can in preparing that sort of proposal. If you're interested in hosting a local, the local is what led to this JuliaCon Global. So please do. It's a great way to build community, and oftentimes has way more attendees than you would expect. A couple more things. We have a code of conduct. Please adhere to that code of conduct at all time while you're at the conference. We have both a JuliaCon code of conduct, a NumFocus code of conduct, and a community code of conduct. They're all relatively similar, but they are all a little bit different. So just please be aware that you must adhere to those at all time. We just want to create a welcoming and collaborative experience. If there are any issues, we have a phone number here and an email. And there are 2 organizers who are sort of the first points of contact for any issues that arise. So please talk to them, and they will maintain confidentiality until you wish to breach that confidentiality. We have a little bit of logistics finally, and then I'll thank some organizers, and then we'll be out of here for State of Julia. So some logistics, please always check pre-talks for the latest schedule. Sometimes there are minor changes, swapping of talks, and various other things, but the schedule is pretty set in stone. You just may see some talks move around here and there. We'll try to minimize that, but I know at least one talk moved yesterday. Speakers, if you're worried about any issues with your laptop, you can use pre-talks to upload your slides. Please do that. You'll be able to use the laptop that's in the room to access those slides and display them in case your laptop dies or fails or Julia crashes or whatever. There is no Julia on that laptop, so it's only for non-interactive presentations. Like I said before, volunteers have orange badges, organizers have red badges, and breakfast and lunch will be provided on the 3rd floor. So with all that logistics out of the way, I have one more thing, and that is to thank our organizers and volunteers. I won't go through them all today. I'll talk about them on Friday. But if y'all could give a huge shout out to our organizers and volunteers, that would be fantastic. I also want to give a massive shout out to Guillaume, who swapped his talk with me today to allow me to finish these slides. So with that, I will introduce the State of Julia talk. So please welcome the State of Julia speakers to the stage. Briefly for the future, there's a stairwell at the back of the stage.
Sorry, is this your phone?
It's okay. It's
okay.
It's...
Hey.
Yes, it's working.
Okay, hello everyone, and welcome to this year's State of Julia talk. Let's first introduce ourselves. My name is Christopher Carlson. I work at Julia Hub. A long time ago, I used to do finite element modeling and material modeling. Then I started helping out a little bit with the new fancy package manager, and one thing led to another, and now I'm standing here presenting State of Julia.
I'm Lilith Hafner. I work on language and tooling with a focus on making Julia more inclusive to new contributors to the language.
And my name's Elliot Saba. I did electrical engineering until I needed something to replace MATLAB, found Julia, fixed a bug in it. Viral was very welcoming, and now here I am.
So first, I want to give a little bit of what is the Julia experience, and this will of course be a very small slice. The Julia experience is very big, but this is a little bit how I feel about it, and what are sort of the core things and the important things. So first, I'm putting some representative code here, and representative code is very hard, but I try to at least include some things that are sort of typical for Julia. So first, we have some useful packages we're loading, like static arrays, fast static-sized arrays. Maybe we want to use units in our code, so we load a unitful package, so we don't add a meter to a second or something. And then maybe we want to find the gravitational constant there, and there's a physical constant package that I can just get that from. And that's also a unitful constant, so if I would take the g there and add it to something, it would error for me. Then we have a struct here, a planet that contains some data. And typical Julia, we have sort of very generic code. So here I'm parameterizing this planet on the floating point type. And I'm also saying that this mass should actually be a mass. It should be a uniform mass. So it's not just a number, it's a mass. And if I do dimensional problems, it's going to error for me. I have some position and a velocity. Maybe I can compute the kinetic energy of a planet then, or the potential energy between two planets. So as you can see here, we have quite a high level of abstractions. We're using units. And there's not that much boilerplate. Sometimes when I go into other projects, I try to find where is the actual code that does the computation. And it could be sometimes a bit hard to find. But I think with Julia, it's pretty easy to find, OK, there's the actual code that is running. And now I could, for example, create the Earth planet here, and I'm using the units here. I'm telling it in kilos and the kilometers where it is, and the velocities in kilometers per second. I'm computing the kinetic energy, and I get that back as a unitful answer here. It's a bit interesting unit here because I'm using kilometers for the velocity, so I get this in kilograms, kilometers squared per second squared. But I can convert that to gigajoule or something that we're more familiar with. So now we have some code, and I think typically in Julia we want to do some performance evaluation. We want to see that this thing runs fast. So here I'm trying to load the benchmark tools package, but I hadn't installed it. But then the package manager comes in and is like, oh, I know this package. Do you want me to install it for you? Yes, please. OK, thank you. Now I can use this convenient macro syntax to run the benchmark. And for the potential energy between two celestial bodies here, it was a few nanoseconds. So here we can see we have these zero-cost abstractions in the runtime. I used a bunch of units everywhere. That's going to, at compile time, check that it's going to check that the units are correct. But when I do this at runtime, there's no performance penalty to it. And doing this, I can update my code, and I can benchmark it, and update it, and benchmark it. So it's pretty fast to iterate on some code to make it go faster. And the second part is, if you really want to deep down, you can do this code inspection. And so you can look at this is if you're really interested, but you can look at the LVM code, and you can even go and look at the native code. Here I'm running this on an ARM processor, so there's ARM assembly there. And at least for me, learning this LLVM code and assembly, this was using these inspection macros, because in many other languages, it's kind of hard to very easily see, OK, for this function, this is the code that's actually going to run. It's also possible to do some static checks. For example, there's the jet package, and you can do this thing to tell me if I'm doing some common mistakes. Maybe I have type instabilities or something. But here it says no errors detected. OK, that's good. But before we just ran this thing on one thread, but with Julia, we kind of want to use all the compute we have. So if I do this threads.nthreads here, I see I have 8 threads. So if I want to compute the total energy in a system of planets, I can just do it with a simple loop here. I loop over all the planets, compute the kinetic energy, and then I add the potential energy between all the other planets. So this is going to run on a single thread. And it's not much you have to do to make this run on multiple threads. So here I add the threads macro in front of the loop. I just make sure that every thread accumulates into its own variable, and then I do a sum in the end. So now I'm going to define a kind of funny function. It's called a random planet. So I'm just randomizing the mass here. It's going to be maybe it's more like a random asteroid or something, because it's going to be between 0 and 1 kilos. But anyway, it's just to generate some data, a random position, random velocity. And then I can check this, how long time it took when I did the total energy of the planets with the single-threaded, and I can run it with the threaded, and it's quite a bit faster. No, it's not linear speed up here, but it's also this laptop has like different types of cores. It has this fast cores and this more energy-efficient cores, so it's a little bit complicated. There's also more higher-level threading packages that, doing these threads on a loop, it's a little bit low-level maybe, so you can also do this on a more higher level. But let's say I have this very, very strong computer, a cluster or something I want to run Julia. So here's an example. I have this super fast cluster where I have some nice GPUs I want to run my code on. But I log into that cluster, and I do ls, and there's absolutely nothing in there. It's the first time I logged in. And it says, I'm trying to run Julia. It cannot be installed. Please ask your administrator, it says. But I don't think we have to do that. So it's very easy now with Julia App. We can very easily install Julia here locally on this cluster. So I'm just doing this Julia App install command. It installs it. And in the end, I have Julia installed very quickly. So now we have Julia installed on our super fast cluster. But we also have to get our files on there. So I just copy my files from my local hard drive up to the cluster. OK, now they're there. But now in my code, I used a bunch of packages, right? So if I start Julia here on the cluster and I do a status, it shows all these red things that are, the packages are not installed here. But now very easily, it tells us we can just do instantiate. It downloads all the packages we had locally. And it even downloads stuff like the CUDA runtime. So basically, I timed this. It took less than 2 minutes. And everything was installed, and I could start it running. And that was from pretty much scratch there on the remote system. So let's try use these GPUs then. And the fact is, you have to modify your code a little bit to run on the GPU, because running this iterative code is not very well suited for GPUs. So here I kind of rewrote this energy code to be a bit using this broadcast. And now let's see if this is useful, or if we spent $10,000 on a very expensive GPU card for nothing. So let's see. I have 64 threads on this remote machine, apparently. I have these 2 GPUs. I create these planets firstly on the host, or on the normal memory, and then I also have it on the GPU. And then let's say I first run it serially. It took some time. Run it with threads. It was quite a lot faster. And now I just ran it on the GPU, and it was even faster. So thanks, we didn't spend all that money for nothing. So to summarize a little bit the Julia experience, we have generic code, the abstract over the floating point type, the dimension. We have a lot of useful packages like units and so on. High-level abstractions that ideally doesn't cost anything at runtime. Not that much boilerplate. A package manager that helps us install things and install things on remote machines. And also using all the computational power we have available. So just one thing I want to say too is Julia is not only numerical computing. Here my example was kind of focused on numerical computing, and I think Julia has evolved a little bit now. So for example, Julia can also be art. So we have just a very narrow selection of packages, but we have the javis.jl, which can do animation type of things. We have, of course, Luxor by Cormullion here to make very nice figures. And I saw this Twitter post saying that I've experienced using Julia for generative art, and it worked very well. And it's also, people use it for games. So here is julgame.jl. It's a game engine in Julia. So to the left there, we have some kind of Pac-Man looking game. In the middle, I don't know, maybe some Zelda looking. And to the right, we have a level editor running in Julia. And of course, there's a lot of web stuff going on. This is just a short selection of packages, but we have the Genie, of course, to make web apps. There's a talk about that. We have Franklin to make websites, and Documenter to do our documentation. And I think Julia is spreading even a little bit further than expected here. This is a Twitter post from someone who was in Egypt. And there was this Julia sign here on this leather trading store. So watch out, we're coming for you next. You don't know where we're going to show up.
All right. So I was tasked with digging through our package servers to pull up some interesting statistics over the last year, just to kind of show how the community has grown and is continuing to expand. So somehow we've managed to grow to where we're serving 170 terabytes of resources every month from the package server network globally, which is not an insignificant amount. There are 2.5 million unique IP addresses served. A new package is registered and served every 7 hours, and a new package version is released on average every 24 minutes. So our community is really, really active, constantly creating these new packages. Clients make 135 requests a second to check for new registries. So every time you say package add or package update, you check for a new registry to find the new versions, and we're getting that 135 times a second. We wanted to pull out a few interesting tidbits looking at the package server data graphs, which you can get from links that are posted on Discord. In this case, we want to give the most improved award to accessors.jl, which went from having only about less than 1,000 downloads a week at the end of JuliaCon last year to this year having over 5,000 downloads a week. So good job, accessors. And if we, instead of looking at per week, we look at per day, when a new version of ordered collections comes out, you end up with 16,000 installs per day, which is just an incredible traffic spike, which I thought was kind of funny to see. You can also see here that people really do use Julia at work, because on the weekends, the installs drop quite a bit. The star history for the base Julia repo continues to skyrocket. We now have over 40,000 stars on the base Julia repository. And for those who are interested, that is when 1.0 was released. And industrial adoption continues. So here we just have kind of a smattering, not even a complete list of the logos of the companies that have publicly talked about their different Julia usage. Of course, we have ASML. For those of you who saw, WhatsApp a little while ago released a video talking about how they used Julia to prototype the new audio codec, et cetera, et cetera.
So, and those companies are a big part of the community, and also a lot of individuals form this community from around the world. So there's a lot of ways to interact with the community through discourse, through, if you're looking to be more contributing to folks rather than getting questions answered, and getting questions answered, GitHub issues and pull requests, all those releases coming out, all that activity is also happening in discussions. It's people opening issues, opening pull requests, fixing things. If you have an issue, if you don't understand something, maybe a documentation pull request to a package. And there's Zulip and Slack for more informal communication. And of course, JuliaCon, great way to interact with the community. There's educational resources for getting to know Julia better and to get nice workflows. As more tooling for effective use of Julia comes out, getting that nice Julia experience is evolving. And this Modern Julia Workflows project is an attempt to take people from 0 to a basic script and to optimizing code and getting effective systems, making the best use of the existing tooling. So that's a new resource this year. And another new resource this year is this month in Julia World, which is a monthly newsletter. So check that out. And it is posted on Discourse and Slack and Zulip. Yeah. And there's also a lot more resources. These are just the 2 prominent new resources from this year. But there's a lot of other resources on julialang.org/learning. So a lot of ways to learn from asynchronous communication, as well as the synchronous communication, or closer to synchronous, of these other interaction mechanisms. One huge part of Julia is open source contribution. And something that sets Julia apart from a lot of languages is the transition from writing personal projects to shared code that other people can use is pretty straightforward in Julia. And if you think other people might benefit from your code, feel free to share it. Writing personal code in a package is great because packages provide a whole bunch of infrastructure for like testing. So much tooling to support packages, and the step to publish that package is just a quick registration. And so that transition, combined with the fact that Julia is primarily implemented in Julia, and all the Julia packages are primarily implemented in Julia, makes it really easy to accidentally fix a bug and then give a State of Julia talk a couple years later. So do that. I recommend contributing to packages. It's great. Most folks find package contribution much more effective as a use of time than contributing to the base repository, although love contributing to the base repository too. 1,430 new packages since last JuliaCon. That's a lot of packages. And I think part of the reason that package development can be so productive is that it's very scalable and low risk. If you publish a package and it's like not up to your standards, it's not good, then people won't use it, and that's okay. It doesn't hurt anyone. And in that way, in this big open namespace, we can collaborate and have a lot of people working on a lot of different disparate packages and duplicating effort sometimes and reusing sometimes, and it's lovely to open source your packages. Give us this little gift. Yeah, and this Julia experience, that relies on these packages. That's where CUDA comes from. That's where all the units come from. There's a bit that comes from core Julia, but mostly, if you want to be productive, we need good packages. And so appreciate all those package authors out there. You can do a lot of seemingly internal things in a package. Like Julia syntax, that's a package. PKG, that's a package. Weird. Yeah. Also, of course, contribute to Julia Lang/Julia. Appreciate that too. So now we're going to talk about some new things that are happening in Julia since last time.
Yeah, so one thing I want to say is that Julia now is better than ever. It's quite common to read that, I tried Julia a couple of years ago. It took quite a long time to plot my thing, and it didn't have the packages I needed. So just as an example here, I did the time to first plot from Julia 1.0 to 1.10. And what I also did, I checked out the registry at that specific release date. So I got like the exact snapshot that someone would have experienced at that point, because quite a lot of this latency work has also taken place in packages. So it's been quite a good improvement. So the time to first plot here, from going from Julia has not been started to it actually showing you a plot, has gone from 16 seconds to 1.4 seconds. And there's been a lot of various latency work. Perhaps the most significant one, which was discussed a little bit last year, is this in 1.9, that the compiled code started being saved to disk. So then it dropped all the way from up here to down here. But even from 1.9 to 1.10, it improved. So the work is ongoing. The number of packages then has increased from over 2,000 to 10,000. So if you try Julia today, you might have a better experience than you did at the 1.0 era. And we also have now a parallel compilation of packages, so actually getting started running code is also much faster. So a little announcement then is that 1.10 will be the new LTS. So 1.6, yeah. So 1.6 is of course a great release. It has 7 patch releases with bug fixes. However, for example, we have moved to a new CI system, so it's a little bit hard to make new releases for 1.6. 1.6 does not support, there's a feature compressed registries. Before you had to unzip all the files in the registry, and especially on Windows, that makes CI pretty slow. 1.6 is starting to be kind of old, especially for a relatively new language. And there's many features that have come since 1.6 that are almost feels like a given now. So, and many authors, they do try to support all the way back to the latest LTS, but I think yeah, it's time to allow them to upgrade now, so this is sort of saying that 1.10 will be the new LTS. Another thing that's happened is that moving out standard libraries from the sysimage. So historically, we had these standard libraries, and all of this was baked into one big sysimage file. And there was some good things about that. It was quite fast to start with that, and all your standard libraries were immediately loaded. Now the standard libraries, most of them have been moved out, so they're loaded just like a normal package. So a little bit of a drawback then is that standard libraries are now not free in parentheses to load here. So if I load PKG on 1.10, it's fast, but if I load it on 1.11, it takes a little bit of time. Now, why would we do that? Well, for example, based on this, we have a faster Julia startup time. So there is actually some cost to having to load, for example, a package manager every time you start Julia. If you just want to run your code, then loading a package manager might not be something you want to do. It also allows to upgrade and version standard libraries. We have delimited files and statistics that are trying this now, so I can add statistics, which is a standard library, add some version, and it's going to use that versioned standard library. It's also in some sense a little bit fairer. Why should the standard libraries be these in a special position? Let's say sparse arrays is standard libraries. It makes it hard for someone else to write a better sparse arrays library if the standard library is in this special position. There's some, for technical reasons, there's some standard libraries that are still in the sysimage, like linear algebra and random, because they do some type piracy, and sockets, which is used by Julia itself when doing TCP. But there's some thoughts about how maybe to move those out as well. Okay, let's look a little bit at what PKG has improved on. So we have this in 1.11, this new sources section you can put in the project.toml. So before, you used to have to bundle a manifest if you wanted to instantiate a project with unregistered dependencies. But now you can specify a URL or a path for packages in your project file, so you don't have to always carry this manifest around. In 1.12, there's this workspace feature coming up, where you can have multiple projects that share a single manifest. So if you have, for example, a monorepo, or you're using many private packages, having all these manifests everywhere can be a bit annoying. Now there can be one manifest, one source of truth, and all these projects refer to that manifest. And then we also have a bit of a work in progress with apps, which is to install command line tunes with the Julia package manager. So right now, let's say you want to start Pluto. You start Julia, you write using Pluto, and then pluto.run. It would be arguably a bit nicer if you could just install Pluto and then run Pluto in your command line tools. You don't have to do this whole startup procedure.
All right. I'm going to talk a bit about static compilation analysis. Just a quick note on the previous slide. 1.10 is the new LTS. It's been released for a while. 1.11 is going through the release candidate process right now. 1.12 will be released in the future. So last year at JuliaCon, we had some talks about static compilation, how we're going to get away from needing to have a JIT all the time, how we're going to get away from needing to load liblvm all the time. And a lot of the stuff that we talked about was in the future at some point to be worked on. Well, I'm happy to announce that we have 3 talks this year that are talking about different aspects of the progress that has been made in this direction. So Julia is a dynamic but compiled language, right? We write this code that doesn't have strict types assigned, but through type inference, we're able to identify regions of code where we know precisely what the types will be. We call those this kind of static subgraphs of the program. And for those static portions, we're able to highly optimize it, turn it into machine code that knows precisely the kinds of instructions and data types and such that need to be encoded there. So there's been a lot of interest in looking at what would happen if we could make the entire program just one static subgraph. And that's exactly what JuliaC aims to do. It tries to provide a mode for Julia to run in that makes the entire thing static so that it can be compiled completely ahead of time. And so if you're interested in that, I suggest you come back here to the main stage to see the new ways to compile Julia talk. There's also a talk by Keno and Shuhei about doing different kinds of static analysis with the Julia compiler. And separately from compilation, a more analysis-focused talk will be with Gabriel and Cody on alloc check, which is a way to use the Julia compiler to check to see if there are any allocations happening in your program, which is a very important thing when you're trying to write high-performance or non-allocating completely code. There have been many improvements to the GPU stack recently. CUDA has an integrated performance profiler, which allows you to not have to exit and reopen with the NVIDIA tools to do simple performance profiling. There's been a lot of work into simplifying application porting, both for the CUDA and AMD stacks, that will work well with unified memory. Improved GC integration to help you bring your memory usage down and have it interact more reliably with Julia's GC. In one API, we now have support for the Aurora supercomputer. Metal has been improved with lots of bug fixes and improvements just all around. And the GPU compiler core package itself now interacts with Julia's precompilation cache, which is going to lead to greatly reduced latency in the future. Tim and Valentine and Catherine have some talks, as you can see on the right there, about these aspects. Just as a quick teaser on the kind of performance improvements we're talking about. In Julia 1.10, which precompiles but does not have a cache, initialization here is taking 70 seconds, whereas in 1.11, with precompilation and the cache, it only takes 12 seconds, and you can see the time steps are also greatly improved due to that precompilation and cached code. I believe the motivating example for this was using a GPU cluster where each node in the cluster was taking like a couple minutes to do the precompilation of these packages, and they're using like weeks of compute time just doing precompilation, whereas now it's brought down to a much more manageable fraction.
So Julia Up is now the official recommended way to install Julia. It's what we showed in the example experience part. It supports installing Julia, which is the primary use of it. And it also has a lot of other nice features, like it prompts you when there's a new Julia version so that you can update if you'd like. And you can launch as many different versions as you'd like. It's got support for the long-term support, for release, for pre-release, for nightly. Work in progress for for just installing a pull request, a proposed version of Julia. That's in the works coming soon. Highly recommend it. I've been using it for managing Julia versions for a while now. Annotated strings is something that it's raining, lovely. Is something that Timothy's been working on. They allow us to give a first-class representation of metadata attached to strings. So that's going into base, and styled strings, a new standard library, is creating a way of styling them, adding syntax highlighting. And that helps make all sorts of things prettier and makes the user experience, or the developer experience of people writing those pretty codes nicer. So that's a useful thing. Mostly it's going to be coming down the pipeline in future versions. There's some REPL improvements coming soon in 1.11 and 1.12, neither of which are released quite yet, but 1.11 is soon, with auto-completion inline suggestions and syntax highlighting in Markdown is going to be 1.12. We've got better error messages ongoing, and we now, when you load a package that hasn't been precompiled, we do parallel precompilation then instead of serial. So that's a thing that might be helpful to some folks. Lowering, so flashback, parsing is now implemented in Julia as of 1.10, I think. And soon, lowering will be as well. And that gives us code provenance. You know where the code, where lowered code comes from. And that's super useful for macros, for escaping, and for better error messages. So see Claire and Tim's talk later. I don't know what room. The public keyword decouples namespacing, that's export, from API, that's which symbols are public or not. And that allows us to more clearly define APIs in packages and in base. And if you ask for the docstring of an internal symbol, you'll now get a warning as of, I think, 1.11, telling you that it's internal. And that allows us to communicate more clearly. And I've got a talk on that later today here. And all these improvements, thanks to our vibrant community. JuliaCon's a celebration of us all, new and old. Thanking the sponsors, the organizers, the attendees. Can't have a conference without attendees. Thank you. Just going to highlight some names, word cloud. These are, for the most part, new contributors to JuliaLang/Julia who haven't committed last year and haven't committed before last JuliaCon. There are going to be a little bit of errors here. Tracking contributions is tricky. But shout out to Timothy for all this styled strings for the formatting better user experience. And shout out to Florian for making pre-compilation improvements and making relocatable precompile files, which is the first step to not requiring local precompilation, to being able to serve that. And then you'll never have to wait for precompilation again, which would be super cool. Yeah. This is just all the contributors to that repo in the past year since JuliaCon, and this is from all time. There's a lot of people. There's some core ones whose names we probably know, but so many others. It's wild. It's too many to be legible. And even more people contributing to package authors and contributing to packages. So, I mean, we shared the highlights of the core language in this talk. The highlights of the package ecosystem are too big to fit in a talk, and so go to all the talks in all the tracks. Yeah, thank you. And now we're going to have a little Q&A. So would the people joining us for the Q&A slither on up to stage?
All right, thanks for the great opening talk. And we have a little bit of time for questions. So I'm sure there will be plenty of questions. If you have one, please raise your hand, and I believe we will throw a mic at you. So we'll see how that works.
Any sort of questions about Julia, the future of Julia, the present?
Now's your chance. You have them all on stage. There's one here in the front. Can we get? We will get you a mic for the stream.
All right, here we go. Ready?
Try to catch it. Okay.
Hey, how big is Hello World?
So if you see here on the slide, it's at 890 kilobytes at this point this was taken. So.
Behind you? Yeah.
So there's some cool new features in Julia 1.11, 1.12. Are any of those going to be like in the compat.jl package for 1.10 for LTS?
Probably not. A lot of the cool new features can't be backported like that.
That said, I think public and a couple of them are getting like syntax compat, so if you use it, it will do somewhat sensible things.
Yeah, public is supported by compat.jl.
Chris in the back. Yeah, that's going to be a tough throw. Awesome.
Can you speak a little bit to garbage collector improvements and allocation improvements and things going on with improving the timing of code that is allocating?
Here's
Where's the mic? Okay. So working on the garbage collection is a continual improvement. Since the last year, I think last year we got parallel marking, and in the meanwhile we also got parallel sweeping going on, which nope, I think we have both. We have concurrent and parallel sweeping. So those are incremental improvements to the garbage collector to make the collections shorter and have them have more work happen while other threads are doing things. And as always, we're working on reducing allocations on packages via optimizations that the compiler can do, eliding allocations that semantically might be there, but the compiler can see that nobody sees the allocations exist, so we can throw them away. And all of these are very iterative things, not necessarily one big thing that changes your code to be non-allocating. You might note small differences here or there.
Is there some way that people can find out if they're allocating or not?
Yes. Me and Cody have a talk about allocheck.jl, which is a tool that helps you reduce your allocations in your code. So go there if you're curious about how to reduce allocations.
The best GC is the one that doesn't have to run.
Yes, agreed. I have a small question. I know that there's this change on the array interface, and there's this new memory type, and I don't know what that's about. Do you have some words for that?
Oh no.
Oscar? Maybe you could throw it over for the answer?
Oh.
I'm sorry to disappoint all of you with my catching capabilities. Come to main stage at 2:30, I think. Jameson and I are giving a talk on that. But the short answer is, yeah, now array is a first-class Julia object that you can look at the internals of and mess with them. And if you do illegal things, you'll get seg faults. So don't do that.
And there's a new memory type that is like an array, but without all the features. You can't resize it, and it's a little bit simpler. And that's now not a first-class object. Yeah, so you can use this new subtype of abstract array for that.
I wanted to ask about Julia lowering. So the examples here were more about like understanding your code or better error messages, but I wanted to ask, is there also some new capabilities of Julia that could arise from that? Some weird new macro code generation stuff?
Yes, indeed. So do come to the talk, but yes, I've been working on a new macro kind of, a new flavor of macros where you can emit like precise error messages from the macro as the macro author, so people will be able to see exactly where in the code, like it will be just as good as lowering or syntax errors are now. You'll be able to see precisely these characters where the error occurred. And I'm trying to remove ESC. So people who don't like the ESC function, who write macros, if you'd like it to go away, then I'll keep working on that.
Yeah.
Yeah, so I guess those are the goodies. But come to the talk on Julia lowering. Actually, the name of the talk is "Dude, Where's My Code?" Come to that tomorrow.
There's one on the right, top right. Tim Holly. We need the mic for the stream, unfortunately.
Thanks, Tim.
Just to add to Claire's answer, the other many good things I think will come from moving lowering into Julia with better provenance, and the sort of applications that might be usable or visible to users are essentially better versions of Cthulhu, better versions of the debugger, and possibly Revise could get a sane design and maybe move mostly into Julia itself. So.
Yeah, there's a lot of things that could come from it. I mean, things like stack traces, which tell you precisely where the function call was as well. One day in the future, it's a long process to push that precise provenance information all the way back, like all the way from the parser all the way through the compiler. So we're about a third of the way.
So,
loop vectorization has sort of been deprecated with 1.11. Are there any plans to bring some of its functionality back anytime soon?
Is Chris here?
No, Chris. Different Chris.
Yeah, different Chris. But all right.
Can you bring the mic to Chris Wacaucus?
Yeah, the other Chris I think can answer it. Chris's boss, Chris, can answer it.
Yeah, so we are actually just looking for more people who want to maintain and help grow that stack, right? So loop vectorization did actually get an update for version 1.11. I think that most people might not actually seen there was an update out there, so it actually does run on 1.11. There are 4 known things that need to be done, so that way it'll work on the 1.12. But there is a SciML small grants project, so there is funding for if someone wants to be the next maintainer to help do this. There's an issue list that says exactly how the update needs to happen. We're willing to get new maintainers trained in on this. So yeah, there's nothing really that's required for getting loop vectorization in. It's just more, just getting more maintainers in there to help with the maintenance process.
I think long term we will also have to look at adding more vectorization capabilities and vectorization intrinsics and handling modern vectorization styles in the language itself. But that's of course a years-long process to get to a design that everybody agrees with.
Can the static compiler generate for different platforms like Go?
Not yet.
Just behind you.
Thanks. Will there be a time where we can revise everything?
Rewrite?
No.
Revise.
The answer is the provenance doesn't help with that. The answer is Tim says no. I'm optimistic, but the answer is probably no.
It depends who answers. Tim will say no. Keno might say yes.
Speaking for Keno, since I'm closer to the mic, yes. Keno has a PR open right now that makes it so that you can revise, or so that you can edit structs. Yeah. Revising them is still a bit out,
but there's still things that you cannot simply revise, and it often also is the question: what does it even mean to redefine the code while it's running?
Yeah, so I think it's never going to be always, but it can get to be much more stuff can be revised.
There's 2 questions in the middle, one in the top, one here. Yeah.
Thank you. Regarding the static compilation, is there any plan to support creating shared libraries so that we can embed it in the existing code? And if so, would it depend on the Julia runtime or not? Or what is the plan?
Yes, there is a plan. Come to our talk. We're going to talk about those things, but yes. About embedding the Julia, so currently it has this Julia runtime separately. We're working on statically linking all the binaries together so that you have a binary that looks a lot more like one you would get from C or C++ that you wouldn't know that it's a Julia binary. It's just a shared library. And that's on the pipeline, and we're working towards that. So yes, I think the short answer.
With regards to the Julia runtime, it always depends on what you need. If you want to use multi-threading, if you want to use the garbage collection because you're using allocations, then you will need to link against the Julia runtime.
But it will be way smaller than the entire...
So already the Julia runtime is split into the compiler pieces and the real runtime, and I think the real runtime is around 5 to 7 megabytes, whereas the compiler is much larger.
Okay. Thank you. Thank you.
In the top middle, second to last row, Mason, I think.
Raise your hand.
Oh, okay, the question has been answered by the last one. Then to your left.
No.
Are there any current plans for RISC-V support?
Yes, but we depend on... So getting Julia to build on a new platform requires a stack of things to happen. A couple of them Elliot here has been working on, which is to get the binary builder ecosystem working, because we need to build our dependencies and all of that. We also require LLVM support, which is in progress, and a bunch of things need to happen. A random user, which I cannot remember the name, did get Julia working on a RISC-V with a bunch of patches that they did, and it wasn't super complicated. So I think we're all waiting for a really fast CPU that is capable of running Julia in a good manner, which I don't have access to one, and I think that's pretty much it.
Yeah, so we need development boards or something to run CI on. Ideally, we need like 8 of them to keep up with the constant, deluge of pull requests that people are making against Julia, so we don't accidentally break something. We also need someone who's just very invested in the platform, so that when something breaks on only RISC-V, they're willing to dig in and get to it. You'd be surprised how difficult it is to find that even for like Windows 32-bit, much less RISC-V.
And I would say the same answer holds true for Windows on ARM, since that has been a recent point of questions. We don't have Windows for ARM systems. The compilers aren't ready yet. And it's a huge lift to get a new platform working. So if you care, if you're interested, volunteering is the best way to make sure that that happens.
And we're more than happy to guide these kinds of explorations.
Maybe 2 more questions. One on the right. You already have a mic.
Yeah. So you show that's easy to install Julia and packages anywhere. But we've got clusters and computers without internet access. Do you have any advice on how to avoid my administrator there?
SSH tunnels.
Yeah.
And you can, on many of these systems, you can just straight up copy a depot. So you can install a depot on a machine of that architecture, then just tar it up and move it over.
Yeah, that's also the work that was mentioned earlier from Florian Atteneder, is to make copying depots much easier and simpler.
Okay, cool.
All right, in the interest of time, let's maybe stop here. Thanks for all the questions, but more importantly, thanks for the answering and also the opening talk. Let's thank them again. And before we have our first sponsor talk, I've been told to remind you all that if you have code snippets on your slides, make sure that the font size is big enough, not just for the stage or the room you're in, but also for the online stream. In the past, sometimes it was hard to read on YouTube afterwards. So maybe increase the font size even further on your slides. That goes out to all the speakers. All right, and this brings us to the first sponsor talk, I believe. I don't know where Ray is. Anyways, then let me take it over. So the first sponsor talk, will be by Klaas Nielsen and Can Wu, Juliet and Romeo. The official way is if you go down and back up, then you don't have to climb up here. Sorry? Oh, missing microphones. We can use this one. Should back up or? I see. Okay. Yeah. Yeah, you can have it. Do you want to come on stage or? Yeah. All right. So once again, the first sponsor talk, Juliet and Romeo, making Julia a hard real-time robot language. And I'll hand over, and hopefully the other people will be equipped with mics in a second.
Yes, thank you. So, Amina, there is one microphone for you here. Where is she?
I think she's
there. You are. Okay, that's for you.
See if it works.
So then Kaan is getting his microphone right now. Well, maybe we get slowly started. You will see our booth on the sponsor area, third floor. So this is a brief presentation of what this is about, to bring Julia into the world of robotics. Sorry. So we followed Julia from start. When we started the company, Julia started. But now it's time to consider it mature and do some real business. Okay.
Hello.
Okay, then let's start it. So my name is Claes Nilsson. I started Cognibotics about 10 years ago, together with some research colleagues from Lund University. So we are located in the very south of Sweden, in Lund, and we are now about 45 persons. So we are a deep tech company on a mission to create better, more useful robots for the many people, because the society needs many robots. But we start in factory automation, because that's where we have the real and demanding performance needs and requirements on productivity and high-quality workplaces. So that's Cognibotics. And then we have our partner.
Hello. Hello, everyone. My name is Ken Wu. I'm the CEO of Aston Automation. So Aston Automation is a 30-year-old robotics and automation company with our headquarters in China. Last year, we sold about 25,000 industrial robots. And we're also currently expanding globally. Welcome.
Okay, and there are many ways to instruct robots. Maybe you do manual guidance, you use gestures, etc. But it also means programming. And no matter how you instruct robots, there needs to be a textual language underneath. And there are over 200 robot languages in the world. They are old-fashioned. They have grown up from vendor-specific solutions, started with sequencing, adding flow control, and then, yeah, they do their work for that robot brand. But what the market needs today is a solution that brings different automation providers, technology providers together, such that the IT people can join the operational technology people in creating these better robot systems.
Yeah, I fully agree. You know, during our growth history, we also increasingly experience the need for better and new robot programming languages. To us, robot programming language is very important. You know, it directly interacts with users, and it also tells users what a robot can do. Also, in addition, you know, from industrial or automation world, there are also many devices and peripherals around the robot, which is right now controlled by traditional PLC languages. So I think this should also be changed. In the future, we would like to see a new robot language can control both the robot and also the peripheral devices. So I think the need is there. It's very clear. The only question is, in which way can we innovate it?
Yeah. So consider this event as the starting point for Julia, by means of Juliet, reaching out to both the community in robotics, but also other areas, like telecom systems, other types of automation, etc. And the emphasis when we developed Juliet and Romeo as a technology environment is coexistence. So that's why we are reaching out to other technology providers and interested partners to see how can we shape this technology to be more of a general usage. So together with us, we have here Jesper Öqvist, who is one of the main implementers of our compiler solution, and Amina Goyak. So we will now run a video explaining some of the specifics in the solution and how it relates to Julia. And then a couple of minutes after that, Jesper and Amina will maybe add some comments, and if we have time for questions, we can do that. But otherwise, let's run the video.
Present a new robot control environment and runtime, Juliet and Romeo. The origin of Juliet and Romeo comes from several decades of research and industry experience from Cognibotics and Eston Automation. Eston Automation founders and Cognibotics founders had visions of enabling new technologies in industrial robotics before having met. And when they did meet in 2015, their ideas aligned for a new product.
Some technical issue.
We are here to present a new robot control environment with a new powerful language and runtime, Juliet and Romeo. The origin of Juliet and Romeo comes from several decades of research and industry experience from Cognibotics and Eston Automation. Eston Automation founders and Cognibotics founders had visions of enabling new technologies in industrial robotics before having met, and when they did meet in 2015, their ideas aligned for a new product. The first 3 years of the development was about finding requirements and possible technical solutions. Early on, Julia was favored as the language itself has most of the required features and more. However, some of the requirements, such as having real-time garbage collection, raised some uncertainties for using Julia as is. After investigating further, it was decided to make a new language as close to Julia as possible. The language should use static typing for predictability, bytecode as intermediate format to fulfill user needs for interactive motion programming, real-time garbage collection, and a Romeo runtime designed for consistent low latency and preemptive multitasking. The requirement to stay as close to Julia syntax as possible is important and is only broken if predictability would be compromised. An important feature for Juliet is to be able to save as Julia to then run in the Julia environment instead. Juliet and Romeo are targeting the real-time domain for controlling robots and other machines, and Julia has powerful packages and libraries for digital twins and AI models, which is important in modern automation. This is Juliet. To the left, we have a Juliet program, and to the right, we have a robot simulation extension. The extension is showing an ER20 Eston robot. A motion kernel is feeding the simulation positional data. However, the positions will not be updated unless the motion kernel is being fed with new motion commands. These commands will be sent by the Juliet program. Juliet can be started either in run or debug mode. Stepping over the first function will initialize the connection between the program and the motion kernel. Stepping over the second function will initialize the connection between Juliet and the simulation. Now, going inside MoveRobot will show one of the few syntactic differences between Juliet and Julia, which is the var keyword. In Juliet, variables must be declared before being used. Since we are in debug mode, it is possible to set breakpoints. Running to this breakpoint will show that we have a program pointer as well as a motion pointer, marked by this robot icon. In the simulation, we can manually set a trace. Adding another breakpoint and running to that point now looks like the robot is drawing something. It is not uncommon for a robot operator to wish to change the code in an already running program. For example, there seems to be a line missing to fill this path. In Juliet, you can add modifications to your program without losing the current state. This kind of editing in a stop state allows for more complicated code changes, such as adding new functions. Now, the tool center point color is changed, and I would like to execute the motions backwards. This is possible in Juliet, because the motion library has defined behavior for backwards execution of the moveJ function. This is entirely expressed in Juliet, and that is possible due to Romeo runtime support. The last function in main will draw the 3 circles of the Julia logo. In this function, you can tell another difference from Julia, which is that variables can be declared without being initialized. The circles will be drawn in an infinite loop by first moving the robot linearly to the top position of each circle, followed by drawing the outline of the circle before filling it with a helper function. Note that the linear movement moveL has a keyword argument onFinish. This argument is a function which will be called whenever the motion finishes. The onFinish function will be executed asynchronously. However, if I add a breakpoint to the last line inside the while loop, you may notice that the program pointer does not stop there immediately. This is because the last motion instruction inside fill circle will block the current task until the purple circle is done filling, due to this sync flag. The kind of language features that Julia provides is unheard of in the robot programming world. This is why Julia is such an inspiration to Juliet.
For predictable runtime performance, we required static typing, and the compiler should specialize as many function calls as possible. This is to avoid unpredictable dynamic dispatch at runtime. Note that type declarations are optional in Julia, but in Juliet type declarations are required in certain cases. In Juliet we also wanted static checking of variable declarations to remove avoidable runtime errors due to undefined or unassigned variables. Another important requirement was fast incremental compilation and code loading. These requirements all led us to create the Juliet compiler from the ground up to support static compilation and incremental code generation. The compiler supports type inference, and the type system is very similar to Julia. The main differences being that we require static types, and all variables must be declared before used. Unlike Julia, we do not use LLVM, and there is no runtime code generation. Everything is statically compiled. In a few cases, dynamic type checks are required in runtime code, but we try to limit this as much as possible. The Juliet compiler supports macros and has a REPL. The Juliet REPL is useful for exploring the language. Here we declare a variable and do some computations. Let's print the result. Let's write a simple for loop. The Juliet REPL has a command history you can navigate using the arrow keys. Here we declare a function that doubles the input. The Romeo virtual machine has a real-time garbage collector designed to minimize latency and jitter in high-priority tasks. The fundamental principle, semi-concurrent GC scheduling, is that the memory management is organized so that work done in line with application tasks is kept to a minimum. The most part of the GC work is scheduled with a lower priority than the timing-critical tasks. By using fine-grained incremental GC, a high-priority task can interrupt the GC with very low latency. The measurements shown are the lengths of such GC increments on a Linux machine with an Intel Core i5 CPU running at 2.5 GHz. This is the GC times for an entire run of a multi-threaded Juliet application. Zooming in, we see that the vast majority of increments are below 1 microsecond. 0.12% of increments took more than 2 microseconds, and the longest increment in this execution was 8.3 microseconds. This indicates that the worst-case latency caused by the GC can be kept below 10 microseconds. That's all, folks. Thank you. that was not quite all. With final few words. So we didn't show much of the meta-programming. We do support macros, and it uses the same incremental, the same interpreter, compile time interpreter that the REPL uses. So it's very, very useful to have Julia-like macros in our language.
Yes, and we also didn't mention that the garbage collector has a dual heap and is concurrent real-time GC. And we didn't go into detail on the preemptive multitasking. So therefore, we invite you all to come to our booth on the 3rd floor to discuss Juliet and Romeo further. Thank you.
Thank you very much for the interesting presentation. In the interest of time, maybe one quick question, if there's one. There's one here.
Do you have any techniques for verifying safe state machine transitions or before the code runs?
Well, first of all, the language as such is safe. So now undefined execution is permitted. But other than that, we have a couple of projects ongoing or upcoming on state machines. So that's it's a topic to be worked on. And of course, we welcome the community input. And I think this is a perfect example also of where packages and solutions will be the same for Juliet and Julia. So the two communities can really come together and be one. Thanks.
I'm afraid in the interest of time we have to move on, but you can feel free to check them out at their booth, right? They will be here throughout JuliaCon. So let's thank them again.
Okay.
And then we'll make a switch and move on to our second sponsor talk, which is about JuliaSim. And I welcome Viral Shah, Gary Mansouri, and Chris Rokakis to the stage, which should already be mic'd up behind the stage. So let's welcome them with an applause, maybe.
I think the mic's for Gary.
Welcome, JuliaCon. Woo!
It's great to be here, everyone. Oh, is this? All right. So, this is the 11th one or the 12th one. I'm kind of losing track. This is an awesome venue. It's great to be here with everyone. We're going to take a few minutes to talk about what we're doing, at the company at Julia Hub. We started out by building a programming language, as some of you know, maybe. And we've increasingly sort of gone up the abstraction chain, building lots of innovative things for modeling and simulation. So for those of you who might not have seen this picture, this is how we like to talk about what we do. At the bottommost layer, the foundation is the community. It's all of us here. We all work on this shared and common vision for Julia. And we have this amazing open source ecosystem and packages. But as a company, in addition to that, what we do is we build Julia Hub as a cloud platform to run a bunch of modeling and simulation applications. And now we've gone up the abstraction chain, building products for modeling and simulation. Many of you have seen Pumas, which is a company that spun out and is something that we're very closely involved with. JuliaSim, which is what we're going to talk about in a little bit. Chris is going to talk about a lot of it today. And then we have Gary Mansouri from Boeing, who's going to also talk about sort of model-based design. And we have a lot of interesting things around JuliaSim that are coming up. The third one is Cedar, and we have a few talks at the conference about that as well. So this is sort of how we're building products as a company. I just have this one technical picture. I thought that people out here who understand compilers or who like working with compilers would sort of appreciate it. that the world of modeling and simulation has been these kinds of bespoke systems that are like hand hacked with all kinds of horrible in all kinds of horrible different ways built over the last 40 or 50 years. And one of our goals is to use all the beautiful Julia compiler tooling and abstractions and have a lot of different front ends, not just Julia, but whether it's a SPICE front end or a pharmacometric front end or a systems modeling front end, right? So you'll see a lot more of these evolve, leveraging a common backend that we've all built together. If you want to know more about this, find Keno or Chris later on during the conference. We have about, I think, 24 talks, or Julia Hub staff is involved in about 24 talks at JuliaCon. Many of these talks are actually in partnership with community members. I actually have, there are 3 pages of talks, actually. So these are all the talks. I'm not going to sort of wait for these. Without further ado, we'll have Chris talk about JuliaSim next.
Thank you very much. So JuliaSim is Julia really taken to industrial modeling and simulation, right? Because you might know a lot of companies out there, like, there's like the Modelica community with like the things like Dassault Systems. You have all the things that ANSYS builds, right? And there's also this company that starts with an M, which we won't finish, right? And so there, but the thing that is there about a lot of modeling and simulation tools is that they are written as bespoke software, right? You have one thing that does computational fluid dynamics, you have one thing that does, chemical process modeling, and they can't connect. And when the moment you try to connect all these, you have issues, right? And so the idea was, could we build a modeling and simulation platform with a common compiler, a common core, so that way we can optimize cross-domain modeling and make it work in such a way where we can deploy it to real systems and send it off as, flight software, automotive software, and all these applications, right? It's a lofty goal, but this is what we've been building towards with JuliaSim. And so JuliaSim has a whole stack here where we have these graphical user interfaces and VS Code extensions that make it so that way someone can drag and drop and build a very high fidelity model and then send this code to a system where they can then build out custom deployments with custom drivers and make it so that way all of the things that we do with machine learning integration, all the things that we do with all this like binary generation, all of that works as one stack that is in changing the way that we are building the models of tomorrow. And so here's a view of JuliaSim, and we'll be showing a lot of people things as is coming out, right? In the next year, we're really going to be showing a lot more material. So stay tuned and subscribe to our YouTube channels if you want to see all the things coming out on JuliaSim. Here you can see an early view of the graphical user interface. You can see that you have a drag and drop editor, and from this drag and drop editor, which works in the cloud, you can grab all of these different model libraries, right? So you have one of the key things that we've done with this form is that we have analysis components. So you can say, not just, I want to just simulate, I want to make a plot, but I want to run an optimization. I want to automate the discovery of new physical elements using data that I have. And I want to run a gigantic parameter search over a GPU cluster. And all of this can be done using this cloud-based modeling and simulation tool that we've been developing. And so one of the key things that we've been adding to it, too, are these built-in libraries, right? So there'll be talks on different libraries here. For example, we have a talk about the JuliaSim HVAC library, which is a high-fidelity two-phase flow system modeling the exact properties of these, a lot of refrigerants. There's a model library, or there's a library on JuliaSim batteries, which will be talking about different electrochemical models and how those are then used to be able to build models of battery packs that can be connected to other systems. There are multi-body components that we've been developing as well, and there's all these other talks that you should go to. So there's JuliaSim itself is not just a system for building models, but it also has a lot of these industry-focused, high-fidelity models that are pre-built, so you can just drag and drop in a digital twin of an HVAC system with a digital twin of a battery, and then build out this entire model of here's an electric vehicle, and what will be the what kind of battery will I have? What will the thermals be? And how will that affect the car design? Can all be built as one composed system,
right? And now there's going to be some talks on this new piece that we're releasing here, this JuliaSim modeling language, right? So the JuliaSim modeling language is the language that is it's a declarative language which is underneath the way that the GUI is built, and it has a very nice property in that everything that you do in the GUI shows up also in the JuliaSim language. If you make a change to the code of the language, it makes a change to the GUI display. You make a change to the GUI display, it also goes back. So we have this round trip ability between the way that you use code and the way you use graphical user interfaces. Because we have an idea that these graphical user interfaces of the past should be of the past, because everyone today is using some form of coding, and so you need to have code and graphical user interfaces live in the same world. And that is what we're really trying to make sure we can do to change this industry. And one of the other pieces involved with this is JuliaSim Studio, right? So JuliaSim Studio is a set of extensions for VS Code, and what you can do is you can take this model that you've built using the JuliaSim modeling language and the graphical user interface, and you export it to Julia Modeling Toolkit code. And so if you know Julia Modeling Toolkit, if you've been working with our open source tools, you get a full representation of your model, and then you can say, you can write your drivers, you can use the new JuliaC tools, and you can create, you can take the model code that you have and the analysis that you've done in the graphical user interface and create bespoke code for then the deployments to real-world devices. Last but not least, we are integrating the scientific machine learning tooling in every part of the stack. So you can see, for example, here's a demonstration we have of the digital twin generation, where you can build a physical model where you have like a real HVAC system, a real battery, and you say, maybe I used ideal physics for one of these pieces. And what you can do then is you can integrate a neural network into this process and tell it to train this neural network to improve Oh man, there's definitely something going on there.
I think the planes came out a little earlier than when Gary was supposed to talk.
So that's JuliaSim, right? And we're really working with the industrial modeling and simulation world and really building out a new tool that can make sure that we can bridge this gap between GUI to code to embedded devices. And so I'm really happy to have Gary here from Boeing, who will have a quick question and answer session to be able to describe, what are some of the things that Boeing is looking for, and just as one of these people to understand, who Julia Hub is working with in order to make sure that Julia crosses this gap from being a great language to being a great language for industrial computing. So Gary, we're going to have a few questions for you, and afterwards, if this question and answer session, if you find it interesting, we'll have a birds of feather session on safety critical software, which anyone can join, and that'll be right after these sponsor talks. So question number one, Gary, how does one go into a career on model-based design? So how does one step away from if you're an academic here and you really want to work on putting the software onto an airplane, how do they do this?
Thanks, Chris. First, I'm more excited than Chris, but I'm not showing it. So good morning, everyone. Very nice question. How does one go about a career in model-based design? So there are different paths. Perhaps the best path is to be good at something that you already do, whether it's modeling battery systems, electronic systems, dynamics of some sort, could be power systems, hydraulics, vehicle dynamics, whatever the path might be, even mechanical design. So be good at that. Then model-based design applies the whole set of processes to make the design come to reality. So model-based design is not modeling. It's using modeling via a process so that basically we conduct systems engineering with that modeling process. And that's what model-based design really means. And people tell me all the time, well, Gary, we have been doing modeling for 40 years. Why is this new? What is this? And so what is this about is to use modeling as a means of debugging, if you will, to refine your requirements early up front so that your design becomes virtually debugged before you actually design it, before you have the physical design. You heard Chris talk about the digital twin. It's really having a digital twin that represents your actual design such that your design is meeting very high confidence before it's done being designed. So how does one go about making it a career? Be good at one specific topic that you're good at, whether it's, again, battery design or dynamics. Understand the systems engineering with model-based processes and then apply to that, and then you become the go-to person. That's probably the best answer I can give.
That's a great answer. Now, the next question we have is, how is modeling and simulation used in Boeing? What are the types of things that get modeled? And what is the downstream effect on an airplane that is made?
Well, that's a very big question. So modeling and sim is used very, very broadly and extensively at Boeing. Pretty much almost anything you can think about on an airplane has been modeled to some extent. You have the fuselage of the body of the airplane, the wings, that are now composite. They all have been modeled. Then we can go into the structures of the airplane that has already been modeled. So that all basically CATIA, using tools like CATIA with CAD, CAM design. Then you go into the systems aspect of the airplane, where you talk about avionics, flight controls, actuation, power systems, ECS, which is environmental control systems. That's the cabin air and all that. And basically everything else. All of those systems have been modeled very carefully. The application of model-based design comes in where we actually use models as requirements so that we catch everything very carefully, not with a shall statement, but rather with a descriptive dynamic model. And so instead of having a switch written as a shall statement, you can have a transfer function that describes that switch transition. And so, but going back to the question, those are just the airplane design. Then there's all the, we're talking about the system installation, how all the equipment and parts and pieces come together. The flow and efficiency of that has been modeled. The production line, the flow of that has been modeled. The finance, parts assembly, parts delivery, the optimization of how that gets delivered has been modeled. And going forward in the future, even production system and the finance part of the company is being modeled. So everything basically is going through modeling and sim.
Everything is a model. And now, next question is, why does Boeing use model-based design? Can you quantify its effect on downstream processes, estimate things like dollars saved or development time reduced? And what can you give any examples of early detection of potential issues?
Sure. And that's a really, really good question. And this is basically my role at Boeing as a technical fellow. Model-based design, and this is based on data in the industry for the last 20 years, primarily from the automotive industry. The aerospace industry has been somewhat behind because of all the regulatory aspects, but model-based design based on industry data, you're talking about approximately 30% savings in schedule time and about that much in cost reduction. And that's very significant. So if you think about the overall traditional development cycle, you're talking about cutting off about a third of that. Also about a third of that in cost. But the most important aspect of that to us, to Boeing, is really the first pass quality, is improving quality, is getting something that when it comes out has significantly less problem reports. You can think about cars when you have a car that gets a recall. So it's to avoid things like that, minimize that. That's what we call first pass quality. And by the way, quality leads to improved safety. So, so we use it at Boeing to improve our first pass quality, but to stay competitive in the market, we have to utilize new technologies and new processes. And model-based design is an enabler for that. It's a way to using model-based technologies so that you have higher confidence in your design before you have the physical system in place. That's the answer.
Yeah, and there's a reason why people are saying like Boeing is a software company, right? Because a higher and higher percentage of the savings are coming from software developers like you. One last question we have here then is, what is the main thing that engineers need to know in order to understand software development for safety critical environments?
Okay, this is a very big question, and it's a very important question. So let me ask you this, and when you think about safety, what drives safety? One word I'm looking for. Like, what leads to better safety? Anybody raise your hand? Any? Accidents lead to lessons learned, but what I'm thinking of is an attribute that you use in your design to lead to better safety. Redundancy is a very good word too. Quality assurance.
I think we had someone with testing.
Get it, Boeing. You're welcome. So quality assurance. Now, all of those answers were correct, but quality assurance is what leads to safety critical environment. It's all about the quality. So how do we get to a quality assurance environment? It's really two things. The process has to be very well defined. So you have to have a very well defined process. That means you can just start coding or modeling. You have to follow a very vigorous process. And then you have to have a very, very strict set of requirements. And both of those are required before you start doing your modeling. So when you talk about flight critical, really the number one thing that comes to mind is quality assurance. And quality assurance, and that's your prize, is again driven by process and requirements. So there are two different processes that we follow per regulatory aspirations or requirements. One is DO 178C. That's for all software that is going to be used for flight. And there are different tiers of safety, different tiers of usage. Flight critical would be 1 or A. And then there is the DO 331, which is model-based software that's derived from models. So both of those two processes we have to follow as part of the regulatory authority requirements. And the fundamental starting point for that would be to have a very clear process that is captured, that we can follow and demonstrate that we follow that process. And that's what quality assurance comes about. And basically, it's a very extensive checklist of items that we have to do that ultimately includes qualification of tools. That means you freeze your tools for that. So that's a very high-level answer to the question. This question I can spend about a week and 8-hour days in different segments to answer. But I hope that gives you kind of an insight as to the extensive process and work that goes into creating safe flight-critical software.
And we'll have a whole birds of feather that'll be discussing about, what it is to be using Julia now within these, safety critical environments, right? Because we've been working with folks at Boeing, but also with groups like Pumas. We've been working with the FDA, right? As you know, certain therapeutics have been, fully processed and the clinical trials have been done with Julia. And so what does it mean to be programming in these environments, and what does it mean to be programming for these environments? If you're very interested in, how these open source tools have been growing and the industrial products that have been developed on top of them are reaching these standards, we'd be happy to chat with you more on during this Birds of Feather. So,
or if you're just curious, right? Like if many of you here are software developers, maybe have not worked with modeling or model-based environments, and if you got curious by listening to Gary, I suggest join us at 10:15, the Birds of a Feather session, and all questions are welcome, right? Like if you have anything that you'd like to learn, please come there. I know that working with Gary, I've learned a lot about what it takes to build software that you can trust. And so I request all of you who are curious to join us at 10:50.
Thank you, Viral. And thank you all for your time.
Thank you. Right.
All right. If I manage to get up there. All right, that concludes our very first morning session. We will have a short morning break now, and we will reconvene in the separate rooms with the separate tracks in them at 10:50. And yeah, see you guys around. Enjoy JuliaCon, and enjoy the morning break. Uh-huh. Oh.
And now it's your responsibility.
All right, hello everyone for this first session after the morning session. I'm afraid we are still missing the first speaker. At least I can't see Andrew. So Andrew, if you hear this, please come to the stage. Yeah, we'll see. All right, since Andrew isn't here, it's only a 10-minute talk. We will start at 11 with the next talk.
I can't hear. Oh, and it seems like we're working. Yes. Awesome.
Is the screen working? The screen isn't working yet. Can we switch to HDMI? Oh, the cable. Check the cable again. I mean, it's in there. Let me unplug and plug in again. Oh no, now it's working.
Oh.
Now something's
Okay. Can I move this onto the others?
There you go. All right. I think it's clearly visible. So welcome again, everyone. Sorry that the first slot, the first talk didn't take place. So it's my pleasure to announce Frames here to give the first talk of the session about the core compiler and plundering around with it. And Frames is obviously well known in the Julia community for various contributions to the core language, also the differentiation interfaces. And yeah, take it away.
Okay, hi everyone. So yeah, I'm Frames. Yeah, I'm here today to talk to you about a way of doing IR transformations, really. So before I start, I just want to say this is a much better location for any conference. It only took me 26 hours to get here. This is like a huge improvement over Boston, which took me 48 hours to get to. Like 26 hours is basically next door to major common locations with many Julia users like Perth, Australia. Very big city, not somewhere obscure like Boston. No one uses Julia in Boston. So more talks in this part of the world, please. What is this talk? So this talk is about writing custom optimization parsers in the same way that Julia itself does optimization parsers. This is in contrast to something like IR tools or even cassette, which is re-implementing a lot of the analysis and modification utilities itself. We're going to reuse all the stuff that the compiler itself has built in to do it, and that has some advantages. So this is used extensively in DAE compiler, which is the kind of underlying mechanics for the CEDA system. It's used a bit in diffractor, not all diffractor, but some parts of diffractor use it. And it's also used in Will Tebbett's new AD called Taper. This talk actually came from like a small gist I wrote to show Will how to do some things which he wanted to do. So yeah, why would I want to do this? So one thing you might want to do is run a different optimization pipeline. The Julia optimizer is actually heavily parameterized with a bunch of different options you can configure, but you can't actually change most of them because you're not running the optimizer. Julia is. But you could, for example, enable union splitting with more than 4 elements. The other big case is you might want to say generate multiple functions from one definition. So DAE compiler generates about a dozen different types of Jacobians and callbacks and all these other things that SciML universe likes from a single function definition that it does a transform on. This kind of thing requires custom intrinsics, which I'll be talking about towards the end of the talk, and also some analyses, which you'll hear about in Kenno and Shuhei's talk tomorrow, probably. Yeah, so just a big warning before we start. This is very unstable internals. This is so far from what is safe and easy to use. It is relatively stable. It's not as unstable as you think it is, but it will break on minor Julia versions. But hopefully the core conception of what I'm teaching will be useful in an ongoing basis. Up on the slide is the version number that these slides have been tested with. But yeah, it works on more or less the same on most versions. Another thing to note is a lot of the utilities are not in the base namespace. So people are probably aware, if you're at this talk, that Julia has 2 namespaces for a lot of things, core and base. A lot of the utilities live in core.compiler rather than in base, and that tends to break things like getIndex, which lowers the square brackets down to like a call to current module getIndex. So you need to bring those into the namespace of base where you'll actually run your user-written pass. I've got an example for how you can do that up there. If you look into Fracta compiler utils.jl, that has for every version of Julia exactly which things you need to bring into the namespace, and it's probably the best way to work this out. So if you're at this talk, you're probably very familiar with this. If you're not familiar with this, this talk is not going to be very accessible to you. So we start out and we've got the source code. That's a string. Cool. So we parse it, and then we get the AST. So this is where normal macros run. This is normal metaprogramming time. We lower it and turn that tree into a list. We get the untyped AR. So this is when Zygote runs. It's where cassette runs. We run type inference, and then we get typed AR. So this is where the Julia optimizer runs, and this is also what we're talking about today, is running more things on this typed IR. Finally, we do code generation to get LLVM-IR, which is where Enzyme runs, where GPU compiler runs. And eventually, you assemble the whole thing into machine code, and hey, you can execute that. Hopefully, that wasn't a surprise to anyone. So to kind of zoom in on what we're talking about, we're talking about this this typed IR. So I'm going to make the perhaps moderately bold claim that both the AST and the lowered IR are simple lexical transformations of the source code. There is no semantic information in here. It's not until you have types involved that you can really talk about the semantics of what the code actually means. I mean, we can't even resolve dispatch without knowing the types. So I'm going to say the typed IR is kind of the first level where we can really process the code in terms of what it actually means. So it's actually, I think, a really good place to run your code transformations because you can do advanced analysis. So if you've used the @code_typed macro, you've seen code IR. You've seen the code info object, which contains typed IR. For this talk, we actually want a relative of that. We want what's called the IR code object. It's just a different internal representation of kind of the same information, but with a few extra things that's going to be useful to us, which I will show you in this talk. So if you look at this code up here, this is what we're talking about. We have some function quux. It does some things. It's got some branches. And if you look at the code IR code, we can see, oh, look, it's a list. It's all in single static assignment. It's got some code. It's flat. It's got some jumps. It's fine. This is the kind of code we're talking about transforming. So to break down the parts of this talk, the parts of this code, the main thing we can think of it as is being a list of instructions. So an instruction has a number of parts. So the first part is the part we think about the most, the statement, SMT. So that statement is the expression. It's what it's going to do. Then we have a type, because the type is what we got for typed IR. But actually, when you look at this thing, the type isn't just the type. This is actually anything that's being stored in what's called a lattice, which I think you'll probably hear about a bit more from Kenno and Shuhei tomorrow. So there are other things that store in here, like information about, hey, this is actually like the constant 5. The other one we have to concern ourselves with is the flags, which I'll talk about a bit later. An important thing to note when working with these instructions is to always use this square bracket colon statement and those other square colon forms, not dot statement. The fields of these objects are very scary and nasty, and they don't work the way you think they would. But we have this getIndex overload, which makes it easy to work with them. So I said the main bit was the expression. So people should probably be pretty familiar with expressions because you see them in ASTs all the time when you're working with macros. The only thing special about this in the IR is that it is in what's called single statement assignment. Basically, each statement only is single and it's assigned to its position. So we can have its position is 1, it's the first position. And then we can have something we're assigning to it. But this one, foo brackets 2 times 2, close bracket, that's not a legal single statement assignment because there's 2 statements there. There's the 2 times 2 and then there's the call foo on it. So it actually needs to be broken down into 2 statements. So first we're going to multiply 2 by 2, and then we're going to call foo on the result. Not too surprising, I think. So you've seen this before. We have SSA values. So those represent both positions and values, because a value is always assigned to hold its position, or a position is assigned to hold its value. And yeah, you can see here that you just see this %1 that shows up and %2 that shows up, where in the place of basically a variable. Cool. So arguments are the other thing, which is very closely related to a SSA value. They're basically SSA values that only have values. They don't have positions. They're just the arguments to the function. So you can see here the code for plus. It just calls addInt on the second argument and the third argument. The first argument is the plus object itself for the function. Yeah. Literals. So we're all familiar with literals like 1 and like a string like hello. But you can actually put any literal into the IR. You can do that in Julia itself just using like add eval and interpolate them in. And if you look at the R code, we can see that it's actually interpolated in the value there. This does have weird effects. Like you can mutate that thing, and it will persist the mutations across the calls because it actually lives in the IR object. It doesn't live in a variable. But yeah, you can see that there. We can contrast that to if we hadn't interpolated it in, which has this big pile of code where it's actually constructing at runtime rather than having it pre-computed and constructing at compile time. In general, it's really useful to insert literals because you can often work out, say, a tuple of indices that you needed to know, and you can just compute those all at compile time and insert them straight in, rather than having to like insert the code to generate a tuple. Invoke and call. So again, everyone should be pretty familiar with call. It's what calls a function. In IR code, we have a second one called invoke. Invoke is like call, but we get this extra first argument before the function, which is the method instance. So invoke is used when there's a static dispatch where we know which method instance we're going to hit because we've run type inference and have predicted what methods we're going to use. So invoke, yeah, invoke's better because it's fast. It's what makes Julia fast. But generally, you don't want to write it because working out what methods you're going to hit is annoying. So generally, if you're inserting them manually, you can just insert the call, and then you can just run type inference, and type inference will convert all the calls into invoke if it's inferable, which is good. It's good to just reuse stuff type inference does. At the cost that you are having to run type inference probably a second time, and maybe a third time, depending on how much stuff you're doing. OK. Cool. So basic blocks. So let's see. Can you actually see all my code? You cannot. That's OK. There's nothing much missing at the bottom anyway. So we started out with code which like a quux, and that's an expression tree. Like it's got all these branches. The if statement is a branch away from the other statements. But when we do lowering, we flatten it down into a list. The type IR is just a list of instructions in order. However, we do need this structure. This structured information is actually very useful to us because we want to know things like what variables have been defined. We want to know possible paths you can take through the code. To do that, we have a structure called the basic blocks where we break down paths that you can take through the code into sections that are always in front of each other. And you can see those here on the code where we've got this. There we go. We've got this one. This is the first block. It's got 2 statements in it. And then we've got 2, which is the second block, and it's got some more statements in it. Yeah. So then from the basic blocks, we can construct what's called a control flow graph, which is every possible path through the code. And you can see here, these are the possible paths through the code we have on the slide before, where you can start here in block 1, and depending on the result of the if, you'll either end up in this block, or you'll go straight to this block. And so you can use that to do various kind of analyses, and it needs to be maintained. It's one of the things that you get from IR code that you don't get from code typed. Yeah, these things have previous and successor, like a general graph structure. OK. The other weird thing, so even if you're familiar with cassette and zygote and stuff, you won't have seen before, is these things called a phi node. So a phi node is basically, it's basically like an if-else, where the condition is what block I came from. So this phi node I got up on screen says to return the value %8, SSA value 8, if I was previously in block 2. Or if I was previously in block 4, return %17. It's basically, it's got hysteresis. It knows where it came from. It's kind of almost the opposite of a go-to. It's an if came from. And you'll see those anytime you work with code that has any kind of branches in it, basically. Yeah. So, on to how to do things with this structure. So a basic thing you might want to do is replace an instruction. So to do that, we're going to get out the instruction. We do that by indexing the IR object with the SSA value. Now we're going to change the statement to be some new statement here. We're just going to set the info field there to no call info because we're not doing anything special. And then if we know the type, then we can put the type here. But if we don't know the type, we can just put any here. And then we can add this flag, IR flagged refined. And that says that when you go and run type inference, please go and find the type for this thing. It's changed. You need to run it again. You don't have to. You could just leave it as any. You could not run type inference again. But the net result will be your code will be very slow because all your dispatches will be dynamic, which is generally not desired. But it does speed up your compile time, so maybe you want to do that. Deleting instructions. So functionally, we do not delete instructions when working with this structure, because if you delete an instruction, you make all of the IR numbering wrong, and it gives you no real gain. Instead of deleting the instructions, we just set the instruction statement to nothing and the type to nothing. And that will then have no effect on what actually runs, and when LLVM runs, it will delete this instruction anyway because it has no observable effect. Inserting instructions is a bit more complicated. So we have this new instruction, which takes a statement of type, info, which defaults to none, line, which defaults to copying line above, and flag, which it works it out. But mostly you just pass in the statement as type, which again you could pass in the type as any and the flag as refined. So you get this instruction, and then you're going to insert it with insert node at the position. Attach after just says that if I said position 1, does it attach it at the 0th position or the 2nd position, depending on how you count it. Inserting instructions. I guess the other thing that's kind of interesting when inserting instructions is if you're trying to do something non-trivial, you might have to insert a lot of instructions. That's a pain. I recommend against doing that. Instead, you can just go and create a little function locally to do the thing you want to do, and then interpolate that function in, and then when you run the optimizer again, it will inline all that, and it'll be as if you'd manipulated the code to do something more complicated, and that's easier than directly creating like 10 instructions to do some non-trivial operation. So the other thing to note is that when you insert a node, it's actually left pending. It's not actually inserted. Immediately, you can see here it's up in green. And what's actually done is it's recorded this as a pending insertion at this location until we run this compact instruction. And the compact instruction, basically, it says go through and insert all the pending nodes to be inserted, because we don't want to insert them immediately, because if I insert like 5 of them, that would involve renumbering all the IR 5 times. So we just pen them all for later and run compact. The downside of this is a whole pile of other transforms you might want to do. Probably assume there are no pending nodes, so you may have to call compact every time you start a new optimization pass, depending on what you're trying to do. But yeah, basically go through, insert a bunch of instructions, do whatever you like. At the end, call compact, and you get back new IR that has all the new code that you've changed. Yeah. The other more advanced tool that I don't have time to really go into today is this core.compiler incremental compact. What this lets you do is lets you iterate through the code, compacting it, while also making changes. So you can express your whole problem as like a series of calls to incremental compact that just loops over the code again and again, each time fixing up the pending stuff from the last. But it's a bit harder to write, and it's a bit more fiddly. And yeah, this talk I only have half an hour, so I can't do it. But I recommend incremental compact if you're really getting into writing optimization passes. Cool. The last kind of special feature I want to talk about is what's called a custom intrinsic. So for our purposes, a custom intrinsic is saying it has special handling by our custom pass, and that doesn't end up in the final code after our passes are all done. So a major use of this is to push things into a custom lattice during abstract interpretation, which you may hear about from Keno later on during the conference. But yeah, I'll show you kind of how it goes. So to insert a custom intrinsic, we basically want to create a function that has no real effect, but that definitely ends up in the code that we're going to observe. So to do this, we need to turn off inlining, so we know inline it. Otherwise, it could be inlined away, and we wouldn't be able to go and identify it during our pass. We need to put a compile barrier const here so that it doesn't ever get constant folded and thus deleted from that. And that's generally enough to make sure it won't be deleted. However, if you also need to avoid it being deleted due to dead code elimination, say it's on a path that is provably not taken, but for some reason you want it to like show up anyway, which is an unusual thing, you can also add a base.do-not-delete inside it, and then it won't be able to be deleted even by dead code elimination. The other thing you do is you declare its effects using assume effects manually. You could also insert these effects later in post-processing, but generally we want to like just do this here, and then we can just update it with whatever we replace it with. So here I've added the no throw and the effect free, which is generally true for most things I've seen custom intrinsics used for. To show you a bit of, show you how you kind of use this. So we can go through all the IR statements. We get out the instruction, we get out the statement, we check, is the statement an invoke? Yes. If it's an invoke, is the type, that's the argx type, args2, if you call singleton that, which just converts types into singleton instances of those types, is that compile datetime? If so, we're going to replace the instruction with datetime.now, and which has type datetime. So this custom intrinsic basically inserted into our code at compile time the current date time that it was being compiled at. I don't know what this is used for. Someone might want to use it. It's a kind of novel thing that you can do with a custom pass that I don't think you can do very easily in other ways. But yeah, that's a custom intrinsic. So to talk about how to kind of hook this all together and run the full compile pass pipeline manually, the first thing to do, you want to get or create from scratch this IR code object. So you can either get one and then transform it, or you can create entirely based off from scratch. You're going to run inference on it. You're going to run optimization on it. And you're going to give it to an opaque closure and tell it to compile that into executable code. That's not necessarily the intended use of an opaque closure, but it is a thing you can do with an opaque closure right now. Valentin next might talk about kind of the more future sensible way to do this, or he might not. Valentin is shrugging. So I'm going to go through these kind of steps. So how do I run? I've already talked about how to kind of transform and create these. So how do I run inference? So here's the code that you actually use to run inference. So we get an empty method info object. We look up the world age. We get the spec type. So this is the types we're going to specialize on. Here we're just reading it from the ir.arg types, the IR that we're passing in. And we get the interpretation state, which is made up of all these things. And then we run this core.compiler IR abstract constant propagation. Effectively, this runs type inference and constant propagation. That's how we run it. So to do this, we're going to need some parts. We need the IR code that we've already generated. We need an interpreter, and we need a method instance. Basically, where we're going to put it. So where do I get an interpreter? If you have a custom interpreter, then you already have a custom interpreter. Yay! Assuming you don't, you probably want to use the native interpreter. That's the one that is built into Julia itself. So this thing is called a compile native interpreter. It has two sets of parameters. It has the inference parameters and the optimization parameters. So the inference parameters are stuff like this. This says stuff like maximum union splitting, how much to splat tuples, other things to determine kind of how hard it's going to try to infer things. It actually has a really good docstring. Bits of this has really good docstrings, bits of this doesn't. The other thing we've got is the optimization parameters. So this controls, in a big way, it largely controls inlining. So you can make it more or less willing to inline things. Do a few other things. Assume fatal throw says any exceptions can be treated as just fatal and won't occur, or if it does, you'll add error versus like actually needing throws to be able to be caught. There's a bunch of parameters here that you can set, and setting these is kind of one of the neat ways you can reconfigure things. But yeah, we can create native interpreters. That's fairly straightforward. The other thing we need is a brand new method instance. So there's not much to this. We have this C call of this particular function you call that just gives you a new method instance. Then the only other parts we need is to set the specialization types and the module. So the only interesting thing here is we can take the archetypes and we're calling this widen const on it. And that name is slightly deceptive. What it actually means is to discard all lattice information that isn't type. So the main source of lattice information isn't type is the fact that something is a constant. Thus the name widen const. It just gets rid of the const part of it and leaves you just the type. But yeah, that's a case controlling what it should be specialized on when it compiles. And then to just bring this all together, we get ourselves a method instance, we get ourselves an inferred version of the IR on that second line. We create the stuff to run the inlining pass, and we compact. Then we run the SROA pass. What's that? That's scalar. There we go, scalar replacement of aggregates. It basically turns structures where you access the fields, it basically deletes the structure and just leaves you with the fields, which gets rid of a bunch of get index operations and things like that. We do the ADCE pass, which is the aggressive dead code elimination, and again, we compact. And those are kind of the actual main optimization passes that exist in Julia. So by running that set of things, you've basically run the optimizer at this point. And then we verify the IR to make sure we haven't made anything illegal, and pass it to the opaque closure. So you can insert kind of your custom passes either before or after inference would be the normal place to run them. Or you might want to insert them like after you do some of these things and maybe do them again later. But that's basically how you use this. Cool. Yeah, just some final points. So if your code segfaults, it is really, really easy to make things a segfault when you work at this level. The first thing to do is to use verify IR, and that checks most of the assumptions that the compiler makes. I would say that if you've got code that segfaults, it's worth opening an issue and being like, hey, is verify IR like not capturing this? Or am I doing something sufficiently obscure that verify IR can't catch it? In particular, if you are using incremental compactor that I looked at earlier, you need to make sure you're not modifying the IR that is being compacted while you're compacting it without using the incremental compactor interface. Yeah. But if all else fails, run Julia in GDB. It's awful. But it's also like kind of the only thing you can do to debug a segfault. I would really appreciate if someone would run like a whole JuliaCon talk just on using GDB, but yeah. To conclude, let's talk about what you can do now. So you should be able to now understand the optimization part of the compilation pipeline really well. Hopefully you'll be able to write IR transformations to use the compiler's own utilities to do your own cool custom transformations. As a fun challenge, you can write a function decorator macro that does the IR transformation of your choice on the function it decorates. If someone does this, or wants help doing this, come bother me during, I don't know, the hackathon or during a break. I've done just enough code to prove you can write this as a decorator macro. It's neat. You can make a function that does more optimization than normal. Yeah. Cool. That's all I had. So
Thanks so much. I think we have time for one question. Maybe you can already switch notebooks while we take the question. Is there a question from the audience? Yep, over there, Mason. Can we get a mic there? Perfect. Downstairs to the right. Downstairs to the right, Max. Mason, you can help him maybe? Yeah.
So in some ways, these working on the code IR and using opaque closures and stuff is a big step forward because we can actually work on typed code.
Yep.
On the other hand, it's a huge step back compared to generated functions because I can't, with a generated function, I can stick that in the middle of my code pipeline and it will only do the compilation step, this big heavy compilation step in the middle of the code pipeline if it hasn't been compiled yet. Whereas I can't do the opaque closure construction in the middle of some pipeline with zero cost.
Right, yeah. If you want to do something like this, you need to manage the opaque closure construction yourself. You need to manage the caching yourself of these things to avoid that. But also, if you can write your function with a generated function, like definitely do that. That's way easier to maintain than like a custom compiler pass.
So is there any hope of kind of having the advantages of a generated function for these sorts of things in the near future?
Maybe.
Yeah.
All right. Let's thank the speaker again. And before we move on to Valentin's talk, just one comment. You might have noticed there's a bit of construction noise in the background. I think it's still kind of acceptable, but if you have issues, hearing the speaker properly, there are headphones that you can get where, the audio is live streamed too. So feel free to grab a headphone if you like to. Having said that, let's move on to our next speaker. I think Valentin, doesn't require any introduction, I guess. He's brought to us lots of interesting features, including the caching that he will talk about. And Valentin, take it away.
Thank you. And thank you, Frames, again, for this fantastic talk. I think I'm glad to have it, because then I can skip over other things that I otherwise would need to explain. So if you're just coming in, I'm sorry. So my talk today is about compiler plugins and non-native caching. And I'm going to start at the back and end with compiler plugins. So if you remember this slide from last year's State of JuliaCon, we managed over the last couple of releases to greatly reduce latencies, primarily time to load and time to first X, which is our lovingly name for this desire to get a cup of coffee the first time I start Julia in the morning. Nowadays, time to first X is massively reduced, and that's fantastic. How did we manage to do so? Well, in the beginning of the world, when Julia was very new, we had a concept called system images. So I went back and I looked at when this was introduced. System images are essentially a serialized state of a bootstrapped system. And this is a common thing in Lisps. So we load a program, we run some code, and then we white out the state of that program, and then later on we reload that. And that's what a system image is. Jeff added this in 2014, 12, 13, very early on. It's a part of 0.1, so there was never a world where we didn't have this. But even in the beginning, system images did not include native code. Native code is a machine code that your machine will actually execute. It's object files, stuff like that. So this was added 2 versions later. So this was added by Jamison. You can look at the pull request. It's a long discussion. And at the end, everybody is like, oh my god, everything is so fast now. Julia is actually usable. Great choice. But we didn't have the same thing for packages. So in the beginning, all Julia code was in Julia. And then slowly packages started to emerge as a concept that people wanted to have. And the packages became bigger and bigger until they became the behemoths that is now the differential equations ecosystem, or Maki. And so in 0.4, Jamison added the first notion of incremental compilation for packages. And it's the same notion we start a fresh Julia process, we load all of the dependencies, and then we run code, and then we save out the change. What changed during this process? That's called a pre-compilation process, and that's what Julia is doing while you're waiting for the progress bar to finish. But this did not include machine code. It only cached the state that it was generating. So it took a couple of years, maybe 10 or more. In 1.9, Tim Hawley, Jameson, and I introduced package images, which are essentially incremental compilation cases with machine code attached to them. And we needed to rewrite the serializer. We needed to figure out how to do this in the first place. And it was an interesting journey to get there. So just to give you a little bit of a terminology, when we talk about functions in Julia, we're talking about the name. It doesn't have any methods yet. So if you just type function solve end, you introduce the name solve as a thing in Julia. That's the function. Then we attach to those functions methods. Those methods have a type signature, and that type signature is used for dispatch. But when you then actually call that method, we take the signature of your call, and we specialize and we look up which method to actually call, and we call that a method instance. But we're not done yet, because that method instance is valid as long as the method hasn't been redefined, but other things might have changed in the system. So we have a fourth concept, which is called a code instance, which says this instantiation of this method instance is valid in these worlds, and here's a function pointer you can call and jump to and execute this code. So basically, we have a four-stage process to look up, going from the name that you typed in with the arguments that you passed in, to then actually finding which function pointer to call in the system. I'm glossing over this. This is basically what Frames was talking about earlier. And we have tools to work at the levels of compilation. So if you want to look at what code is being executed by a function, you can use edit in there, which to find out what actually is being executed. You can work with macros. You can look at the output of macros. You can look at the lowering process. We have typed IR. And as people mentioned, we have generated functions. We have cassette parsers, all of that fun things. And then at the LLVM level, we have LVM.gl, so you can generate your own code because you're targeting this newfangled vectorized processor that nobody else has ever targeted before. And then at the very bottom, LVM.gl actually provides an ASM call. Please never use this. If you really need to use it, come talk to some of us before. Also, never look at code native. Always look at code LLVM. You don't have an Intel processor running into in your brain, and the code is confusing anyway. But when we zoom in, we actually, as Frames mentions, we have a little bit more of a complicated story. We don't just have one typed IR these days anymore. We have 3, 4. Depends who is counting. So we start at the linearized IR, which is the IR that has not yet any type information attached to it. It's just your program as you have written it, but it's made slightly easier for the compiler to understand. Then we run type inference over that. We start annotating this with types. Then after that, we now prepare the IR for optimizations. We translate the data structure from code info to IR code. That's what Frames was talking about earlier. And we can start munging about and hammering on it. And we have a whole host of optimization parsers written in pure Julia. And we hope to write more optimization parsers in pure Julia on that level. And then we will finalize that typed IR so that the compiler, the LLVM code generator, can understand and consume it. That's the output of add code typed. And then we pass it to LLVM, and LLVM does things with it. Oh, we pass it to CodeGen. CodeGen generates LLVM IR. And then LLVM optimization parsers run, and so forth. So why package images was a great success, and why we have this complicated and sophisticated Julia compiler, we run into an issue that code that was supposed to be running on the GPU was not being cached. And it sounds like, okay, maybe you're running like a couple of kernels. That's a couple of seconds per execution. Is that really a problem? We did a Gordon Bell attempt 2 years ago, which is basically trying to run the biggest number of floating point operations on a supercomputer possible. And our startup time was roughly 13 minutes. If you multiply that by the number of machines involved, you end up in a crazy world where you spend weeks of your compute allocation, weeks of compute hours, just compiling GPU code. OK, so why can't we just do the same thing again? Right? We figured it out how to do it for the CPU. Why can't we just figure it out for the GPU? Well, part of the issue is that GPU compiler talks to the underlying infrastructure, but the underlying infrastructure is not necessarily meant for GPU compiler to exist. So we always work at the boundary of what is technically feasible and at what is advisable. And most of the time, we are away from the advisable and do new things and try to get this infrastructure working on this ever-changing software platform called Julia. One of the primary things that we can't do is we can't leak inference results or optimization results into the native cache. And that's also true for what Frames was talking about. It's a big no-no to apply a custom transformation and then leak it to the compiler and just be like, ha, your assumptions are still true. Please execute this code, and I don't want you to crash. The compiler will probably crash. So a master student of mine, Colin Warner, spent a year long experimenting with how could we integrate these systems. And the big issue he ran into was the fact that we are doing incremental compilation, and we're filling these caches incrementally, but then we need to serialize them. And that serialization process was very tricky, because you need to figure out what existed before, what existed now, what is the difference, and white only out the difference. But we have an incremental cache. Okay. It's built into Julia. So why don't we just use that? Well, the pull request we merged last fall introduces a new field to code instance called owner. And this owner is just a token. And that token bifurcates the cache, and you can use it to look up into that cache and say, I want the compilation result just for this abstract interpreter, for this GPU compilation, for this whatever I want as a transformation. And with that change alone, we we improved compilation times by quite a bit. So on the left side here, the red numbers are if you just run in the REPL on either 1.10 or 1.11. And this is where, if you sum this up, it's 13 minutes or something like that, and it's ridiculous. This is an ocean simulation. It has a lot of different small GPU kernels. If we actually use package images and do pre-compilation with Snoop compile, the situation improves dramatically. But we are still talking about more than a minute to actually get going. And then when we enable the GPU cache, we slice off a good chunk of that time. We go from 69 seconds to 44 seconds, which is a good improvement. But the question is, can we go lower? What are we spending our time now on? This is a little aside. If you're wondering how to do this, you can actually use package extensions, which is new, to also compile GPU code. So you can define a package extension that depends on CUDA, and then when only CUDA is loaded, you can say, if CUDA is functional on this machine, also run the pre-compilation workload and warm it up for CUDA specifically. It's a very neat way of making sure that you don't depend on CUDA in your main package, and you only add it and necessary capabilities in later when needed. So the on-disk cache is a pull request that originally was written by Tim and then rewritten twice in the meantime, and was flying around. It was very experimental. So what we wanted to do is we wanted to save machine code as well. But because we have many different versions of GPUs around, it didn't feel right to bake it into the package image itself. So instead, we are writing out small files into a Scratch directory that contains the necessary assembly, so that if you're changing options or flags, or you're changing GPUs, you can still cache it, and the next time you execute, you don't get a cache miss. With that improvement, we went from like 44 seconds to 12 seconds, which basically is acceptable. It's still not perfect. I think there are some things we can do, but also very important for me was that these time steps is where the actual GPU code is being run, and this third time step is when we're actually executing the model for the first time, as we will for all time steps from now on. And so that went from like 3.6 seconds to 0.02 seconds. So basically, the overhead of compilation went away entirely. So now switching tact, going back to talking about what Frames was talking about earlier, compilation and compiler plugins. We have this very powerful tool in the ecosystem called Cassette. And if you've played around with transformations, you might have encountered it. And it's been starting to bit rot, and it's not... There are issues with it that are hard to fix. And so the question is, are there better ways of fixing it? I understand Cassette as primarily a tool to apply code transformations. Other people see it as a tool to do other useful things. But at the core of Cassette is a code transformation engine. In order to do so, it transforms all calls that look like f of args to a call that overdubs context, f of args. This allows users to run code transformations, similar like if you were to take add code load, extract the code, and start editing it manually. But Cassette confuses Julia's inference engine, because now every call looks like we are calling overdub, which we'll call overdub, which we'll call overdub, which we'll call overdub, and ad infinity. So it looks like it's a very recursive program, and we have heuristics that say, this is too recursive, slow down, we don't want to run our inference engine for the rest of the heat death of the universe, let's stop here. So we fixed this very early on by introducing this beautiful hack that is called method for inference heuristics, where you say, hey, by the way, yes, this looks like you're calling overdub, but actually you're calling f of args. It's beautiful. It's a hack. We should not do this. It also relies on generated functions. And while generated functions are very powerful, they have an Achilles heel. Generated functions only work on concrete type signatures. So if you have an abstract type signature, the generated function will not run. Your generator will not run, and we will not generate IR, and inference says, oh, you know, this is any. And it sounds fine, because, I mean, isn't all interesting code statically inferred? But actually, it turns code that used to infer well and turns it into code that doesn't infer well anymore. And so it can ruin inference on user code, and it can ruin things like parse or rand. And suddenly, you're in a world of pain that you can't recover from anymore. So closing over this is Frames basically talked about this. We have this notion of an abstract interpreter. It's a bit of a misnomer. Abstract interpretation is a technique that inference uses. An abstract interpreter in Julia is an API to modify and extend our compiler pipeline that includes abstract interpretation, but not only. This is probably hard to read from afar, but there is a recent pull request that I was fiddling about, which shows an example how to modify the abstract interpretation engine in GPU compiler to add support for deferred calling, and basically introduces a custom intrinsic for GPU compiler to do some challenging transformations. So somewhere in November, I couldn't sleep, and as one does when one doesn't sleep, one goes onto Twitter and posts bad thoughts. So I just had implemented scoped values, and it was I started to enter the era of everything I need is a scoped value anyway, so what can we do with it? If you want to know more about scoped values, I have a talk in a little bit about them. And so I was like, couldn't we just implement the compiler as a scoped value. Well, then I implemented tag code instances to solve the GPU compiler cache problem, and now we have this handy owner field on our code instances that we can use to do cache lookups. And then it was end of November, and I still couldn't let this thought go. And in some conversation with Keno, I was like, really? We should just do this. Well, there has been a PR up on GitHub that if you intentionally avoided the word compiler plugin or compiler instance or customization of compilers entirely, and I just called it support execution of code from external abstract interpreters. What Frames was talking about is you run your abstract interpreter, and you get this object, and then you stuff it into an opaque closure, and you feed it back into the compiler, and trust me, this is OK. So can we do this a little bit more formally? Can we customize compilation on a scoped level? We don't want to do it globally. We all have experienced how global flags can turn to ruin very quickly. So the core concept is very simple, almost trivially. So each task, which is the Julia unit of code execution, gets a new field, which essentially is a scoped value, but implemented as a privileged one, because we need really fast access in the places where we don't have scoped values yet, like in C. And that carries a compiler instance. And then we use that compiler instance as the value that we store into the owner field of a code instance. And so when we do a lookup, when we search for the compilation result, we say, look at the current compiler, search in our cache for the entry that is correct for that current compiler. It has a very minimal API. You can get the current compiler. You can construct an abstract interpreter from a current compiler, because abstract interpreters are ephemeral. They come and go, as do those. You can get a compiler world, and I'm not going to talk much about this, but that's a fascinating concept to freeze the execution of your code, to not have to big invalidation pauses when you start messing about with things. And then the core primitive, which is invoke within. So you give me a compiler, you give me a function and its argument and its keyword argument, and I will switch contexts, and it will execute within that compiler. So how does this look like? These are examples taken from the pull request. Here I might want to implement a common use case for cassette, which is to replace functionality. So let's say I have a function sine, and I want to change it to the function cosine because I feel evil. So I want to define an overlay, and so we have these method tables that allow me to define these kinds of transformations. But now I want to execute with my new custom method table, where I have put all of my tricks into it. So I define a compiler that now carries the method table. I define a new abstract interpreter, which is what you need to do in generally speaking. I tell the system how to construct that abstract interpreter given my compiler. And then I tell the system, by the way, when you're looking for the method table for this custom interpreter, well, this is how you construct the method table to use as a lookup. And so here we now construct an overlay method table that uses this overlay that we have defined. And then at the top, we have this overlay function, and that's what the user could see. Right? The user could come with a method table, pass it in, construct my compiler, and that works. Well, it almost works, but it works to the first abstraction. So what other compiler plugins could I construct that are useful? Well, one thing that is very powerful is optimization passes over typed IR. So when I'm prototyping a new optimization pass, and that might be loop invariant code motion, global value numbering, anything else that is currently flying about, it might be very useful to go about and generate a new compiler plugin and be like, hey, by the way, you can just install this package, and you can try out my new snazzy optimizations. I have an example for multi-line fusion, that will come up in a little bit. I could do tracing. I could instrument every call and say, I want to capture all arguments to this call, write them out in some data structure, and when this function returns, I want to capture that return as well. One big caveat is we don't have context arguments like in cassette. But what do we have? Scoped values. Scoped values are great context arguments. So problem solved. One thing that I haven't implemented yet, but which I would want to do with this system, is to implement scope bounce check elation. So that you don't have to set globally bounce check equals false, but you can say in this subgraph of the program, turn off bounce checking. So multi-line fusion is something that works over untyped IR. And why, I will talk a little bit why about we need untyped IR here. So we have a program that uses podcasting, and it does like A dot times B and C dot plus A. Now, because in Julia, podcast fusion only happens over statements, these two lines separated each other could be inefficient. So in IR, in untyped IR, this code looks like this. And this is where I disagree with frames. This is actually the entire semantics of the program, and everything else is accidental. So now I want to turn this into this, which is basically C is no longer created. I removed the materialized call, and instead the podcasted in statement 4 now takes the argument in 1. And that is valid. But that is only valid to do before inference, because podcast, as it is defined, uses inference in sense of allowing customizations on the user level. And so those customizations might change depending on the tree of operations that is being presented to the user. So if I do this after inference, the user has no option anymore to customize this correctly. So one challenge of compiler transformations is, do we do before or after inlining? In the beginning, I was like, hey, let's do everything after inlining. That makes my life so much easier. Except when you then realize that the code that you're now inserting 17 times. Julia does bottom-up inlining. So we inline functions coming from the leaf nodes of the program upwards. So if I'm applying my transformation after inlining, every time I'm applying these transformations over the entirety of the inline graph. And so we get a combinatorial explosion of instrumentation if you're doing instrumentation. So do it before inlining. When I'm inserting instrumentation, I was like, oh, I just insert this call to this new function, instrument. Well, now inference will come and visit that, will run my pass that instruments that function, and now I'm instrumenting instrument with instrument. And afterward, I will instrument with instrument because instrumenting was not good enough yet. And you also get fun recursive loops that nobody wanted. So you can change that by just saying, OK, I'm now inserting an invoke within. I'm switching back to the native interpreter for this particular call. Everybody wants to work on typed IR, or maybe even LLVM IR. And some wise person once said, don't do that. That's not correct. And I have to agree with that wise person, who may or may not be in the audience. The problem is, what is semantic Julia code? Semantic Julia code is the code that you are written and you're running, and it may run unspecialized. Your inference may never see your code. Your optimization pass may never run. And so if it's important for you, to the correctness of the program, that your transformations are applied, because otherwise they're semantically wrong, like automatic differentiation. You can't do it over typed IR because there might be environments in which typed IR is never executed. It's only untyped IR. So the most reliable is to do transformations upon IR lookup. And so there is an extended interface to the abstract compiler interface to basically customize that. And theirs is a more powerful version of a generated function. And I'm out of time. So one idea is we could use this to actually customize a lot more about Julia. So we customize the bindings, the methods. We could execute this in the same Julia program as separate instances of code by separating the compiler instances. The PR exists, it's up there, it compiles, it kind of works. It's stale, I need to rebase it on current master. This may never land. This is a proposal. It hasn't been decided on yet. I'm putting it out there to see if this is what we need or if this is not sufficient yet. So if you want to work on this, talk to me later.
All right, let's thank Valentin for the great talk. Are there any questions? I don't know who raised the hand first. It was close. Maybe Oliver. I'm not sure.
So if tasks then basically replace the compiler with a new compiler, and then I guess this will propagate to tasks they start.
Yes.
How will this layer or compose?
That's a great question. It doesn't. In contrast to the cassette, it doesn't compose. You could, in theory, the problem is you have multiple levels to expand. And so it is unclear which level. So on the untyped IR, we could do composition. On the typed IR, composition becomes very hard. But you could write a compiler plugin standard lib on top of this that has pass orderings that you can register passes with, and that way you could do composition.
All right. OK, maybe a quick one. Claire. Yeah.
Hey, Valentin. Would it be useful if untyped IR was in SSA form?
This is almost in SSA form. I call this SSA form with memory. I think that is sufficient. I don't think we do need linearized IR. We don't want to do expression trees. But I don't think we need full SSA form.
All right. I'm afraid I could take your question. Will be plenty of time to ask Valentin. Let's thank the speaker again. And before we move on, I think, Ray, you want to make an announcement or say something?
Yeah. Can you all hear me? There we go. Carson may be about to announce this, but I just want everyone to be aware that there are headphones available, which will transmit the speaker's audio. I do really apologize for the background noise here. This was not, I will be straightforward, this is not the agreed upon schedule. So we are working to amend this, and so please just bear with us, and I appreciate your patience.
All right, thanks. So headphones are available there if you need them. But now let's move on to the next talk, and let me introduce the speaker. So Michael Schlottke-Larkemper is here. Yeah, he is behind Trixie.jl, so you might have heard of that package, active in the Julia HPC community. And he will talk about secure numerical computations. And yeah, the stage is yours, Michael. Take it away. Oh, and before I forget, because we didn't have time to rehearse this, 5 minutes, 2 minutes.
All right. Thank
thanks.
you very much, Carsten. Welcome, everyone, to my talk on secure numerical computations using fully homomorphic encryption. I'm Michael Schlottke-Larkemper, and I'm a computational scientist. So if you are expecting a cryptography talk, then I have to disappoint you already. So this is not going to be a cryptography talk. I will look at all of these, or many of these things that we'll be talking in the next couple of minutes from a computational scientist point of view, from an application point of view, and I will try to put in a little cryptography, but I will keep it to a minimum. Before I get started, let me first acknowledge my student Arseny Kolot, who I've been working with over the past couple of months on this project. It's a side project at the moment, but he did really a great job, and a lot of the results we're seeing today were obtained by him. Also, there's a reproducibility repository that also includes the slides for this talk and all the code that was used to generate the results. So if you want to check this out later, you can do so. And the slides are also on there as well. All right. So Data security, maybe some motivation. Data security and privacy is all the rage nowadays. Everyone has probably had some contact with it. Security and privacy are two related but slightly different things. So with security in general is meant that you prevent unauthorized access, so on a technical level maybe, whereas privacy is the concept of you don't want to share more of your data, more of your knowledge than you should have to. And examples where this is particularly important could be, for example, health data, financial information, or proprietary algorithms. And in general, this concept of data security and data privacy is a major challenge for cloud computing. On the one hand, you have the desire to keep your data private, of course. On the other hand, maybe the data needs to be processed in the cloud. So there's a challenge. On the other hand, you maybe have some algorithms that you want to use and apply to users' data, but these are part of your company's intellectual property, and you don't want to share them with anyone. So you also need to keep your algorithms private. And the concept that sort of tries to resolve this is called zero trust computing. So basically, you don't have to trust someone with your data, and the algorithms provider don't have to trust you with their algorithms. And fully homomorphic encryption is basically an idea or a concept that tries to get there. So I talked a little bit about privacy, about security. So here's a very naive idea, and of course you know where this is going. So what if we want to do computing in the cloud, but instead of sharing our true data, we're only going to share our encrypted data with the cloud? So here's a very simple example. I have the numbers 2 and 4, and I want to compute the sum of them. And I want to do this in the cloud, and I want to do this in a way that the cloud provider does not have any knowledge about the numbers I'm trying to add up. So a very naive approach would be I add basically a random secret only known to me to each number. So instead of 2, I'll get a 7, and instead of 4, I get a 12. And I send these numbers 7 and 12 to the cloud. I let the cloud provider do the addition. I get the 19 back, and then finally I can retrieve or get the real result by sort of reversing this encryption, this very naive idea of encryption. So while this is technically secure, right, the cloud provider will never see the actual data, there are, of course, some problems with this approach. First of all, it requires local knowledge about the exact algorithm that's going to be performed. So if I use this approach, I have to know what the algorithm is doing to basically reverse it on my machine. So this already violates the first principle of this zero trust computing. The second problem, of course, and this is a much more glaring problem, I think, is it does not save computations, right? I mean, this was a very simple example, but we can already see that I wanted to add 2 numbers, but now instead of adding 2 numbers, I have to add a random secret and then send it to the cloud, and then I retrieve it, and I have to do reverse the addition again. And it gets even worse if we go to something as simple as a multiplication. Now I actually have to do many more computations, so obviously this approach does not scale. And this is now where the concept of homomorphic encryption comes in. So the key idea is to be able to perform computations on encrypted data and getting results identical that are identical to what I would get if I would do the plain text computation. And the data and the algorithm is mutually unknown. So we get this zero trust computing concept. And ideally, and this is why sometimes you see fully homomorphic encryption, the fully refers to the fact that I have an arbitrary algorithmic depth of my algorithm. So here's a small visualization just to make sure that the concept is clear. So as a privacy-conscious person, I have all my data encrypted, and the usual way, if I want to process it, would be now I have to decrypt it. I hope one can see the mouse, yes. Then I have my data in an unencrypted state. I can process it. Then I have some function of data, so my result. And then because I want to keep it secure again, I encrypt it again, and then I have my encrypted result. And the idea of homomorphic encryption is that I can basically avoid this detour over the encryption and decryption and encryption process and just have my encrypted data directly be processed and get to the same result in the end. Now, of course, if it were simple and easy, then everyone would be doing it by now, but many of you probably have heard about this for the first time in this talk. So there are some drawbacks, and some of them are very severe, and I will be talking about them today as well. First drawback, I would say, there are limited basic operations, I will talk about which one, that are available to construct algorithms using homomorphic encryption. So that means you have to rewrite probably most of your programs. The second one, drawback is the considerably increased resource requirements. As a computational scientist dabbling in the HPC world, this is of course a big concern for me. And the third drawback is the possibly reduced accuracy for your computations. All right, before we go into more details, here are some very high-level fundamental concepts of fully homomorphic encryption. Again, be aware that I'm not a cryptographer, so please don't use this and hide your new startup's great ideas and then come complaining that someone stole it. So fully homomorphic encryption usually is based on asymmetric, so public key encryption. Similar from what we see when we use PGP, for example. There are different schemes. They're all basically named by the initials of their authors. So there are some schemes for integers, there are schemes for real numbers, and this is the CKKS scheme, so by Chon, Kim, and Song. Is actually the scheme that I will be discussing today. Mathematically, it's based either on lattices or on the ring learning with error problems. If you want to know more about this, please don't ask me too much about it, because I'm not an expert on ring learning with errors. But it is said to be both of these, the lattice-based and the ring learning with errors problems, are supposed to be quantum hard. So some proponents of fully homomorphic encryption also propose it as an idea for post-quantum security. The key principle is in all of these schemes is that you basically hide your data behind noise. So you have your raw data, you add some random noise to it that basically hides the true data. Then you do these computations in such a way that the noise does not grow out of bounds. And finally, when you have the result, you can decrypt it by basically removing the noise again. And of course, the challenge is that this noise that you add will grow with the algorithmic depth. So the more operations you do with your encrypted data, the noise will start to get bigger and bigger. And this is what is called, that requires what is called bootstrapping. That's a process that basically made homomorphic encryption really interesting in the first place, maybe about 10, 12 years ago, is to basically remove some noise during the computation so that in theory you can have arbitrarily long algorithmic depth. If you want to know more about the CKKS scheme, I really recommend this Open Mind blog. It has a 5-part series on how to use and how to implement actually the CKKS scheme, and it's a good read for non-cryptographers. Just be aware that it needs some considerable math, so it's not for the faint of heart either. All right. So what are the basic building blocks for homomorphically encrypted algorithms? Well, everything is a vector, and you can add them, you can multiply them element-wise, and you can rotate them. So I think add and multiply is pretty self-explanatory. Rotate means basically, in Julia, it would be the circ shift function, so you can just rotate it in the order, and that's it. You also get multiplication or operations with plain text values, so you can also have a ciphertext added to a plain text value, also to a plain text scalar, and you have the bootstrapping operations. So these are all the tools in your toolbox that you have to build your algorithms, and that of course is a pretty severe limitation. For example, what you can already see, what's missing is something as simple as a division. So this is already a hard problem. If you want to do something like a sine function or some other nonlinear function, usually you have to somehow model it with a polynomial or something like that. There are a couple of efforts to bring homomorphic encryption to Julia. Ramparts is the first one that I found, but basically, when I started to become interested in homomorphic encryption, it was already not active anymore, or didn't seem to be active anymore. There's the Paillet package by Brian Thorne from 2020, and the toy FHE project from Keno Fischer, which I think was really just a toy problem also. In 2021, I tried for the first time to work with this in Julia by wrapping the Seal library, but really the effort I want to talk about today is with OpenFHE and secure arithmetic that I started basically around half a year ago together with my student Arseni. So what is the idea behind these packages? OpenFHE is an open source homomorphic encryption library written in C++. It's basically a successor of a number of pre-existing libraries that somehow made the, in my opinion, very good decision to join forces and try to develop one powerful library instead of 5 less powerful libraries. OpenFHE-JL is then obviously a Julia wrapper for this library. We have like an intermediate stage, this OpenFHE Julia, which basically provides the C++ bindings using the CXS wrap package. And then we have secure arithmetic, which is sort of a convenience package, add some syntactic sugar for rapid prototyping. So the OpenFHE library is written by cryptographers, and while it is considered to be production ready, it still requires a lot of knowledge on how to use it correctly. And secure arithmetic, the idea behind it was to take some of these this ugliness, let's say, of having to write a code out of it and make it nice. And if you want to add 2 vectors, you just want to write plus. You don't want to write, I don't know, add eval something something something, right? All right. So before we get to the results. In practice, if you want to do a secure numerical computation, you need to set up a secure context. Originally, when I planned this talk, I thought I would be showing a lot more details on how to use this actually in Julia. But then I figured that if I want to show this in a meaningful way, I have to explain so much of the cryptography behind it that I basically will just skip most of this now. If you want to learn more about it, I really recommend to have a look at the secure arithmetic package, where you can see a very simple example of how to use or how this code would look like in practice. Here, just a few words. If you want to do a secure simulation, or a secure computation, you need to set up a lot of parameters up front about problem size, encryption scheme. You need to decide up front what kind of multiplicative depth you want to support. And in the end, you need to make sure that you choose your parameters wisely, because they strongly affect both the accuracy of your results and the performance of your computations. In this case, I put some of the most important parameters here in the table on the right. I think the key takeaway here is that we use a security level of 128 bits. So technically, one could consider all these computations we did as cryptographically secure. Again, with the caveat that I'm personally not a cryptographer and that I just trust the library authors, in this case OpenFHE, that they actually really know what they're doing. All right, so let's have a look at accuracy and performance of some fundamental operations. Maybe before we go here, maybe one more thing. So the ring dimension here, 2 to the power of 17, means that our vectors are essentially of size 2 to the 16. So we always have 64,000 real values in each vector that we're doing the operations with. Now, later we're going to look at some results where we only have, let's say, 100 or maybe even less values that we actually work with. And you're wondering correctly, why would he use a 64,000 element vector if he only needs 40? Well, the problem is if you want to have the security, the accuracy, and the multiplicative depth, you have basically no choice. It ends up that the ring dimension must be 2 to the 17. So that's one of the hard facts of using homomorphic encryption. All right. So let's have a look at some fundamental operations and see how they affect accuracy and performance. So the first one is basically a simple, I have a vector of values, I encrypt it, then I decrypt it, and then I look at the results. On the left-hand side, you see the number of encryptions and decryptions we perform and how it affects the L infinity error. So basically, we're looking at the maximum deviation of the true data, and we see we're here well within, let's say, double precision. So that seems to be okay. But we can already see here on the right-hand side in terms of time it takes, and also that we're here already talking about seconds or sub-second time. So this is not a very fast thing we're talking about. And it only gets worse from here. So yeah, just take this with you. What is also can be seen here is that the actual performance depends on the multiplicative depth. So having algorithms that have a longer multiplicative depth means also that typically all the single operations you're doing take more time. You can reset the multiplicative depth with this process that I described before, bootstrapping. But as we see, bootstrapping also does not come for free. All right, so encryption, decryption, okay, that's fine. Now let's have a look at addition. When we add, the blue line here is if we add 2 ciphertexts, we see that we also have an error, let's say, still on the order of double precision. And we also see that the time is, yeah, 10 to the minus 2 seconds is a little bit better than encryption, decryption, but it also grows strongly with the multiplicative depth. Now we look at multiplication, and multiplication is actually the thing that is the most problematic for homomorphic encryption schemes, because those are the ones that really make the error grow, and these are the ones that restrict the algorithmic depth. So sometimes it's called also just multiplicative depth, because this is what is restricted in fully homomorphic setups. And as you can see now, when we go to a number of multiplications larger than 14, we can see that the multiplicative error starts to skyrocket. So here we are, I would say, leaving the double precision realm already. So just by doing multiplications, we introduce a lot of, or we introduce maybe, depending on our application, a non-negligible error. And we can also see, you know, if you do this with a multiplicative depth of 27, something like this, a single multiplication will take 1 second of compute time. So this is, again, not a cheap algorithm anymore. Now, I also introduced the rotate function as a third basic operation. Here, everything seems to be okay. The error is on the order of a double precision accuracy, and well, yeah, time. It's also not for free, so it apparently is not just rearranging some data, but it actually needs to recompute a lot of things behind the scenes. Now, finally, the elephant in the room, the bootstrapping algorithm. So as I said before, we need bootstrapping if we want to have a fully homomorphic scheme, so being able to have algorithms of arbitrary depth. So there's no way around it. But if you can look at the left graph, you can already see this is a whole different beast in terms of accuracy. So a single bootstrapping operation introduces an error of 10 to the minus 6. So we immediately lose basically half of our accuracy if we use bootstrapping with these set of parameters, with this specific library, but this is what is basically state of the art at the moment. And if you look at the time for a single bootstrapping, you will also not be much happier, I suppose, because a single bootstrapping with this setup now can easily take 30 to 60 seconds. So this means, coming from a person who's mostly involved in high-performance computing, using fully homomorphic encryption is not for the faint of heart. Here's also a table that basically summarizes the difference in errors and times and puts it relative to the addition, but I'll just skip over this. And now immediately proceed to the example that I actually want to show. So my background is in computational science, mostly computational fluid dynamics, or primarily computational fluid dynamics. And the problem that we wanted to look at is a simulation, a numerical simulation. And we, of course, picked the simplest example we could find. So we do a linear advection problem. These are the differential equations here that we're using. So once in 1D and once in 2D. If you don't know anything about linear scalar advection, it's not such a big issue. Just you see there are some values there, and we somehow want to solve this. We want to solve these equations in a numerical way. So we actually use two different schemes for this, and this is now basically where everyone who doesn't know about partial differential equations or numerical methods can now basically join in again. So this is basically an algorithm. In this case, it solves the advection problem, but it could be any other algorithm, and we just write it as we see it. So we have two numerical schemes, a first-order scheme and a second-order scheme. The second-order scheme is more accurate in general, but of course also more involved computationally. So you can already see that the equation 4 is much longer. And now we want to code this up using a homomorphic encryption scheme. And as I said before, what we now need to do is we need to take this mathematical formulation. This is equation 5, here in this case, for the Lax-Wendroff scheme, for the second-order scheme. And we now need to put it in a fully homomorphic encryption formulation. And in this case, it's actually not that hard. So the only change we really need to make is here where we have the UI. We can just take our regular vectors, and then we use the circ shift function if we want to use a vector that is shifted. And by this, we can basically combine this in a smart way to get back our original formulation as basically as a vector formulation using these homomorphic encryption primitives. And this is the only part of Julia code that survived my slide revisions, and I just wanted to show it that you can see. So really, that's basically what our effort with secure arithmetic was. It basically looks like the mathematical formulation, so it's now amenable, I would say, to experimentation and rapid prototyping. All right. Some results before I'm finished in a few minutes. This is now the result for the 1D problem. So we had a sinusoidal wave. We used both numerical schemes to let it run for basically one full period, such that it ends up basically where it started. It's a periodic problem. And as we can see, in this case, I think we used something like 40 points to discretize the whole simulation. So of this 64,000 value vector, we only used basically the first 40 values to do the actual computation, which is overkill, but also if we want to have 180-bit of security, the only way we can do it. As we expect, the exact solution and the second order scheme, they're nearly indistinguishable, so I don't know if it's visible from back there, but the orange and the green curves are more or less on top of each other, whereas the first order finite difference approximation is much more dissipative and obviously cannot capture the solution very well. What we can take away from this is that for a problem like this, our error of 10 to the minus 6 that was introduced by the bootstrapping algorithm apparently is not such a big issue. We also did the 2D simulations, but you cannot see much quantitatively here, but it's a similar story. The first order scheme is very dissipative. The second order scheme is in the eyeball norm indistinguishable from the exact solution. We also did a convergence analysis to make sure that we actually do have implemented proper schemes. If you're not a numerical analyst, you can skip over this slide, but what we can see here is that we get the expected first order of accuracy for the first order scheme and the second order of accuracy for the Lax-Wendroff scheme, both in 1D and in 2D. Now, some error analysis and some performance comparisons. So this is on the left is for the 1D problem, and the right is for the 2D problem. This compares now the cryptographically secure computation with the same computation using only plain text values. So the idea here was that one idea of secure arithmetic is that you can not just run your simulations using cryptographic algorithms, but we have actually different backends, and one backend is an unsecure, unencrypted backend. So you can basically prototype your algorithms, write them down, check the results, make sure everything works, and then you can just switch the backend to the encrypted one, and now you have to wait, of course. But you can basically do the prototyping without having to wait for all the machinery to run through. And what is interesting, I think, here to see is for the first n steps, we basically don't see any errors, because this is when the bootstrapping has not yet been called, right? So in the beginning, on this scale, 10 to the minus 6, our error is still in the order of 10 to the minus 12, so you don't see it in this graph. But once the first bootstrapping kicks in, the error jumps up, and then you can see it somehow goes down a little bit, and especially in the 2D scheme, it's I think, very interesting to see. The error seems to, let's say, recuperate a little bit over the iterations, but then you have a next bootstrapping, and then it jumps up again. So this seems to be how such a scheme behaves in practice. Now finally, for the performance analysis, we see something similar to what we expected before. Let's only have a look at the left slide here, at the left figure here. The green curve is for the second order scheme, the blue curve for the first order scheme. The first order scheme obviously is cheaper because we have less numerical operations. That's what we expect. And we can also see that the runtime significantly increases each time we have a bootstrapping. So these are the little jumps, basically. And interestingly, the runtime seems to be going down the longer we go down the chain in terms of multiplicative depth. So the first few operations after a bootstrapping are rather expensive, so the slope is rather steep. And then once we get to the end of the permissible algorithmic depth, it somehow levels out a little bit, and then of course we have to hit another bootstrapping, and the time jumps up again. All right, final slide to summarize. With fully homomorphic encryption, we are able to perform more or less arbitrary algorithms over encrypted data. There are some severe practical limitations in terms of complexity, especially in terms of runtime, but also in terms of library support. You basically rely on libraries that someone else provides, and there's no way, at least for me, to fix anything or to add anything to that. In Julia, we have now the ability to do simple experimentation with fully homomorphic encryption using the secure arithmetic package. And from my point of view, I would say secure numerical simulation is feasible, also for someone who is not a cryptographer. Whether it's practical, whether it's useful, well, that remains to be seen, but that's what I call research at the moment. And yeah, with this, I would like to stop here. Thank you, everyone, for your attention. And yeah, if there are questions, I'd be happy to try to answer them. Thanks.
Thank you, Michael. Yeah, let's take the time for 1 or 2 questions. So one up here by a different Michael.
Yeah, exactly. Yeah, thank you, Michael. I think it's a great talk. Very nice exploratory work, I would call it. So I have plenty of questions. I'm just going to ask one for now. For your benchmark, how did you actually choose the values? Like in the sense of, did you avoid causing issues of errors from the numerical floating point computations themselves? Like, is the error we see there only the error of the holomorphic encryption?
What do you mean with the benchmark? You mean the problem that we computed, or the setup of the encryption scheme?
The basic setup when you're just checking the individual operations, addition, multiplication, and so on.
So basically, the values that we use here in this table on the right-hand side, these were optimized for accuracy and sanity. As I said before, the ring dimension basically was fixed once we set which security level we want to have. And this the scaling modulus, 59 bits, basically dictates the general accuracy of your scheme. So if you have a higher scaling modulus, you can get higher accuracy, but then you also need a higher ring dimension. But then the highest ring dimension that the library currently supports with 128-bit security is 2 to the power of 17. So it's it's sort of the sweet spot of being able to do this in a secure manner with, let's say, non-negligible multiplicative depth. There are probably a few values you can fiddle around with here, but for what we try to do, there was no other way to configure this. And maybe just as a second, so this obviously is not a standard application for fully homomorphic encryption. So probably many would have expected here to see something about secure machine learning, which is probably the primary driver for this kind of technique, because there you only have multiplications and additions and maybe some activation functions if you have a neural network that you want to compute. We didn't try this yet, but there I think you can get some better results.
All right, since lunch is waiting for all of us and we're a little bit over time, do you have a quick question? Oh, come on, let's take it. Lunch can wait for 2 more minutes.
Thanks for the talk. I'm just curious about, in terms of the efficiency comparing between decryption, encryption versus evaluating the circuit, how do they compare? In terms of the order of magnitude?
So the encryption decryption is more or less for free in comparison to evaluating the algorithm or the circuit on encrypted data. If you look at the actual runtime that you would require to do this on your machine in an unencrypted way, then nothing beats that. Okay, so I mean, if we look at the plain text execution times here, okay, so this takes like 150 steps. This takes like 0.03 seconds. I can't even encrypt my data in this time. Okay, so this is obviously not relevant. Let's say if you're just interested in the results. So this is basically the first proof of concept that you can do things like that, and whether it makes sense, that's to be found out.
Sorry, I was just asking about the execution time for ciphertext and versus the encryption, decryption, and
I'm not sure. So maybe we can just discuss this afterwards. I'm not sure.
All right, then let's stop here. Let's thank Michael and all the speakers of the session again. And now lunch is waiting for all of us, and the tracks will we will reconvene in the rooms for the tracks to start at 2 p.m. if I'm not mistaken. Is that right? Yes, I think sounds about right. See you guys.
Test, test, test.
Perfect. Use that. Cool. And
mirror. Nice. Ah, I can hear my voice now.
Hello, everyone. Coming back in from lunch. We're going to get started now. First up, we have Jorge Vieira, who works at ASML. I will let him introduce his talk. Take it away.
Okay. Am I breathing now? Yes. Thank you. Where should I stand for a camera, by the way? I don't know. Somewhere. Thanks for joining. I hope that's not too noisy today, but I hope I'm even noisier. And I'm just going to talk to you about cryptography packages in Julia and what's missing. So let me just start, like, who am I? So as I said, my name is Jorge Vieira. I'm a chemical engineer, as in not a cryptography expert. So I'm not that person. And that's the extent of my knowledge. I know from reading that book, the Simon code book, that's where I learned about RSA and symmetric encryption and quantum encryption stuff. It's an old book by now. It's from 2002. So kind of old by most people's standards. And also watch a computer file, a lot of cryptography stuff over there. That's the extent of my knowledge. I'm not I have to emphasize that. I'm not a cryptography expert. I might be a user, but not an expert, okay? And that's precisely the point, because right now, I was quoted once in YouTube, and I posted a comment or something. And then some like, oh yeah, because this rando is trying to say something. Yes, and I like the term. So apparently I'm just a rando from the internet, just saying things. And that's the way you should think about this talk. It's just one rando person telling you, okay, I want to use these random packages, but I can't. Or there's something I cannot use. So why not? So that's precisely the point. And let me just get started. So what is this talk about? So there was a very nice talk over here earlier today about homomorphic encryption. Super cool stuff. You can encrypt data and do calculations with that. This talk is not about that. Cryptography is usually about number theory and Galois fields and, I don't know, modular arithmetic and elliptic curves and stuff. Some weird math with integers. Also not about that, because I don't know anything about that. Again, I'm not a cryptography expert. But what this talk is about is about the things we use day to day. So all the cryptography packages that we use for communications to protect some of our data, some of the backbone of the things that we use are kind of made out of conventions. It's kind of messy because it's full of acronyms all over the place, full of code names, standards. It's way boring, but it needs to be done. Otherwise, it cannot be done. So let me now mention that this is not a rant about, oh, my favorite package in Python is not available in Julia because whatever, or my favorite package in Rust is not available. It's not that either. It's just this is kind of like a template of things that we need to do. This cannot be done by one person. So if someone is interested in these kind of things, this is kind of like a to-do list of things that could be cool. I mean, I know that I'm not selling it very well by saying it's boring. I always say that this is boring, but some people find it quite interesting. I just happen to think that this is okay, but maybe people don't like it very much. So if you find this interesting, oh, this is a to-do list for you. Okay, why this talk? As I always, I don't know if I have emphasized this enough, cryptography in every ecosystem is always a freaking headache. Just keep me family friendly, so freaking. So for instance, in Python, it's kind of documented and people can find their stuff. There's a very nice package out there called PyCryptodome. I like it very much. That's where I learned also a lot of stuff, not only computer file, so I like it a little bit. Let me take this off, because this is... And I screwed the microphone. There you go. Sorry about that. So in Python, we complain about Python stuff, but they made a very nice effort putting all the packages together. There's one package that I like very much, which is called PyCryptodome. which is already the second package, which is Python Crypto. And they talk about all the things, well, they describe all the things that basically a regular rando like myself like to use when we talk about cryptography. I will talk about that in a little bit. Still very messy, because there are things that are not there yet or implemented halfway there, but still you can use it and learn very easily. Rust is not exempt of that either. So there are a lot of packages in Rust. Some of them say, okay, these are super secure because it were implemented in Rust in a super fancy way. And we are very sure that's very secure and whatnot and very fast. Sure, but it's also very messy. So I have to emphasize, it's very messy. Now, one last thing. So there are a lot of things already done out there. So this is a list that I took from Wikipedia. I also learned things from Wikipedia. And this is just well, I had to cut the list of all the available cryptography packages available. Some of them implement parts of a functionality that people need, for instance, asymmetric encryption or elliptic curves, and some elliptic curves, but not the others. And it's messy. So there's a lot of things out there. So we don't have to reinvent the wheel, but needs to be wrapped somehow. And just pick the one of your choice. I will recommend Button or OpenSSL, but there are a lot of those in case you want. Still very messy. And now, what's available in Julia? OK, let's start with the good things. So random number generators. Why do we need random number generators for encryption or for protecting stuff? Well, first of all, if you want to protect something, you want to make it devoid of any patterns. So that's why you need a random number generator. And as of Julia, I think it was 1.7. Now we have a cryptographically grade, secure device that can generate random numbers that you can use. Some people are saying no. OK, good. At least it's there. I don't know if they claim it's cryptographically secure. OK, again, I'm not an expert, but that's what they claim. Documentation has an entry. That's the extent of my knowledge about it. You can use it like that, using the random package. You use the random device. That's the one that's cryptographically secure. And you can generate bytes in that way. So that's a way to use it. I don't know if it's cryptographically secure, but at least you can use it. And the documentation says that's cryptographically secure since 1.7. Is that true? 1.7? No? OK. Next. Cryptographic hashes. So that's to ensure data integrity. So we want to make sure that our data, it's exactly what we think it is. Nobody tampered with it. And that's what they call this thing called hashes. The most used right now is the very unimaginative name called secure hashing algorithm, or SHA. There are several. It's a I forgot the word. It's an acronym. No, but it's a convention. It's not a convention. It's just I forgot the word. Sorry? A standard. Thank you. It's a standard. Thanks. It's a standard that was chosen, and then now we're in the third version of it, and that's what we use. It's documented in Julia. Has an entry. I don't know the extent of that. I don't think it's enough, but OK. It's documented. Has an entry. And that's how we use. OK, good. What's next? Symmetric encryption. OK, that we're getting into something over here. So what is this symmetric encryption? So, well, we want to convert our documents, and we have to make it in such a way that nobody can read them. The easiest and usually fastest way of doing that is just use a fast encryption method, which is called symmetric. So basically, you encrypt in one way using a password or a key. And you can reverse that transformation using the exact same key. That's why it's symmetric. You go both ways using the same key. So that's what I learned in computer file. So OK, good. One of the most used algorithms right now is, I think, is considered the most secure at the moment. It's AES-2556 or something like that, which stands for Advanced Encryption Standard. Trivia thing. It was not the original name. The original name was Reidnael. I don't know if I pronounce it very bad. Very bad. Okay. It's a Belgian algorithm. And so it was made here in Leuven or something. So how do you pronounce it? Reindal. Kind of. OK. So that's nice. OK, that's implemented in Nettle, which is good. But the thing is that these kind of algorithms work with blocks, and you need to be able to make them secure. You need to make these blocks kind of consistent with each other and encrypted in such a way that cannot be reversed. So there are several modes of operation. I'm not going to go through them. The most advanced one and the one that people like to use is this one called GCM, or Galois counter mode. Don't ask me how it works. Check computer file. But that's not in Nettle. So that's kind of a bummer. It kind of works for keys, but not for messages. So which is, again, a bummer. Technically, it's documented. There's a README entry. That's about it. You can use it like that with Nettle. I use it in some things at my company, but that's about it. So at least it works, and it's fast. So it's, but it's a C library. It's being wrapped. OK, next thing, asymmetric encryption. What's out there? Yeah, well, first, what is it? Usually, as I mentioned, with encryption, with symmetric algorithms, you can encrypt your data. We can protect your data using one key. But the key itself then becomes a problem. How do we transfer this key? How do we protect it? And one way to protect that is using this asymmetric encryption. You generate something that's called a key pair. One is public, one is only for myself, so private. So I can give the public key to anyone that I trust and say, OK, this is my public key. Please, if you want to send me a message, here's my public key. You can encrypt things to me. But the thing you usually encrypt is just the key, and then the message is encrypted with that key, and that's how you transfer stuff. That's the TLDR. It is available in Julia. No-ish. So in general, no, you cannot access it directly. You can kind of access it via some other packages, the layer, secure layer packages. I'm going to talk about those in a few slides. So usually those are the method, the algorithms are used right now, RSA, Reverse Shamir Adelman. So this is the most used right now. It's considered to not be enough anymore unless you use a very large key. The thing that's getting in, like it's a fad now, but I think the thing we should use is this ECC, elliptic curve cryptography. It's not exactly the asymmetric encryption. You need to do some extra things, but it could work like that. And then in order to use those, you need to implement these two methods of exchanging keys using these asymmetric elliptic curves, which one is the ECDEH, the elliptic curve Diffie-Hellman algorithm, not available, or ECIES, the elliptic curve integrated encryption scheme. So in order to actually encrypt something you can send, you need that implementation. And I haven't seen that in Julia. So if somebody can tell me, like, Jorge, you're uninformed, please let me know, because that's my knowledge so far. So more things. I said about sending the message, right? Sending this encryption key, or the public key. Well, how do you send that? How do you encode this information? Different computers have different encodings. ARM is different from Intel. Some are big endian, some are little endian. So that gets complicated. So of course, there's a standard. And that standard is, well, several standards, actually. The most widely used is ASN.1, the abstract syntax notation to send binary information, usually certificates, public keys, whatever. It's used over there. That's not, I haven't found anything like that in Julia, except by the use of maybe embed TLS. So that's kind of a bummer. Also, PEM file formats. So there's a privacy mail format, and there's some other sort of formats that I forgot the acronyms of those that get very complicated, like best encryption record and I forgot what the other ones. It's like gets designated encryption record or something like that. Some different formats to send binary information. Again, encoding in such a way that it can be used in several kind of computers. I haven't found anything like that in Julia, and could be used for importing these public keys, for example, or certificates. As I mentioned, OpenSSL or Embed has some support, but doesn't have any clear Julia bindings. You can use them, but it's not very clear how to use them. Also, the documentation is not very good. Well, now we talk about this programs. So sometimes you want to connect to your browser. You want to communications from two computers. So you want to encrypt that communication channel so that you have these standards as well. The secure socket layer, SSL, or the transport layer security. I think the second one is a successor of the first one, but we still use the first one because reasons. Technology never really is retired. We just gets older, but keep using it like Fortran, MATLAB. Anyway, so these things are available in Julia. We wrap a few of the libraries. There's OpenSSL and embed-TLS. I have a personal embed-TLS with OpenSSL because I could not really use it directly. I had to use the command line arguments in order to do anything of useful. So I think that the Julia bindings could make use of some TLC, in my opinion. I think they work fine if you use it as intended as a communication layer. But if you use it for anything else, they are not that good. Again, the documentation just points to the OpenSSL library documentation, and that's on the README, and that's about it. So what's needed on this one? Well, more documentation and more extensive wrapping of the functions. I think this is a low-hanging fruit. So if someone gets interested, I think this is very easy-ish. If you want to learn how to bind some encryption libraries, so C libraries. Okay, we're getting. You're almost there. I'm almost finished. I'm almost end up with my rant-ish. It's not a rant. So we talk about handling keys, sending it over the internet, how to encode them. But if I have them lying around on my computer, someone might be able to copy it, and then that is compromised. So how do we secure these keys? So there are several ways to secure those. So there are some computer chips that are built into your laptop. One is called the Trusted Platform Module. It was the TPM. So that's what was kind of a big deal a few years ago because then Windows 11 said, okay, you need that as a requirement. You need a TPM, and people were shouting like, yeah, what if I don't have a TPM? Well, most computers nowadays have a TPM. So that's that thing. It's not a guarantee of success. So some time ago there was a guy that hacked I think it was some Lenovo laptops using a Raspberry Pi Zero, and just hacked into the wires. But okay, it gets more difficult if it's stored in a chip than if you just copy your hard drive, right? So it's not infallible, but it hardens your security. So that's the TPM. There are similar devices that are external usually. One is called the Hardware Security Module, AHSM. Those are usually attached. Sometimes are attached to Kubernetes clusters, and that's where they store actually the keys. So another one is the YubiKey. There's an example over there. So YubiKey are like these USB drives that you can just plug into your computer. And yeah, you can also store things there. And the point is that those devices usually encrypt things, and they encrypt stuff by themselves. So sometimes you don't even need the external libraries. Sometimes they just already bind the OpenSSL libraries, like the YubiKey. But it needs to be there. So this one is, as of now, right now, not publicly available in Julia. But this is where I can contribute my small, I can make my small contribution. So I implemented one version of this library for this standard, the public key cryptographic standard number 11. So there are too many of those. So it's sometimes called CryptoKey. That one I implemented. I'm using it right now at an employer. But we're thinking of open sourcing that one. So be tuned on that one. Maybe we have to cut through the red tape to get there. But that's the one I can say, OK, I'm also put my money where my mouth is. So I'm also going to contribute over there a little bit to the community with that. Well, not me, my company. So then I also say that there's another standard which is kind of parallel. This is more used to store these keys remotely. And one is called KMIP, the Key Management Interoperability Protocol. It's similar. It's just a PKCS11. It just works with local hardware. The KMIP works with remote hardware. That's basically the difference. Again, don't crucify me if I'm saying things that are not completely wrong, completely right. I'm not a cryptography expert. So I'm almost there. So don't fall asleep. So I know you have the after lunch dip. So but bear with me. So there are a few other stuff that I didn't know where to put. So sometimes people tell me, yes, you have these Jupyter notebooks with Julia that work over CMQ, and it's very nice. You have that. You support Curve MQ, right? Curve CMQ, right? And the answer to that is So what is this Curve MQ? Curve CMQ. Well, maybe the name tells you a little bit. It's elliptic curve encryption implemented over CMQ. So you can just have a protocol between your Jupyter notebook that is encrypted, but not in Julia, because that's not implemented. So we lack that. So that will be something that also we can do. I think that's also low-hanging fruit. And one more thing, maybe that helped a little bit with the binary standards. So sometimes you want to send information over the internet in some nice wrapping. One thing that's called the JSON Web Tokens. Finally, something that's not super complicated, unless you want me to explain what JSON is. That actually found that's implemented in Julia, and I actually found 2 packages in Julia. That was actually surprised. So I found that like a month ago. I was very, very surprised. Unfortunately, I didn't have time to test them, so I don't know if they're any good. I hope they are, but at least there are 2, and they seem kind of documented. They have README and examples. I don't know if that's enough, but at least they have that. Okay. Long list of a lot of acronyms and weird stuff that I'm just talking about. Like, okay, this is just the summary of that. Maybe my talk would have been summarized with this table. So these are the things that are needed, in my opinion. You can see which ones are available in Julia. Usually just 5 out of, I don't know, I didn't count them, 12. Some of them are okay, but they're not very well documented. And that's the status update as of today. So what can we do about this? Well, if in doubt, just wrap the existing library. There are plenty of those. And it's not that difficult. Just ask Christopher how to use libclang. You just get a header, automatically generates all the wrappers and stuff, and then you can just fill in the blanks. It's not that difficult, but it takes some time to work on it. It's a very nice thing if you want to learn how to bind some C libraries, so it's a good learning experience. Most of what is needed is available, just not available in Julia, but it doesn't need to be in Julia. Actually, we don't even need it in Julia. We can just wrap the external libraries and get done with it, or even the Rust libraries. And also, if you do that, don't forget documentation, because otherwise people cannot use it. I usually don't say this, because people that know me think that I'm a Julia fanatic, and they want everything implemented in Julia. But these things, I will say that's the exception. We don't need to implement these in Julia. They don't need to be implemented in Julia. They just need to be wrapped in Julia. That's it, unless you're really, really into it. This being said, of course, a security audit might be in place. Someone needs to qualify that there's no weird things going on, that no memory leaks, there's no things that you're doing such that they can copy all the information out there. Again, not a security expert. You should actually ask an expert if this implementation is correct, but first need to be there, and then we can audit it. So in summary, this is a very small sample of cryptographic functionalities in Julia. I didn't cover not even half of the things that are out there. I just covered the things that I think that are needed, at least commercially available. I'm also not talking about fancy homomorphic encryption. I will be happy to be able to use those, not military grade, just commercial stuff. That's it, no more than that. And right now we don't have those things, but I hope this is a template for people that might want to be able to interested in joining the effort. I will be doing a little bit, but again, this is not it's a thing that one person can do, so it needs a team effort. Again, I'm not selling this very well. It's boring, but easy to grab, and it's very satisfying when you have something that works. So I hope we get some more people working on this soon. And that's it.
Round of applause. Do we have any questions from the audience?
Oh, questions. Okay, good. Working?
On? Yeah. Is it on? Okay.
Yes.
So you talk about asymmetric encryption, but there is more a story of asymmetric cryptography actually. There are asymmetric cryptographic groups, and there are cryptographic signatures and kind of things. I think it should be separated. And
Yes. I absolutely agree. This is a small sample. I agree with you. I'm not even talking about, but the things that are needed, that people just need to use for day to day, are just what I just described over here. I'm not talking even about the fancy stuff.
yeah, but signatures are kind of separate.
Yes, yes, indeed. I omitted signatures.
Yeah.
Yes, I omitted signing. That's also
I
that's also needed.
actually have a package, crypto signatures, which implement FIPS 1.4 standard, which is compatible with elliptic curves and modular prime groups, and so.
Okay, maybe you should add that to the list as
Yeah.
signing. Yes. Okay, good. I will add your package to the list. Yes, thank you.
So what was, most of these cryptography libraries end up being like very node dependency C library implementations sometimes. Did you try and wrap any of them with, what's it called, the binary builders.jl? And going through the process of creating a JLL for them? Like, was there any recurring pain points?
So I thank you for the question. Yes, indeed. So I only tried to wrap the one that I needed at the time, which is CryptoKey. The other ones I didn't try. I thought, in my mind, oh, OpenSSL is over there. I will try OpenSSL. And it happened like, I don't know how this thing works. I need to use it right now, and I use it command line. Should be as easy as CryptoKey, I think. Maybe easier, because CryptoKey is kind of weird. It's not really one library. It's one library that's wrapping a set of libraries. OpenSSL should be easier. I haven't tried myself. It should not be that difficult. And with libclang, you have you can generate the code for you even.
Another thing that I think is missing in Julia is an equivalent of what Python has with SageMath. SageMath is a computer algebra system that implements all the groups, rings, fields, and elliptic curves and so on, and lots of number theoretical algorithms on top of them, determining, for example, the group order of many of these things. And basically, it's a nice framework for combining all the computer algebra world has done efficiently implemented algorithms. It's very widely used by people who want to break cryptography, because if you're looking at a binary and you're trying to reverse engineer someone else's cryptographic implementation, and you find some constants in there and they are Galois fields, they are points on curves, then you need implementation of the underlying algebraic structures. And that's, I think, what should be first addressed in Julia, that you have a cryptographic toolkit like this of the data types, because Julia at the moment is all about ints and floats, but that's not what cryptography uses. They use modular arithmetic, they use Galois fields, they use elliptic curves, and a whole range of other things. And that would be nice to have an equivalent of SageMath.
Thank you for the question. I absolutely love it, but that's exactly the thing that I'm not covering. So I agree that we should have those. That's actually the fun part, actually, you know. So you are into number theory, you want to study these kind of things, yeah, you should have those kind of libraries. You want to also go into cryptanalysis, well, also that. This is not about that. This is just about the commercially available stuff that is not there. We don't even have the commercially available, not even the state-of-the-art or bleeding edge things. So yes, I agree. We should also have those as well. Maybe you should put it on the list, but maybe it's a separate table. It's like for the bleeding edge kind of things.
Thank you so much. That's it for questions. Let's have another round of applause for Jorge Vieira. Thank you.
Oh.
Just a quick notice to everyone, if the construction noise is too loud or you're having trouble hearing, we have headphones that are beaming the audio for these presentations up on both sides. So feel free to go grab some.
Cool.
All right. Next up, we have Oscar Smith and Jameson Nash from Julia Hub talking about memory in Julia. Take it away.
Hi, everyone. I'm Oscar.
Hi, I'm Jameson.
We both work for Julia Computing. I do mostly ordinary differential equations stuff.
I do mostly compiler development.
And this was the result of me bugging him for about 3 months to do some language development stuff with me on this until I nerd sniped him sufficiently.
Yeah.
So this talk is about the new memory type in 1.11 and the new array implementation that comes on top of that. So the first natural question is, what's wrong with array? And there's a couple issues that are kind of fundamental to the current design. So array is resizable, which means every time the compiler, or every time your code looks up the size, the compiler has to make a new check to see if the size changed because someone might have changed the size. And also, the fact that there is a size and it can change means the compiler, or the array has to store the size in memory. And if you push or something, you have to store extra space so that you don't get quadratic performance when you push repeatedly. And so all of that means that there's a little bit of extra memory overhead. It works out to about 2 words, which is 16 bytes on a normal 64-bit OS. Also, because array used to be a special internal, not normal type, all of the array resizing functions that have to look at the internal data to the array had to be written in C. So push and push first, and pop first, and insert all together were about 300-400 lines of C code. And writing C code that works with Julia objects is not easy, especially if you want it to not segfault when you run garbage collection and stuff like that. And so this code was not particularly well optimized, and as a result was kind of slow. And then the last thing that was less of a problem, but more of a thing that we wanted to add that we didn't have a great way of adding, is that when you're doing some multi-threaded types of computations, it's very useful to have per element atomic operations. And this was a good place to add that. And if you want to, after this talk in more detail, see the design doc that we wrote for this and we're working off, it's linked here. It's about 3-ish pages. And so yeah, now here's what a memory is. Memory is a one-dimensional list of objects. So it is not, as a surprising number of people that we talked to about it originally thought just uint 8. So you have a memory T. So it's a memory int or a memory ordinary differential equation solution. If you want just bytes, that's a memory uint 8. This is because types are very useful for compilers to optimize things, and if you make the low level just be bytes, it makes the compiler very mad at you, and a lot of the optimizations you want to do become invalid. Memory is also a fixed size type, so unlike array, it is not resizable. If you want resizability, that's what array is for. But the size of the memory is not one of the type parameters. It is just dynamically stored. The reason for that is static arrays.jl is very useful for some situations, but it's not what you want to build most higher level abstractions on top of. And then the last thing, which is a little bit weird potentially, is that memory supports wrapping foreign memory. So if you have an array in C or an array-like object in Java or C#, you can turn that, you can wrap that in a Julia memory, which is necessary for some forms of interop. And so the layout is very simple. You have your first field, which is just your length. You have a data pointer. If it's a Julia memory, that data pointer will just point to the next byte after that, and then you'll have your elements in order. And if it's a foreign memory, then you will instead point to some arbitrary pointer that's separate. And then the one other thing that isn't shown here is for bits union. So if you have a memory union int comma nothing, for example, after all of the data, there will be a bunch of byte selectors that tell you which type each of your elements are, which is similar to how array works, but again, simpler because it's one-dimensional. And so now with this, we can build up a new array struct using this. And now array is just a mutable struct. It has a ref and a size. The size is the easy part. The size is just a tuple with the size along each dimension. And then the ref is another new type of object called a memory ref, where the memory ref has two fields. And conceptually, you can think of it as storing an offset into a memory. So this stores the first element, or the element of the memory that corresponds to the first element of the array. And this is because arrays in Julia are resizable from both ends. So both you need a length of the array, if it's a vector, that tells you how many things past the end are free space, but you also have the first one, which is the first element of the array, so that if you go before it, everything works out. And so memory ref specifically refers to a specific element of a memory. So it's very similar to a gep or get element pointer for those of you who have used LLVM. They're bounce checked on construction, which means that other than the case of a zero-length memory, once you have a memory ref, you always know that it is in bounds to access it. This is very nice for compiler optimization because if you have a bunch of different accesses to the same element, the compiler can construct the memory ref once and then just do a bunch of accesses to it. So it allows you to separate the code out cleanly without having to do that sort of analysis on the LVMIR later. And so now the most important part, obviously, is how much faster this is. For small arrays, we're about 28% faster to allocate. Funnily enough, this is actually the main reason why I cared about this PR in the first place. In primes.jl, there was an example where factoring an integer was bottlenecked by the speed of creating an empty array, and now it's faster. And similarly, if you don't need all of the fanciness of array, you can actually just use memory. And so comparing an array to a memory for a small size, it's almost twice as fast. And now that we've rewritten push and all of the resizing functions in Julia, those are all about 30%, 40% faster. And dict, so dictionaries in Julia, now can use memory rather than array because they do their resizing manually because they need to rehash things, and that means that you need to keep both copies around. And so now that dict uses memory, they're about 30% faster to allocate. And so here's that in graphical form. As you can see, these are all some pretty nice benefits. And on the bottom, it tells you exactly the code that was benchmarked. I believe this was all benchmarked on a Mac M2 Pro, something like that.
I think that's what I used.
But it doesn't really matter. It is relatively architecture independent, the speed-ups. And to implement all this, we have a handful of new intrinsic functions in Julia. So there's you make a new memory, and then you have memory ref new, which makes a memory ref. You have memory offset, which tells you what index of the memory ref is to. And then you have memory ref get and memory ref set that do essentially the get index and the set index, except that because of the memory ref, it's decoupled slightly. So the memory ref get and memory ref set both do not take an index because the index was constructed in the construction of the memory ref, which simplifies some things a little bit.
And finally, we realized we could take this opportunity as we made a more generic array and simplified all of that code to try to figure out what else could we do with this and how can we add some ability to leave ourselves space in the future to make it even more general. And as we looked into that, we ended up finding there was basically two independent axes that we were interested in supporting. One of them we call the memory kind. And right now, we only have two kinds, either not atomic or atomic. But the exciting part of this is we now have the ability to express to the compiler that we want a memory, but we want it to support all of the atomic stuff. I'll go into that more on the next slides. The other thing is kind of an unusual one, mostly comes to us in the GPU world, that we have the concept of an address space. The GPUs have different kinds of memory, and they can have different characteristics. They can be accessible to different threads, or they can have different performance characteristics. And languages have been starting to add the ability to express that directly, and Julia just hasn't had that ability. So CUDA.jl has had to re-implement a lot of what Array knew how to do already in base, and had to use generated functions for that. And so we're hoping they'll be able to use the built-in memory support now to be able to generate the code that they want on the GPU using all of the existing generic infrastructure that we have. And that's parameterized by module as well. So you can create code and say, like, this is a memory that I specifically want to use with the CUDA package versus memory that you want to use with the AMD GPU package. And they could both hopefully coexist, and the compiler would understand which one you were trying to use at the time. On the CPU, only the core.cpu memory exists, and so that's the only one that you can allocate and use. But when you're targeting these other platforms, the other address spaces become meaningful. And so those other platforms can define how to allocate them. We really needed atomic memory that was slightly separate from regular memory, because there's some differences in the constraints on how you need to allocate it. So for example, the alignment that you require is greater for atomic memory. And we didn't really want to just say, like, OK, now all objects have to be aligned such that they support atomic access, because that's very wasteful when most arrays don't need atomic access at all. The other way that they differ is in a way that you use them. When you talk about an atomic memory, we aren't talking about the memory itself remaining any sort of atomic state. The memory itself is constant at a given point in time. But when we do an operation like, say, add 1, unlike normal memory where we'll load that value, add 1, and then store it again, if another thread came in and loaded the value and changed it, well, you were off doing your addition really slowly on one processor, you might lose that intermediate update. And so the atomic memory lets you specify not only do you want to, say, increment that value at that location, but you want to do it in such a way that you don't lose any updates that happen on other threads at the same time. So there's really only one primitive that you must have to implement atomic. That is some sort of modify operation or a compare exchange. The compiler, though, can't always optimize it, given how many things can be expressed with just one compare exchange. So we also have a load, we have replacing, we have atomic store. So we have all these different ways in which you can specify exactly how do you want to use this memory atomically. What exactly are you trying to tell the compiler is atomic about this memory? We added similar things last year. So you can refer to my talk last year on adding it add atomic declarations for fields of structs. So if you had a mutable object last year, you could specify that one of the fields or several of the fields were atomic. But now we can have the ability to specify that an arbitrarily sized memory is atomic. And so that should allow us to write some new algorithms that we weren't able to write before directly in Julia. Some more key points about this. So as I was saying, when you specify that the memory is atomic, what you're really specifying is that you want the operations on that memory to support the ability to do them atomically. So that could mean simply that you want the store to the memory to be atomic, so that if you have another load on a different thread that's watching that store, you want to make sure that the loads can only observe values that were ever stored there and not invent a value out of thin air, as it were. Or you might say you actually want to increment the counter such that if many threads are incrementing the counter, you don't accidentally lose one of the increments to the counter. But as we were also doing this atomic work, so had already been looking at this previously with the threads, with the struct part of things, we were looking that there's an asymmetry between reads and writes that we wanted to be able to reflect in this. So when we look at a load of a value, those are always, if you just have multiple threads loading a value, there's no data race necessary. And so you can safely load values from an atomic generally on many threads without really needing to carefully think about what is the intent. However, if you ever have a write or a store to the value, and any thread is doing any other operation on the value at the same time, whether it's a load or a store, that will cause a data race. And a data race effectively just means that you need to instruct the compiler what your intent was and what value it's allowed to throw away, or what part of the operation is unnecessary. So to reflect this difference, when you just load the value, the add atomic is optional, so you can specify it, but you don't have to. And if you're stored to it, then you can have to specify add atomic. So for this example on the slide, you can load x of I, assuming x is an atomic memory object that's been initialized and has at least I elements. But when you store to it, you have to write the same x of I equals 1 that you would have written before, but prefix it with this add atomic macro. And if the add atomic macro was missing, or if you tried to use add atomic with an array that wasn't atomic, then you'd get a concurrency violation error at runtime that points you to that part of the code to say this part isn't using atomics where you probably meant to use it. And so that gives you a hint that you need to go look at your code there and see what it was I trying to express, what does the algorithm require of me in that point. They're mostly compatible with C11 for is-bits types in Julia. So if you have a plain old data type in C, and you have an is-bits type in Julia, those should get pretty much the same alignment. They'll emit pretty much the same compiler processor intrinsics for that, so that they could interop. That only works up to about double word, and then we use a different optimization, a different layout than C. So if you wanted to just interact with C, what you actually probably want to do is look at my talk last year where I talk about some of the unsafe load, unsafe store, and unsafe modify class of functions. So those existing functions that work with C pointers have been extended so that you can pass in a memory ordering and specify that you want to use those atomically. So that work actually is already in if you're just looking to interact with a library that's in C. So it really depends on who are you trying to have own the memory, and where do you want to manage where this memory is being passed around to different threads. Is it in C or is it in Julia? And finally, I think just another big point here is that Julia wants to make things easy so that you don't have to code differently depending on the properties of the object that you're trying to put in there. So this works regardless of the size of the object, whether it's abstract or concrete, whether it's a union type. And even if there's interior pointers. So if you're just wrapping an object in a tuple, singleton tuple, we don't have to allocate the singleton tuple. Same with the field of a struct. With an atomic field of the struct, we can do the same thing, where there's one or up to about 2 pointers, because that's what hardware support gives us, is 2 pointers to be able to do atomically very directly. And then beyond that, we will allocate a lock per element of the array, so that it can do still per element atomic operations, but using what's available on the processor. So it can lock that element, do the change, and then unlock that element. Now to go on to some examples. Say we wanted to make a histogram of some computational results. There's basically 3 ways of doing this. So originally, we might have just done a single-threaded approach where we create a large array. Here I'm making a histogram of 400 elements simply of the rand function. So you could plot this afterwards and try to see, is my rand function fair, or what does it do? So I compute the index using the rand function, and then I increment that memory location. This is no atomic operations, and there's no threads here. And so when I do that, it takes about 1/3 of a second over 10 to the 8th elements. Computers are great at doing large amounts of operations very fast. But say that wasn't fast enough for us, so we think, I want to make this faster. I don't have a atomic memory yet, so I'm going to try to just use a single lock over the whole array and see how does that do. And so if we make a single lock over the whole array, we can use our new lockable object to make that conveniently expressible. We could have also used a separate lock from base and allocated those separately, but this just gives us a nice version of that. And then I believe I ran this benchmark on 16 threads on a server architecture, Intel. machine, but also tested them on MacBook M2 and got similar results. And so I could show that I got the same answer. I asserted that it came out and the sum was correct, so I know I didn't lose any updates from my threads. But suddenly this took 13 seconds instead of 0.3. So we're got a very large number of lock conflicts. I think it's very fun now that we have the lock conflict information, so you can actually see some idea of what was going wrong with this algorithm. And one thing that's probably not super clear is that the plus operation is so fast. Basically, all of the time is spent with the lock trying to update it. Now we can do atomic memory, so we do the same thing, but we're just going to add even more annotations to our code here. So everywhere I had a vector or similar before, now I have an atomic memory, and at atomic, I'm going to initialize it. We don't have as much resources built up right now, so the for loop, for example, I couldn't use the zeros function because it's a store, and I needed to specify when I tried to assign all these zeros to it, how exactly did I want all of these zeros to be assigned into the array? In this case, I gave it the monotonic ordering because I don't really care. I just need it to be filled. It's still a single-threaded object at that time. And then I run the threaded loop, and it takes about a second. So we got some great thread scaling out of this. And this is actually probably what I would expect. We've really increased the memory traffic. These CPUs have to be really chatty to notify all the other CPUs that they have a new value, and then they have to go back. And so there's just a lot of back and forth that really doesn't allow us to get much scaling or get negative scaling here. But in some cases, this will be the right thing that you need, and this is now available and possible in Julia. And is quite a bit faster than the global lock, although it is not as quick as the single-threaded. So one of the takeaways is just that this is not an ideal algorithm. You would just not want to multi-thread it in this way. But it is fast, and it is now possible.
And so for what we learned about this, the biggest takeaway I had from this entire process is that really it was probably a mistake to make array be resizable, and it's way too late to fix. But sometimes there's a fixed-sized array package now that is using memory also as of 1.11. Shout out to Gabriel for primarily doing that. But yeah, just having to deal with resizability is a total mess.
Yeah, part of this work we kind of knew. We could write a lot of these optimizations in C, but it's a lot of repetitive work, and it only handles really specific cases. Once we moved this into Julia, it became much easier to write a really fast push-bang function, and now it's in Julia as well, so we can customize it in Julia. We could evaluate a new over-allocation function and see how that performs, all directly in Julia without leaving the REPL.
Also, language design, it turns out, is really, really hard. This is, I think, the third time someone has made a pull request to try to add this functionality. And it was the thing that ended up getting merged was our third or fourth rewrite of memory, as there's a lot of design decisions that you have to make, and each of them precludes other choices, and finding the right balance of things is very difficult.
And finally, memory models are hard. It's really hard to define what it means to store things into memory. What do you expect when you store it into memory, and how do you explain to the compiler what your intent is as users? So with that, we can go to Q&A. We also have a question for you. Do we try to make a breaking change to make the atomic emoji shorthand for atomic the macro?
Let's have a quick round of applause. Thank you so much. Questions right here?
How does any of that relate to string? Will one day string be on top of memory? And string is immutable and arrays are mutable. Is there a sort of immutable version of memory?
So we've thought about making an immutable memory kind. It is potentially doable. There's some complications there.
Yeah, it's been internal discussions on Slack and different channels that I don't remember which one on there. Looking at the idea that we have the ability right now to make strings, and they sort of swap between the memory and string representation in certain cases. So if you make a I/O buffer, it defaults to making a memory, but it's actually a foreign memory that's backed by a string. So when you're done with the I/O buffer, it can give you back the string that you've already populated.
Also, yes, we
so
did
in some
say
ways
that
behind the
wasn't
hood,
allowed.
it
Don't
is
worry about it.
Making a string for you with a memory on top of it. And we're discussing, I think we could make strings more directly convertible from memory, but it opens up questions on what does it mean to be a string if you can change parts of it, and what does it look like? How do you prevent changes when you didn't expect them? So we haven't quite figured some of those out. And then, yeah, as Oscar was saying, one of the other kind of memory that we've thought about using in that type parameter is constant or something of that nature to say, this memory actually doesn't support modification because it's derived from some object that doesn't support modification. And is that, we're trying to figure out, is that useful, and how would we integrate that?
Can we get a fixed size array in Julia?
A fixed sized array, I'm not sure whether we'll add it into Julia itself. We have it in a package. My guess is that might be a Julia 2.0 thing, but we'll see. Depends on demand.
I have to listen to them.
Hello, thank you for the talk. Very interesting here. So I'm just wondering, how does memory work? Is there an abstract memory type? And when you're looking at an array, I think it's really exciting to think forward to GPUs and potentially like immutable types that you might want to use memory for. And so is memory kind of hidden inside? Because it's not in the parameter brackets of like what memory are you using versus GPU array type.
So currently array, or actually array only supports the normal non-atomic CPU memory, just because we don't have type parameters for it. One of the nice things with the fixed size array package is that it does actually support all of the fancy things. So that does support atomic arrays and GPU arrays once CUDA, or once and if CUDA or someone else actually implements those.
Also, so there's two objects. Generic memory is the thing in core that implements everything. Memory is actually a type alias for a generic memory where we filled in the kind as being not atomic and the address space as being CPU. You can make a reference to a type of memory that has a different address space by using the generic memory and then filling those in to specify what kind and where. There isn't support for that in base because it's not a CPU thing. And so we're hoping and anticipating working with the GPU folks so that they can use that abstraction. However, to add more caveats to that, I'm expecting that will be what you run on with the GPU, but you wouldn't actually have an instance of that object on the CPU. So you'd have some sort of indirection objects. So you'd still have like a CUDA array object that just tells CUDA where to find that object. But because they're in different address space, like they kind of have to be indirect because it's not on the CPU accessible. So you wouldn't have the object itself.
Have time for one more very quick question.
So I'm sorry if I missed that in the talk. So there's the atomics package with an X, which already adds add atomic for arrays. So is that just using locks so far, or how does it work?
So the atomic X, or however we pronounce it, package, in the past has been using LLVM call, so it has a very limited support on what types it can work with, and it can't correct the alignment of an array. So it works with just very basic primitive int, float. I think there was support in there for some sort of any, perhaps, but GC allocated types were mostly not supported by it. So this is now providing, should be equivalent functionality, but integrated with the add atomic macro in base, and integrated for all types rather than just the specifically listed built-in ones that it could handle.
Also, I believe atomics.jl is going to be getting a PR sometime in the next couple days to weeks to support the atomic memory stuff in 1.11 because due to time constraints, the fanciness only got there in 1.12, even though the type exists in 1.11.
Thank you so much. That's all the time we have for questions. Let's have another round of applause. And just a quick reminder, we have headphones available. If anyone's having trouble hearing the speakers, they should be available up at the top. So please feel free to grab one. All right, next up, we have Christopher Carlson talking about app support in PKG. Take it away.
Thank you. So yeah, the main focus here will be app support in PKG, but I managed to squeeze in 2 bonus features that's been in, so I'll talk quickly about those first. So the first one is this new sources entry that can be put into project files. So just a little bit of background here. So the project file, as you know, it contains sort of required packages, those that you need to have. And it's sort of an input file. And then you have the manifest file, which is an output file from the resolver that contains the set of packages that are all compatible with each other and all the dependencies are there and so on. And information about the set of available versions, dependencies, and all the compatibility is available by the registries. So the default registry in Julia is general, but you can also add in more registries. But you can also add packages by URL or by path, which we call the dev package. And in that case, you don't use the registry to look up dependencies or compatibility information. Instead, you look at the project file of that specific package. And the information here, for example, the path of the package gets stored in the manifest file, so that next time you do a PKG operation, you know that path and you can look it up. So we said that the manifest file was an output file, but now we're kind of using it as an input file as well to read the path, so we can sort of feel that something is maybe not 100% right there. But the version of packages that you add by URL or by path is sort of frozen. Those are fixed, but the other packages can be, the version can vary. So unregistered dependencies then are packages that are not in a registry. And we need to either provide a path to those packages or a URL so we can download them and read their dependencies and compatibility info. But right now, they're only storing this URL or the path in the manifest file. So if we don't have a manifest, we cannot read information about these unregistered packages. So if we delete our manifest, for example, that's very annoying, because then all of a sudden we have to manually add back all our unregistered dependencies. If we have a lot of packages that are using the same unregistered dependencies, it's also annoying because you have to add all these unregistered dependencies one by one. It's possible to use this local registry, but sometimes that's a bit overkill. So the simple solution here is just to allow specifying URLs or path in the project file as well. So that's what sources does here. So I'm printing out here a project file. And then there's this new sources entry that has a URL to a package and also a path to some other package. And you can see now I nuke my manifest file, but now I can still instantiate this project because the information for where to look up these packages are there. This is kind of obvious in hindsight. Maybe they shouldn't be stored in the manifest in the first place, but at least now things are the way they should be. The second little feature then is called Workspace, which will be available in 1.12. So right now, there's a little bit of a manifest mania, I call it, in that each project file requires a manifest file to know sort of what versions you should load for that environment. But each manifest file can only provide package versions for a single project file. So every package, you have a project file there, and it requires a manifest. If you have a documentation project, it needs a manifest. If you have a benchmark project, it needs a manifest. So it's a little bit like this sometimes, where you have these manifests all over the place. And there's a bit of a problem with that in that a manifest is sort of a source of truth. It says what versions you're going to load. And if you have all these manifests everywhere, it's very easy that they become out of sync with each other. And maybe in this package you're loading one version, in the other one you're loading another version of a dependency. But sometimes you kind of only want to have the same package versions for a bunch of projects. So the idea then is, could we have one manifest that's sort of used by many projects? And that's what a workspace is. It's a collection of project files, but they all share a single manifest file. So when you do a resolve in a workspace, you go through all the project files and collect all the packages. You intersect all the compatibility constraints. And then in the end, you do a resolve and you produce a single manifest that will be next to, it's called a root project. I'll show a bit later. And in that single manifest, then are all the packages of all the projects, and all the package versions will be compatible with each other. And as a consequence of that, many PKG function now takes you can take a keyword argument, workspace is equal to true, or if you're using the REPL, you can use dash workspace. So if I do PKG precompile, maybe I want to precompile my whole workspace, or just sort of the specific project, and the same with the status and the Y and a bunch of other APIs there. So as an example here, let's say we have what I call a mono repository here, where we have some project packages in there. We have a project.toml there in the end, and we have a manifest, which will be the single manifest of this whole environment. So if we look in this project file, then we have this new workspace section. And in that, we add what projects should be part of this workspace. So now if I do status with the dash workspace here, it's going to show me many project files. All of those are included in the workspace, and then all of the packages that are included. And if I activate one of the projects inside this workspace, you can see the PKG REPL is a little bit different. It shows you that the mono repository here is the root project name, and then you have the private package, which is part of that workspace. And you can also nest workspace. So if we, inside one of these packages that were part of the workspace, also have another workspace, for example, the benchmarks here, and if we activate that, we can see on the REPL that's also part of the workspace. So if we go back here, even the project file inside the benchmarks folder there is part of the workspace, so it's not going to have an associated manifest. So all of these packages in all of these projects will end up in one manifest. And that's convenient for if we update something, we get the same. We only have one place where the versions are stored, so there's never any case where things become out of sync with each other. So that was the 2 bonus feature. Now let's talk about the main thing, which is called apps here. I don't know, we can also call them programs or executables or command line tools. There's many different names. Apps is kind of short and sweet, so that's what I'm going to use. Just want to state here that this stuff is not in any release or pre-release, so things can change. So when we talk about apps, let's think what is an app and what's a library. What are the difference between those? So one thing is sort of the entry point. In an app, we start at main, sort of. In Julia, there's a new convention where you put function and you have this main macro. It sort of defines saying that, okay, this is where you will start executing. But with libraries, there's no defined entry point. You just call a function there. Maybe you need this one. Some other package maybe calls another one. That's one difference. Another thing is how they're executed. Apps are typically called by their name. It could be from the terminal. I mean, you could run an external command inside from Julia, while a library just load them into your process with, you load a package and then you start calling things. Another difference is with the memory. With an app, they have a separate process. It has its own address space. It's sort of contained there. While with libraries, you share the memory with all the other libraries you have loaded. When it comes to dependency resolution, apps, since they execute in their own isolated environment, they don't have to think about compatibility with other things that's going to get loaded. So they sort of are resolved on their own, have their own dependency graph, which is independent of other apps you might want to run. While libraries, they are sort of interacting with each other in the same environment, so all of those are going to have to be resolved together. in some sense, we can say that all Julia packages now are kind of libraries, because you kind of always start Julia, and then you load them, and then they might have sort of like a main function, like Pluto Run or iJulia Notebook or Franklin Serve or something. But it would be probably nicer if you could install Pluto and then just write Pluto at the command in the terminal and have it run instead of having to start the Julia REPL and do this little mini startup thing. So let's think about how we should structure a Julia app then. So a good idea is to start with having as a package. So we have a standard project file. We want to have a bit of extra information. So we want to have the name of the executable. We still can have dependencies, compatibility, and maybe we want to specify exactly what version of the dependencies we want to use. So we can add a manifest in there as well. Here, there's this new app section, which has the name of the executable. And there's possibility there of putting some metadata in the dictionary there. But for this case, there's nothing there, so it's just an empty dictionary. So if we look at the content of this app, then it's called rot13 because what it does is it rotates every letter, 13 steps in the alphabet. And the point then here is we have this @main function. That's the execution point, and it loops through the arguments, and it does this rotation. And there's this new -m flag we can use to execute an entry point. So in this case, if I'm inside this project, I can run with the -m, say the package name, and then give some arguments. But we kind of don't want to have to start Julia like this into the -m flag. We want things to get installed for us, so we can just write the name of the app. So let's go further. So what do we need to do to install the Julia app then? Well, first we need to get it from the internet to our computer. We need to get the source. And it's a big overlap with installing packages here, so this is probably best handled by the package manager. It gives registry support, PKG server support. We have the REPL syntax, auto-completion, and so on. There's a lot of conveniences in there. Then we have to store the app somewhere on our system. But since the app is kind of the same as a normal package, we can just use exactly the same storage scheme. We have to install the dependencies of the app and store this resulting environment somewhere. So we could have a special environment folder called apps, and then we have the app name folder in there, and there we store the project and the manifest file, which is the resolution of that app. We should precompile that environment. And then finally, we need to create this shim that actually launches the app, which needs to be in our path folder. So as an example here, we have this little bash sim. If I print it out, it sets the load path to where this environment got resolved. It does the -m thing for us. It does the package name, and then it passes the arguments. And we also want to keep track of what apps are actually installed. So we have sort of the same as we can do package status. We read the manifest file or the project file, and we can see all the packages that are installed. So in the same way, we want to keep track of what apps are installed. So here there's this new app manifest.toml in the apps folder in environments, and it keeps track of all the apps that are installed. Now it's just this rotate 13 one. And there's also a list of all the executables provided by that package. And you can also see here we stored the Julia command that's going to be used to run this app, and also the Julia version. I'll come back a little bit to this Julia command, what Julia version is used to run it. So then there's some new PKG commands, and there's a new submodule, pkg.app, and we also have this app prefix in the REPL. So we can add an app with app add, or we could delete it with app rm, and there's app status, app update, app precompile, and so on. So kind of like all these package API we had, but now we also have one for apps. So let's do a little short demo then how this would work. So first I clear out my .julia bin, I clear out my environment thing so that I'm starting off at a clean slate. Then I do app status. It doesn't show me anything because nothing is installed yet. I try to execute this route13 command. There's nothing there yet. OK, good. So now I do this app add command then, and I give it a URL, same way you would do for a package. So this is an unregistered app then. And it's going to do these steps we went through. It's going to download it. It's going to put this project into this environment apps. It's going to pre-compile it. Now everything was already pre-compiled. And then it's going to create this shim so we can just run it. So now when I do the shell after this, I can just run this thing with rot13 ABC, and it rotates those ladders 13 steps. So instead of having this be rot13, we could be Pluto or something, and we just write app add Pluto, and then after that we can just run Pluto in our command line. Now when I do app status, it looks in this app manifest.toml, and it shows us, okay, this is the package we have, and it provides this lower case executable, rot13, and it's going to be run with this Julia command. And I can delete it, and it said it deleted all apps for this package, and this is the particular executable deleted. And now if I do status, it doesn't show anything there, so we kind of added, executed it, and removed it. Okay, everything looks good then, right? Well, so why isn't this sort of merged and ready yet? Well, there's quite a lot of complications I found out that made things tricky. So for example, what Julia version should be used to launch the app? There's like many right answers. You could have the latest compatible with the Julia compat of the app. Like if the app says, I'm compatible with every Julia version above 1.8. Shouldn't you want to use the latest one then? Maybe. Maybe you should use the one that installed the app. Like if I'm used this specific Julia version to install it, maybe that's the one we should use. In the bundle manifest, there's also a Julia version entry that says what Julia version was actually used to generate the app. So maybe the author of the app should have the decision there. And it's also, should this be integrated with Julia Up? So if I change my Julia version with Julia Up, or maybe I update it, should these apps sort of move along with that? Another thing is, should you be able to have multiple apps in one Julia package? Right now, with my previous example, I just had the main function in the package module. But maybe you want to be able to provide multiple executable in the same package. So then you could maybe have different sub-modules with different main things in, or maybe in different individual files that have main functions, but then those need to be compiled separately, and it's a little bit tricky. Should a manifest file be required so that the app author says like, okay, these are the versions we're going to use, and that's it. Those are the ones we use. Another thing is that JLLs can provide executables, and it would be nice if we could also install those as apps. So we can have a little Julia distro almost, where we download our command line tools, not only the Julia ones, but also the ones that are provided by the JLLs as apps. Should there be some naming convention, like if you write add something, how do we know that that provides an executable? Should it like be forced to end with the app there or not? Can a package be both an app and a library at the same time? So let's say Pluto, right now it's a library. It probably wants to add a main function. Should it need to add a new package like Pluto app.jl, which has the main function, or could those be in the same package? Should apps be able to customize arguments to Julia? Maybe this is like an app that wants to run multi-threaded, then maybe it should be able to say that, okay, I want to run with all threads or something. I want to run with a high optimization level. There's also this XDG compliance that people says that, oh, you should install binaries to .local bin. But typically, Julia hasn't really followed that so much. It keeps things in .julia. We have precompiled files that can get evicted. There were precompiled files in Julia. It's like a cache, but after a while, if there's enough of them generated, it's going to start deleting the old ones. But it could be kind of annoying if you want to run your command line thing, and it's going to have to start precompiling things again. There's also, what should the exact interactions with depot path be? If we go back a little bit, you see I installed things in .julia environments. That is the .julia is the first entry in the depot path. But what if that gets changed? So you run with the custom depot path. So that's, I would say, why this is not merged yet, even though like the basic usage works pretty well. So I think we just have to go kind of through this one by one and take the easy path, and then depending on sort of experience and so on, try to know what the best answer to these questions are. Yeah, I think that's actually all from me, so I end a bit early. Thanks.
Thank you so much. Let's have questions. Right up there.
So with the package REPL, you have app add. Why did you choose that design over just having add and then having something in the project that indicated there was an app inside of it?
So the question is here, why app add and not just do add and then deciding on the project file, which would happen. I think I wanted it to be explicit from a user point of view that this is going to like add a new executable to your system. So that's why this was separated, and it felt like it would be needed for like status and the other things as well. So that's why it felt like symmetric to also have app add.
Okay, I was just thinking having one may be better for combined libraries and applications.
Yeah, so if there would be combined libraries and application, let's say the Pluto example, what it would do in this case, if you just did add Pluto, it would just get the library. And if you did app add, you mean like, okay, I actually want the Pluto executable to be installed. Of course, if you just did add, then maybe it should install both the library and the app. But the thing is, the app is kind of independent of your current environment. But the library is not independent of your current environment. So if you in one single call both do like a global change, which is the app, and the local change, which is the library, I don't think you want to do that so often, maybe. Like, I would say for the Pluto case, you very rarely want to add it as a library. It's kind of, yeah.
I think you definitely made the correct choice here that app add should be completely separate from adding a library, because in Conda I've seen this go horribly wrong. In Conda, when you install a package, they add lots of binaries. And the most famous one is in Conda, if you have Kerberos as a dependency of something you didn't even know you wanted, then they install a new kinit program for you. That overrides on macOS the different kinit from Apple, and it wrecks your entire Kerberos functionality, and kinit no longer works. It's a very common user support problem that people have installed binaries that override system binaries of the same name without actually knowing it. So I applaud you for having app add separate from add too.
Okay, thank you.
I'm in on that.
Lots of fun stuff there. So question about source. So it looks like you specify either a URL or a path, but presumably when you instantiate, the URL will get turned into a local path. Is there a syntax for making sure you reuse the local path in which something that's installed from a URL occurs across packages?
So one comment was that when you have a URL here, it can turn into a local path when you install it. Yeah. Actually, what's end up in the manifest when you add something with a URL is the git tree SHA one. And based on that, Julia computes a path, but that will be based on your current depot path, so you will not have an actual path there in the manifest. It will just be a hash entry, and Julia will know, like, okay, I'm going to look through all the depot paths to find that hash entry. Could you repeat the second part of the?
Oh, I was just wondering, so if you have multiple packages that use the same environment graph source, are there protections against making sure that you don't have many different copies of the same URL checked out?
So one thing to comment here is that this sources section will only be used if this is your active project. So if you have a dependency with the source entry, it's not going to be used. So you have to have this as your active one. There's also some checks that goes through if you have multiple sources that it's going to be the same one, basically. So it shouldn't be the case where you could get confused which one it's using.
Sorry, I might just jump in here. Yeah, this is great. I've wanted to have apps, so thank you. My question is about the naming of @main. Why is it not just a normal function name that the user, any function that the user would like to call it, with an annotation out the front of that function? And how does the user test that function? Say they want to test it from the REPL, calling the main function, so things don't have to be reloaded every time. Yeah, how do you do testing of that entry point?
So basically what Julia does now is when Julia exits, it will check if there's this type of @main in your main module, and if it is, it will execute it with the arguments. And the reason why this main was specifically chosen instead of just that you could specify it in the project file or something like that was just, I think it was just a design decision. It was decided that we should have a single name, and if Julia exits while this thing is defined in your main module, it will run that function. So, yeah.
Sorry about that. Quick question about the workspaces that you showed.
Yeah.
Does this work with the testing suite?
Yes.
Yeah, okay.
So if you have I didn't have that here, but if you have a test folder with the project in, those are also going to be put into this manifest. And when you run PKG test, it's going to see that, okay, this test is actually in a workspace, so I'm going to use this manifest. So yes.
Hi, thank you for apps. I've been looking for this as well. I was wondering how just-in-time compilation works and whether you can use a system, I think somebody talked about it today, like static compilation using JuliaC, so that, for example, when I create GUIs using Julia, you know, when you first load up the GUI and you press a button, at the moment my app, it's like the first time you press a button, there's this lag, and then there's the just-in-time compilation, and the user's like, what's going on? Like, why is it not working? And it works the second time. But you have to be patient the first time.
So the question is about pre-compiling apps. So one thing to try to do, it's kind of tricky with GUI apps, because typically how you pre-compile right now, a normal package in Julia is to you have a little workload that you run. And this is sort of a workload that gets run, and you collect, based on that, you see which functions actually end up getting compiled, and those are going to get stored in your package image, and when you load that package image, you have the compiled code already there. Now, when you have a graphical user interface, it's a little bit trickier, because you want to sort of automate that process, and maybe you actually want to have to click the mouse and so on. So I guess how to do that is you would have to have a compiled workload that's going to end up executing the same thing as someone would press the button when the GUI is actually running. And other than that, there's no difference pre-compiling an app from a package. And I know, so yeah, I would say you would have to do the same as you would want to do with a package that you want to have a good pre-compilation for. Have like a representative pre-compiled workload that gets run during pre-compilation of the package, and yeah. I think that's the way it has to be done.
We have time for one more question.
I'm looking forward to Christopher other side.
Oh, there.
I'm looking forward to all of these features. So 1.12 next LTS. But no, could we also put into sources custom registries as sources of truth?
Yes, so that's one thing now, is that there's nothing, not the project file nor the manifest file, that stores the set of registries that were used to resolve this environment. So if you're using multiple registries, it's not enough to send your project and manifest file to someone, because it's only going to download the general registry, or it's already going to be there. But then it's going to say like, wait, this dependency, I can't find it in the general registry. So you somehow have to manually say like, oh wait, for this environment you need this specific registry as well. And that's a little bit of flaw about that. You should only need the project and manifest file to have this total reproducibility, but there's actually a bit of information lacking there. So I think there's two things that can be added. The first one is in the project file. I'm not sure it should be in sources. Maybe there should be a separate one saying like which registries to use. But maybe also the manifest file should include what registries were used to resolve the environment. So then you would just send your project and your manifest file to someone, and those registries that were needed to resolve this environment would be stored in the manifest and could be downloaded for the next instantiation.
All right, thank you so much. Let's have another round of applause. I believe we are taking a 10-minute break right now, and then we'll be back at it. All right, everyone, let's get started. First up, we have, I'm going to say this wrong, Stefan Sam. He is the founder of Jolin.io, and he is talking about JuliaScript.jl. Please take it away.
Thank you so much, Julian. Yeah, welcome. Thank you for your attendance. I built JuliaScript.jl to finally have Julia scripts which actually run fast. There are a couple of things to it. And you'll see there are actually 3 steps how we can speed up things. They are kind of the usual steps, but it's still really cool to see the differences. And I hope that further Julia versions will improve even further. It's a short part, first kind of a couple of words, but then we look into the concrete executions. So it's really just an executable like Julia. Instead of Julia, you write Julia script and then your script. And you pass further arguments as you want. It's really kind of intended to be as simple as possible. And the first time you run it, it will create a module for you, a Julia module, Julia package, which does then part of the compilation, pre-compilation, and the second time it uses this. It's still not doing everything, but it's doing kind of quite something. And there are kind of 2 layers to it. The first thing is that if you call Julia script, it's a bash script to have it kind of really being fast and no overhead on this side. And then there's kind of a library which does also the caching. And then finally, the module caching is done via just tracking tracing all the compilation steps, saving this in a big precompiled statement file, and then precompiling this. Has an advantage of being good in interaction with the package compiler. Maybe you have used that. But I'm also using the precompile tools, which you should have known about since Julia 1.9, widespread. And there the recompile invalidations macro is kind of a little extra thing which we can do. But let's look into a concrete example so that you get an idea. So I have here this little Mandelbrot script which I just took from Julia Discourse, and it's just doing kind of some Mandelbrot computation. We could have put this as an arc parse.jl thing or similar, and finally we are storing kind of this figure as a PNG. And if we are going to run this with normal Julia, then this time it's kind of already the best it can get, because if I'm doing this, I'm using kind of my main Julia environment. So this is now using Julia 1.10 environment on my system. I have all the packages already installed. So using Julia, I need to make sure that all this is kind of fine. And I can even make it a bit larger. And we are 3.2 seconds. And if we run it with Julia script, the first time it's going to do a little bit more. It's creating this module, doing the tracing, tracking all the compilation statements. And then afterwards, but in the background, it then runs the pre-compilation now, so that this is also kind of already done the second time you call it. It's an overhead. We have 8 seconds on the first time. And if we run it again now, very same command, we actually get an improvement. So it's slightly something. It's only a trivial example. The more code you have, the bigger is this improvement you get now. So it's really kind of using the package precompilation. And because everything is stored in such a big file of precompiled statements, what we can do in addition is to hook into the package compile ecosystem and actually create a sysimage from this data. So it surprised myself, but so actually kind of having all the precompiled statements brought into the big sysimage really gives another improvement. So this will take some time. So I'm not sure whether you've done this already. So last time I ran this, it took like 4 minutes, maybe a bit less. So building this image is kind of an overhead. And you see also, if someone knows about this, there's an error happening. It's not fatal, but if someone knows, yeah, concurrency violation error, deadlock detected and loading unit full latechify. If the package author is here, that could be something which we can solve. Anyway, it's not crucial. The compilation still happens. And yeah, and then the next time kind of it finds the sys image, it will take this and we can then compare the timings. And to give you now kind of this a bit the insight, what's going on under the hood, I want to show you kind of the that there's kind of a special directory. This is it. So under Julia scripts cache, all these different cache modules are stored, and you see that they have the file name in the front, and then a hash, which is the hash of the script. So as soon as you change kind of something in the script, a new module will be generated and compiled for you. This is the way it works. And having the file name up front makes it easy kind of for debugging these things. And if we look into it, then you see it's really just a normal script. And as soon as the sysimage compilation is done, we also see the sysimage over here. And you can imagine that somewhere these things stack up, and you can simply kind of also clear out this directory, and the caching would be redone the next time. Okay, 2 minutes. We have other 2 minutes. Okay, so this is kind of the key thing. You can also activate that the package compilation is triggered every time by setting an environment variable. Take a look at the website, at the GitHub site. So that's pretty easy. And and to add, in the future, there's kind of Windows support needed, and also the famous Comunicon package does not work yet so far. I need to do some macro expansion to make this work as well. And that's about it. Let me see. Okay. I hope it's done after your question. Let me take a look. Okay, so thank you. We have time for one question, I guess.
Let's have a round of applause for Stefan Sam. We have time for maybe 1 or 2 questions.
One question, okay?
Right in the middle.
Please go ahead.
Have you, without the package compiler, I assume you've benchmarked what is the remaining time mostly due to? I'm guessing it's actually just package loading, right?
Yeah, it's a good question. I'm not so much into the details, unfortunately. I would like to have an answer to that. Yeah, must be something with loading. I'm unfamiliar, and it's a pretty big thing missing. So we are 1.2 versus 2 something seconds, so it's just even half it by just putting all the precompiled statements into the sysimage. So there's a lot going on still.
I mean, the big difference is that when you build a sysimage, you don't have to check for invalidations when you load all the packages, because you write the sysimage after all the invalidations have happened.
Yeah.
So but if you load them as separate packages, you have to check each individual package, and that's the main bottleneck in package loading.
Yeah, thank you for the comment. One further question?
Yeah, so if I understand correctly, you get a new package every time that you change the script, right?
Yes.
So this would be then more of a tool to use when you finished your script, when it can take like command line arguments and stuff, and not really for during development.
Yeah, so it's not a big overhead. Yeah, we could improve this probably to have a bit more kind of a balance between these cases. But so far for my development, it was totally fine. As you see, tracing is only small overhead if you use it the first time. And anyway, the speed up is needed if you want to run the script again and again and again. So there, you really want to have optimal performance. Like I want to trace my whole system for some certain files and want to have the scan being super fast.
Okay, thanks.
Thank you. Let's have another round of applause. And next up, we have Valentin Charavi talking about scoped values.
And what they're good for. Perfect. Yes. Thank you. If you were here in the morning and listened to me talk about compiler plugins, you might have heard me talk about scoped values. Scoped values are a new language feature. They are arriving, I think, with 1.11. And they solve a problem that we found ourselves to be having in concurrent applications a lot. We need to persist settings, configurations across tasks. And we had a very special implementation for that for the logging infrastructure. So when you called with logger, and you set your logger to be a fancy logger or a network logger or a logger that goes to a file, that logger would be propagated across all of the tasks that were spawned within the region of the code. And that was very useful, and other people wanted to have that as well for their special settings, configurations, or similar objects like loggers. Scope values takes this notion of an inherited value, generalizes this, and then allows it for users to have it. Funnily enough, it was inspired by me reading an OpenJDK enhancement improvement, which is not normally where I get my good ideas from. And I also need to acknowledge prior work on this in Julia. Takafumi Araki proposed context variables, which had a lot of the similarities, but some key differences. What were our goals? Where we wanted them to be as cheap as possible. So when we switch tasks, there should be no copies, no overhead, anything like that. Also, when we spawn a new task, there should be no need to copy something. They should also be cheap to access, and that's actually very tricky. Like, it's very hard to get to what is cheap to access. I settled at around 12 nanoseconds. That would be lovely. And it should scale to large numbers of scope values. So we did a lot of different implementation exercises, and we scaled a huge swath of them because they wouldn't scale to 3,000 values, which is what I expect the differential equations ecosystem to eventually need anyway. They should also be minimally special, right? Yes, this is a new language feature. This is a feature that the runtime supports, but the code implementation outside of some very small things you should have been able to do in a package. And actually, there is a package that up to Julia 1.8 gives you backwards compatible for scope values. One difference to prior solutions is that I really wanted immutable semantics. So when I look up a scope value in a context or in a scope, it should always return the same value back to me. And this is really important because it allows for compiler optimizations. OK, so how did with logger look like? Right, we have a function f. It accesses the logging state. And then with logger would spawn that function. And I could concurrently also change that to a different logger. So I could have as many loggers as possible in my system. Well, if you look at scope values in 1.11, I now have this const backend, which is basically a global constant value, which I initialize to be a scope value. I give it a default value because I like default values. And then I can access this within my simulation argument as if it was something special. And now I can use with, say I want this global value to now be pointing to CUDA. I'm switching my computational backend to CUDA. And now somewhere deep in the simulation stack of differential equations, somebody calls this function. And it can look at this global constant scope value and get, oh yeah, I'm supposed to be running on the CUDA backend. And that's it. You know, very simple. Some people have asked me, why are these not just arguments? And that's because, right, if I have an argument, I need to thread it through everything. And so these scope values, I can access them from anywhere, as long as I have a reference to the actual key. So scope values are constant within a scope. You have no set index, but get index is used to access the value within. If you want to change the value of a scope value, you need to enter a new dynamic scope with width. That's a sentence to say. And if you're messing with current task.scope, you're using undefined behavior, and the compiler will come and eat your code. There's one person I know who currently is doing that. Please stop. But while scope values are immutable, they can point to mutable data. So if I put a dictionary into a scope value, I suddenly need to think about, OK, what happens if I mutate that dictionary? So my recommendation is on scoped entry to then create a new dictionary where I merge the values across. One of the implementation secrets is that a scoped value actually is empty. It's just a mutable struct. Why is it mutable and not immutable? Because of object identity. So when you create a new scoped value, that acts as a key to the hidden persistent dictionary that is in the background implemented. We could have gone with immutable dict, but then we couldn't have scaled to 3,000 variables. Also, one of the lessons I had while implementing it was the storage location is typed as any. And to maintain that uncertainness, that any, as long as possible to avoid performance penalties, and just at the last moment before handing it back to the user, do the type conversion and the potential unboxing. Thanks to Keno, we have optimizations, so current scope can be get folded. The compiler can now reason about persistent data structures. Right now, there is a little bit of an inefficiency in that an access might allocate. Cody is working on fixing that, so thanks, Cody. And the funniest use I found is in MLIR.gl, where it changes the dynamic library being used by the API. So you can load multiple versions of a dynamic library and have one package access it all. Which, why, is a good question, but it works.
All right, round of applause for Valentin. All right, we have time for 1 to 2 questions.
One question. Do we really have a use case with 3,000 scope values?
Not yet, but I know my customers. Actually, I recently found a use in Cedar where it might look like they have a lot for no reason that I fully understand, but yeah. They're growing, they're multiplying, and that's the problem with a language feature. We don't know. So we need to be robust, and it wasn't too costly.
This seems related to dynamic scope variables in Lisp, in Common Lisp from the 70s. Is that?
Yep. It's basically the same thing, except that it's not a variable. So I went back into literature, and that feature-ish thing has been existing for a while, but the difference is it's not mutable. Dynamic variables in Lisp are mutable, and I think that's why they fell out of fashion, because they're so hard to reason about because of that.
Thank you so much. We don't have time for any more questions, but let's have another round of applause.
Thank you all.
And quick reminder, if the construction noise is getting a little loud, you're having trouble hearing the talks, we do have headphones up at the top.
All right.
All right, and next up we have Joris and Anand talking about renovating some stuff.
Why, that's a coincidence. Thank you, Julian. All right, yeah, so hi, everyone. My name is Joris. I'm Anand. We work for Julia Hub. This is completely unrelated to Julia Hub. We work on JuliaSim. We use some of this. We use the tool we're going to talk about to support some of our processes, but that's where the similarities end. So we're going to talk about today is automated dependency management specific to Julia. And the renovating thing is, well, very apt, but it's also, the tool that we're talking about is called Renovate, hence, you know. So like any good story, at least related to Julia, this starts with a nerd snipe. Also, again, Mose was sort of at the source of this, asking about 8 months ago, like about Renovate, some dependency update manager, similar to Dependabot, and there's been some pull requests open for a long time, or not a pull request, an issue, like asking for support, but it's been stalling for years. I was wondering if it, could be a replacement for Compat Helper, or maybe just being a wrapper around it. At the next point, Avik sort of goes CC Baugler, which is my nick. So that's when I got pulled in. Luckily for Mose, this also happened. So he, the maintainer, Reese Arkins, of Renovate, Mose asks, like, is there a way to make this happen? Do you need help with anything? And he just goes, well, you do it. So now I've been using Renovate for a long time, mostly combined with GitLab because it supports many different platforms, typically to manage like JavaScript and TypeScript dependencies, some GitLab CI dependencies, Docker, stuff like that. And so it's a core tool that I use. So I've always wanted Julia support in it. Like it's been on my list to do for years, but this was sort of the straw that broke the camel's back, so to finally just hop in it. And so within the JuliaSim team as well, we sort of use Renovate to manage these front-end dependencies, stuff like that. So yeah.
So real quick, let's first start out by answering the questions that Mose had for us. Starting off with, what is Renovate? So Renovate, as Joris mentioned, is a dependency management solution. It's primarily written entirely in TypeScript, and it can be compared with Compat Helper and Dependabot, which we'll get to in a minute. It is AGPL licensed. It was started in 2016, and it was also acquired by Mend, which is an open source company which is an open source security company. It was acquired in 2019. It's available in 3 formats. One is a CLI, which can be used on any CI platform that's running a self-hosted instance, or it can also be run locally. We typically use it in the CLI form in Julia Hub and also for our personal projects. It's also available as Docker container images. There is also a free public GitHub app, which we'll sort of be walking through and showing you how you can use in a live demo. Sure, live demos are great, right? Nothing can go wrong. And there's also a paid offering if you want to use it for your enterprise needs. So this is sort of a demo pull request that shows how Renovate opens up a PR. So you can see multiple metrics here. One is essentially a quick overview of the kind of changes that are being brought about. There's also release notes that are included, which the package authors themselves include while making a release, and breaking changes and so on and so forth, right? Yep. Here's what the dependency dashboard shows up like. This is essentially a go-to place where you can see all the dependencies that are going to get updated. And some more features of Renovate, right? For starters, Renovate is extremely configurable. And by that, I mean extremely. You can configure it down to as granular level as you can, right from when you schedule the updates to what kind of packages get the updates, what kind of packages you don't want to get updates for. It works very well within mono repo settings, which is something that Compat Helper doesn't really cover very well. It also has shareable configurations, which is something that we are sort of seeing an emerging trend, right? As in with SIML ecosystem, where we are moving towards more centralized CI setups for bigger organizations, so it gets easier to track things.
Yeah, so that is personally, that's one of my more favorite subjects. Right? One of the things that always annoys me about many CI processes is like copying stuff everywhere. Those that might have seen my talk last year on GitLab CI processes, that might seem familiar. So I really like this sort of, there are just two central ways to sort of have centralized configuration for Renovate. One is it respects if you have like a top-level .github repo in your organization and you put configuration in that, then it just applies to everything underneath that, so you only have to configure things once. That's nice. And what is also quite, what I also like is you can have these configurations, you can ship them as NPM packages, or they don't even have to, actually NPM is deprecated, scratch that. You can put them up on a GitHub repo or a GitLab repo and it will just fetch the configuration from there and then just apply it to whatever project you're working on. One other really nice feature that I like is custom managers. So what I often run into is when writing CI/CD pipelines, GitHub Actions, GitLab CI, it doesn't really matter, is that I need to keep track of certain tools that I use, like Julia Formatter or anything else that I want to use a very specific version of, but I don't want that in my project toml or in a separate project toml. It's just annoying. I want to know where that version is right where I use it. So one of the things that the custom manager stuff is really nice about is that you can define custom dependencies, sort of. So you can know, like, that thing, that string over there in that file somewhere in my repository, that's actually a version you need to maintain for that dependency. And from then onwards, it just keeps that stuff in sync as well. So that's a really nice thing of, I personally really like that. And we'll actually see that in action just a bit later. It can do stuff like, typical things you'd expect, lock file maintenance, so, your package lock, your manifesto toml would be able, maybe, if it has Julia support, I don't know. It has grouped updates, right? Many times, like Anant mentioned, like in the SIML ecosystem, there might be groups of packages you want to update all at once. You can define that. There's many, actually, like, it comes baked in with many like custom monorepo or things that need to be grouped together. Obviously, not for Julia at this point. You can, as Anand also mentioned, updating can be, or updates can be scheduled as granularly as you want, like from a month or once every 2 months or every day or as soon as stuff comes out. So that's quite nice. It releases very often. It uses semantic release, so basically every pull request that does anything that's a feature or a fix gets immediately released. Community is helpful, which we like, right, if you need help. And yeah, it's a really mature product. So next up, we just want to walk you through a quick demo, sort of how do you get this set up, typically. So we'll be sort of interleaving back and forth a bit because we need to wait occasionally. So we'll be coming back to the slides in between. So what we're going to demo is how we add this to a, let's see if this actually works like this. OK, let's do it like this. So I have a little demo repository here. That demo repository has a package JSON for NPM, which includes a single dependency. It contains a single dependency. For those that aren't familiar with NPM, right? So the caret means it needs to stay within, I want it to be compatible within version 35. So this is one dependency it's declaring. Then the other dependency this thing has is, well, that's too big, is in here. It's a GitHub action, which has a dependency, which we've actually, I've pinned the action, right, which is to a specific Git shell, which is typically right, sort of best practice to do, so you don't run into supply chain attacks instead of pinning to a tag. And you see this nice helpful version here that I like to keep putting in here for myself, so I remember what version I'm actually using instead of having to look up the SHA every single time. So we'll sort of let Renovate loose on this repository and see what it does, sort of to give you a feeling of what it does, how it differs from something like Dependabot or Compat Helper. So to do that is it's quite simple, right? You go to the Renovate GitHub app, you hit install, which then takes you to where do you want to install it? Well, in this case, I want to install it in my own organization for a select repository. So you can install it globally as well. So that's the one. Yeah. Just scroll down a bit. Now, if you use the GitHub app, I do have to sort of say that. I knew this was going to go wrong. You'll need to agree to the terms of service by Mend. Shouldn't be too much difficult stuff in there. We tend to use it on different platforms as well, so we tend to self-host. But in this particular case, we wanted to show this off. So let me just quickly sign in. Security best practices. All right. That's that. So it just fetches some stuff over from GitHub. And basically, we get dropped into the Mend app, which is provides you an overview of all the projects you're managing. You can already see that it started to sort of renovating our project. So if you go in, and it's probably take a second, we should oh no, this is the wrong repo. We should see a configure renovate. Well, I'm going to close this one. Well, I don't want Dependabot. So we get a nice PR that's going to tell us how it's going to onboard, what changes it's going to make to our repository. It tells us the package files that it detected, which is very convenient, right? Because occasionally you run into a situation where you go like, why are you not keeping track of certain dependencies? You just go into this dependency dashboard, which echoes the sort of similar information, so you can see the dependency that it actually finds. Then it's going to say, like, this is the standard configuration. This actually automatically updates if you change it. If you have your own configuration that you use for your organization, that will be reflected here as well. And then it tells you what it's going to do. Something's messed up. But anyway, we'll just keep going. So it actually tells you, like, I'm going to open up these pull requests. So it's going to update the checkout action. And then it's going to file 2 update PRs, one to bring the Renovate version up to the most recent version that is available within the 35 range and within 37. And then the major upgrade to V37. So it's nicely separating those out as well. So I'm just going to merge this. And we're going to wait a bit because it needs to open up some PRs, which will take a while. So we'll just quickly move over back to the slides. And I'll hand it over to Anant for a bit.
Yep. So I think in some essence, we answered the first part of the question. What is Renovate? Technically, how does it work? And I think now we should probably just discuss how it holds up against the alternatives, which are primarily in Julia land, Compat Helper, and Dependabot. Well, not really Dependabot, right? Because until very recently, they didn't accept any new ecosystems. This is up until the last 6 months or so. Dependabot is exclusive to GitHub only. You don't have the kind of granular scheduling for when you want to trigger these updates available on that. You can't also run, being GitHub exclusive means that you can't also run it on other CI platforms. So basically, people run things on GitLab and Atlassian and stuff. They don't have access to something like this. It also doesn't provide a default groups, which is essentially something that makes it harder for you to run it on mono repos. And Compat Helper is Julia only. So for instance, in the demo that we'll walk through, you'll also see that the checkout action will get automatically updated by Renovate, which is not something that Compat Helper does, right? Compat Helper only cares about your Julia packages in total. Compat Helper is also less featureful. In comparison with Renovate, there are many complicated cases that Compat Helper doesn't deal very well with, particularly log file management and stuff. I mean, you could argue that it's a language level thing and that you might run into it with Renovate as well. But with Renovate, you at least have the primitives that are necessary to get something like that in place. And it's not as much of a lift. Compat Helper also directly uses PKG. Our Renovate configuration that we're going to be demoing right now doesn't directly use PKG. But we estimate that at some point it will. And we'll also get to that later part in the talk.
All right, so let's check back on our pull requests to see if they're actually there. So one of the things I'll note, right, is that we specifically put in, like, the Dependabot is MIT license, which might be a thing for, a good thing for some people. That could be a pro. Renovate isn't, right? It's AGPL license, so you can't make money off of it, of hosting it yourself. Back to my demo. refresh. We should have some pull requests. Yeah, this is the wrong repo. Anyway, it doesn't matter. So we can see that it filed a dependency update for Renovate 35, right? So it keeps it within that same major version. We get this nice little, we get the release notes, which in this case are very long, so I'm going to close them again. One of the nice features that it also has, if you provide, if the backend, sort of the data source, as it we'll get into what it is a bit later. So NPM provides timing information about releases, and they actually keep a dashboard that they include into the pull request, where this is how old it is, this is how well adapted it is, this is for all the CI, for all the pull requests that we filed the pull request for that actually had passing CI on the first try. So this sort of gives you some confidence about, can I merge this without looking at it again if my tests pass? So I'm confident. Well, so in this case, because we actually had the caret in here, right? It only updated the package lock. Not going to look at the diff, it's going to be too big. I don't need to approve. So we're just going to merge that in. Now, unfortunately, demo effect. We didn't ask hard enough. No, we don't want that. That's unfortunate. That was supposed to work. It didn't. So what we'll see is actually, in the onboarding configuration, we saw that it was going to open 4 pull requests, and it only opened 2. So by default, Renovate is rate limiting what it's doing, so it doesn't overwhelm your CI, which is typically a good thing, right? You don't want your CI getting hammered by it opening 20 pull requests. So these are rate limited, which is where this dependency dashboard comes in useful again. You can actually just go in, and because this is one of the advantages of using the app, right? If you're using a CLI, you're going to have to do this on a schedule yourself. You're doing it running on a cron job. Running the app makes it responsive to webhooks. So you can, if I click these, if I enable these two to indicating that I want PRs for these, it's going to open them up in the back end. If we go into the mend dashboard, we can actually see that it kicked off, or we should be able to see that it kicked off a few new runs. So we'll, again, have to wait a little bit for that to kick in, but, and I'll come back to it because I want to show this one in action, what it does here. So let's move back to the slides for just a bit while we wait for those PRs to get opened. Oops. And dive into something completely different. Been a bit of a sales pitch so far. So let's dig into a bit of this slightly more technical, not too technical. What do we need to add Julia support to Renovate? So Renovate is very orthogonal code base, which is quite nice. And to be able to add a new language or a new ecosystem, language is not entirely accurate, right, because it's package ecosystems, you need to implement 3 things: a data source, a versioning strategy, and a manager. And for Julia, well, we have to do all 3. Right? We need a data source to know where to pull packages from. We need a versioning strategy because Julia's versioning is not the same as NPM or any other, at least as far as I know, any other package ecosystem. And we need a manager. And a manager is basically the thing that knows where are, by default, for certain types of projects within an ecosystem, what are the default locations where dependencies are being tracked. So in our case, a project toml and a manifest.toml. So just sort of to not immediately show what we're currently capable of doing, it works. Yay! Can you use it? No, not yet. It even works for like properly private package servers. I'm not going to tell you how to do it, but it works. So this actually pulls it out of the Julia Hub registry. This is a private Julia Hub package. Well, it's not private. You can get it, but you need to have access to that registry. So this also support it. You can see we pull the nice little change logs for HTTP as well. You get a link back to the original package. So what is the actual current state? As I said, unfortunately, you can't currently use it. The pull request is open. It's been open for a while. I needed to fix and fine-tune a few things. It's a consequence of trying to get something into a very big code base that's very mature. It takes a bit longer. So as I mentioned, private package servers are supported. the dependency update pull requests, as we sort of showed, they support change logs and links back to your project websites as long as you have the repo field filled in your project HOML. I know what to do for versioning. I've dug into it already. Apparently, for those that didn't know yet, at least that's the way I found out, Julia's versioning is mostly a mix of NPM's versioning and Conan's versioning. They share similarities. Not sure why, but that's how it works. And then it has its own stuff. And we just need to work on the manager just to get started. Well, let me just quickly go back to the pull requests. See if we got the new ones up, just to show. Yeah. So this is one of the nice things where it actually does separate major versions, but it does skip the ones that you don't care about because you probably don't care about upgrading the 36 if 37 is out. So you can stay behind on an older version and keep getting updates for that while also just getting eventually upgraded to a next version of a package. So one of the nice things I particularly like, I'm not sure why it's doing, okay, just demo did not do it well enough with the demo, not pray to the demo gods. So what this was supposed to do is actually update the commit SHA and then automatically also update the comments. Not sure why it didn't work. That's what it typically does. So if you have these types of comments behind it, it just keeps it in sync with the commit SHA, which is very nice from a documentation perspective. So demo failed.
What can go wrong in the live demo?
4 minutes. Okay. Taking too long. So we can't actually do, we don't have a manager yet. The nice thing, as I mentioned about the custom manager stuff, is you can actually implement something like this, which you just add to your repository, and then now it supports Julia. If you, granted, you have the data source merged. Well, it can manage stuff inside a project HOML. Let me rephrase it that way. OK, I'm going to hand it over to Anant real quick.
Yeah, so in this entire process of trying to figure out Renovate's code base, how we integrate it with Julia, how we can add Julia support for it, we have sort of come across a few big hurdles and a few very convenient things, and this is basically all of that. So the first one is package server starballs are all or nothing. If you want something for a given registry, you get the entire tarball, which, if you don't know, is about 7 MB zipped. And when it's unzipped, it's about 250 MB. So anytime you want a dependency update or you trigger one, you're pulling in 250 MB, which is not optimal, obviously. There is also multiple ways you can interact with registries. So we decided to go with package server because that makes it platform agnostic. You can pull from GitHub, GitLab, Julia Hub, wherever you like. The Renovate code base is really big. It's about 600K lines of code, but it also helps that Renovate's different abstractions are very well orthogonally separated, which makes it much, much easier to contribute to. There's also very, very extensive HTTP request mocking library setup with Renovate, which we can use for writing tests, and that makes TDD easier. Also, the third one is a personal gripe of mine, which I have an issue open for as well, which is basically that PKG doesn't support resolution of environments without instantiating the project first. Even if you try resolving it, it downloads the entire packages itself, which just adds more to the latency. And it also makes log file management harder, which is one of the reasons why Compat Helper also doesn't give log file management, as far as I know. So some advice or requests, especially if you're looking to integrate with Renovate in your code bases. First and foremost is stay up to date. Things move fast, especially in Julia land, even more so in SIML land. I think we have about 3 SIML releases every day, as Chris was saying earlier. So staying up to date is very important, obviously. And the thing with Compat Helper is it doesn't always keep you up to date. Compat Helper's PRs are, by default, they use the GitHub token in a lot of repositories, which means that for the PRs that they open, CI tests don't actually run. So you don't entirely know if it works or not, right? And if you don't believe me, just look at ordinary DFQ, modeling toolkit, or any big repository. But with Renovate, you use a dedicated token, or you use a GitHub app itself, which ensures that CI runs every time. In addition to that, you also get all these nice metrics that Joris mentioned out earlier, right? With adoption, age, the confidence in that particular update, which just makes updating to a newer version a lot more easier. Please provide change logs. Change logs are great. They help people who are updating downstream It makes it a much more easier and less painful process. I know that fix, make things work commits are great, but then it doesn't really help a lot when you're trying to debug what went wrong where in an upstream package. Pin dependencies, having better defined compats for dependencies will greatly help people keep up to date. And also using downgrade CI. I know downgrade CI is a contested topic, but having it is better than not having it at all. And if you're interested in helping, please reach out to either of us. This is something we are actively working on as well on our own time. So yeah, that's about it. Thank you.
Thank you very much. Questions? All right. In the absence of questions, I have one myself. Have you noticed any Julia packages in the ecosystem, public packages, have been using Renovate as part of their CI and workflows?
Do you want to take that, or should I? I'm OK either way.
Well, I don't know. Well, I know mine use it, but not for Julia support, obviously. But no, I'm not.
I think it's something once it's in a more production-ready state. I think it's something we sort of want to slowly start rolling out. Yep.
So this isn't the question, but you mentioned the package doesn't support, PKG doesn't support resolving manifests without instantiating them. So there is an environment variable called Julia PKG precompile auto. Did you try this?
That's not the same thing.
Yeah.
It doesn't precompile, but it still downloads everything.
Yeah.
Oh, OK.
So in your depot/packages folder, the packages still get pulled in.
OK.
Yeah.
I get it. Thanks.
Another question?
Oh, no. Christopher's asking a question.
So regarding the PKG and instantiation when you resolve, it should be fairly easy to fix. It's just that if you have packages that you're added by URL, for example, you need to download those to actually do the resolve. But what we could do is you download those if they exist, and then you do the resolve, and then you don't download anything from the PKG server. And I guess in most cases you only have version dependencies, so in that case it doesn't matter. So I think it should be fairly easy to fix.
That is optimistic to hear.
So just sort of to clarify, that wouldn't even work right now, right? Because only in a manifest, because you can't depend on something in a project home only. That would only affect lock files.
Yeah, so that would only be the case if you had a manifest that has a URL added.
Does it still hold for the new sources thing?
Yeah, you still have to download it, because otherwise you can't have access to the project file, which defines the dependencies and compatibility.
But a sources thing would allow URLs, right?
Yes. Yes, but you still need to download those.
Oh, yeah, no, for sure.
Even if you want to do a dry resolve or whatever you want to call it.
All right.
Thanks.
Any other questions? All right. Well, thank you so much. Let's have another round of applause. And a quick reminder for anyone who's just coming in now, we have headphones up top streaming the audio in case the construction noise is too loud. So please feel free to grab one.
know logically that I'm not.
See him.
Okay, so I can't get the mirroring to work, but this is fine. All right, so hello everyone. My name is Fredrik Ekre, and I'm a software engineer at JuliaHub. And today I will discuss a little bit about the logistics behind the package manager. So maybe some of you would rather play in the sandbox over here, but well, now I'm going to bring you behind the scenes here a little bit. All right, so just to give some context for this talk, so there have been many talks in previous JuliaCons about the package manager, and in 2018, the current iteration of the package manager were introduced by Christopher and Stefan. So it was labeled PKG 3. I had the talk in JuliaCon 2019 discussing about the concepts of the TOML files and environments and so on. In 2020, Christopher had another talk discussing new features in PKG. And in the online version of JuliaCon, there was a discussion from Stefan and Elliot about, again, some updates, but also this, what they call the PKG protocol. So that's kind of where all of this started, which I will discuss more today. Again, this wasn't at JuliaCon actually, but PackagingCon. Christopher discussed the concept of registries and so on. And last year, we had the new features of package extensions. And earlier today, Christopher also discussed some new features with sources, workspaces, and apps. So what's common with all of these previous talks is that they kind of discuss the user-facing parts of the package manager. So I guess that's the interesting part. But what hasn't really been discussed up until today, I guess, is what happens behind the scenes. So basically, what happens when you add a package or when you add the registry and so on. So there has to be some mechanism to get these resources from the internet and download them to your machine. So that's what we will be discussing today. Okay, so brief headline for this talk. So first, I want to take a peek into the .julia folder located in your home directories, because that's kind of the first entry point to finding resources like packages and so on. And then I will discuss the PKG client. So in this setup where we have a server and a client, the package manager becomes the client. So the package manager requests resources like packages, artifacts, and so on. And then we will take a look at the server side, and I will discuss the package called pkgserver.jl, which is an open source implementation of a package server. And that's what's actually providing all of the resources. And then I will discuss a little bit of the current server infrastructure, which is hosted by the Julia Lang organization. And then in the end, I will show you and discuss how you can run your own server if you're curious about this. OK, so let's start with the first part. So this folder, .julia, in your home directory is where basically everything is stored. So if we take a look, so this was on my machine. If we just run the tree command here, you can see that I had something like 30,000 directories and over 150,000 files. So there's a lot of things inside of this folder. And maybe as a side note, if something goes wrong in Julia, you sometimes see the advice that you should just delete this directory, but that's not something I would recommend. It includes a lot of things that you really shouldn't delete. OK, but if we just look at the top-level directories here, so there is one folder called artifacts. And yeah, of course, there are artifacts inside this one. there is a clones directory, which is caching of Git repositories for that the package manager uses if you install by URL. So in this case, PKG will git clone it and then take a snapshot and move it to the packages directory, which we'll come to just below. The compile directory is where all of the precompiled files or package images are stored. So I guess don't take a look at the size of this folder. We don't talk about this. Config is where you, for example, have your startup file. Environments here is where the default environments like v1.10 are located. Logs are, for example, the REPL log and some manifest usage, which PKG uses to keep track of the projects that you're using. And then we again come to something more related to this talk, which is the packages directory, where the package source is stored. And we have a registries directory and a scratch space directory. So for this talk, we will mostly be considering the artifacts, packages, and registries subfolders. So we can take a look inside these as well. So if we look inside .julia/registries, you should typically see something like this if you have one registry, which is the general registry. So there are now two files. There is general.tar.gc, which is a snapshot of the Git repository of the general registry compressed into this one file. And there is a companion file, general.toml, which keeps track of some metadata about this tarball. So we'll come back to how these files end up on your machine. But we can take a look into this metadata file, general.toml. So it includes a file or a key called git3sha, and I remove this here, but it's just a SHA. And this is the 3SHA of this specific snapshot, which is currently installed on your machine. There is a UUID here, which is the UUID of the registry itself. So just like packages have UUIDs to have a unique identifier, registries also has this. So this is the UUID of the general registry. And then finally, there is a key with a value, a key path, which just points to the tarball which this metadata points to. OK. So if we take a look into another subfolder, which is .julia/packages. So this is where the packages are stored. So now I just included the very first package, which happened to be 80 types on my machine, and the very last one, which was XKB common JLL. So as you can see, the source code of the package isn't under this named folder directly. So for example, for AD types here, we have 4 subfolders here with some random characters. And these are actually corresponding to 4 different versions of this package. So on my machine, it happened to be these 4 versions. So I had 1.2.1, 151, 0.24, and 0.27 installed on my machine. So by default, Julia actually stores, when you install a new version, the old one isn't deleted automatically. And for this JLL package, I only had one version here. And finally, the artifacts directory. That's just a bunch of subdirectories with 3 SHA names. And these are artifacts which typically comes from JLL packages, so these contain binary dependencies and so on. So this directory is very opaque, I would say. It's difficult to navigate, and typically you don't need to. OK, so how did all of these files end up on my machine in this case? So let's take a look at the package manager as the client in this case, and how it fetches all of these resources. So let's start with registries. So there's actually three different types of registries which are currently supported. So you can have, in the registry subfolder, you can have a standard Git clone. So that's just a Git repository, so that would be a folder with a Git subfolder, for example. Typically, this is something you will have if you have, for example, a private registry or something that you have cloned yourself. So the package manager can update this one by Git pulling and so on. The second version is a bit outdated now, so I put it as a legacy version, which is basically an unpacked repository snapshot. So taking this tar.gc file and unpacking it, and then store a metadata file inside of it. But this is not really used anymore. The package manager can handle it if this is the case. But the new way, which also was discussed in Christopher's talk before, is to keep the repository compressed. So we just have one single file, which in the previous talk they mentioned it's around 7 or 8 megabytes. And the package manager will decompress this and read this on the fly, read it into memory. So this is the default option since Julia 1.7. And especially for slow file systems, this has been a huge improvement because there is just one file. Previously, we had to unpack the registry. And while it's much better now in the Julia 1.0, there is still 4 files per package. And as you've seen in some other talks, the number of packages are constantly growing. So this new setup only uses these 2 files, which is pretty nice. All right, but how did we end up with these files? So the client will talk to the package server. So by default, there is an endpoint called /registries. And if you request this one, then you get a response from the package server with a list of registries. So in this case, I have 2. So for example, registry with UUID A and another one with UUID B. And they also include the SHA of the latest or the current snapshot. So the response here is really signaling to the client, these are the registries I know about, and this is the latest version. So the default package server, which you can find on pkg.julialang.org, only provides a single registry, which is the general one. So this is how you can reach this one, and you get some output with a UUID and a tree SHA. So the process looks something like this, and I hope you can see this. So what happens when we run pkg update or pkg registry update? So the first thing that happens is that we request this endpoint, so /registries, and then we get back a list of registries that the server knows about and the SHAs. And then we look up, or we match the SHA of the server with the SHA that we have locally. So we can go back here. If you remember, in the registries folder, we have the metadata file here, and here we store the SHA of the version that we currently have. So if this one is the same as what's or what's provided by the server, then we are done, because then there is no newer version to download. So that's the happy path. Then it's just a small request, and then we're done. If the SHA is different, that means that there has been an update on the server side, and there is a new registry version that we should download. So in the response, if we go back here, in the response you get the new endpoints that you should download from. So we can do that. We send another request to /registries with the UUID and the SHA, and we get back a tarball of the registry. And then we just need to update the metadata file general.toml, and then we're done. So this is the flowchart of updating the registry. So it works similarly for packages. So there is a server endpoint which is /package UUID/SHA-1. So the UUID and, for the packages and the SHA-1 for each specific version, they are available in the package registry. So that's something that the package manager finds there. And when we request this endpoint, the server responds with, again, an archive or a tarball with the package source code. And then we just need to unpack this one into the correct folder, so .julia/packages/name, and then we have these random characters that we saw before, which is called a slug, and the slug is basically a hash of the UUID and the 3 SHA. So for example, to download the example package at version 0.5.3, this is the request that you would have to do. So this is the UUID of the example package, and this is the 3 SHA of the latest version. All right, so again, okay, the header is wrong here. This is about fetching packages. So the flowchart is similar, or it's a little bit simpler actually, because we don't need to do double requests to the server as for registries. But if you add a specific version, so for example here I'm adding example at 0.5.3, then we can look up the UUID and the SHA in the registry. We can compute this slug, and then we can check, does this one already exist on my machine? And in the happy case, it does, and then we are done. We don't need to download it again, because maybe we have used the same version in another project. So that's great. Otherwise, we request from the server from this endpoint, and then we unpack it into this folder. Okay, and then finally for artifacts, it's basically the same. Artifacts are defined by a 3 SHA, and the endpoint is simply artifact/this SHA. And it's something that you look up in the artifacts toml file. And maybe it's a bit interesting, but this one is located inside of the package source. So we have to download all of the packages first in order to then request all of the artifacts. All right, so I will speed up a bit. So this is basically the same. If it already exists, we don't need to do anything. Okay, so then let's take a quick look at the other end of this process. So the package server is an open source implementation of this of the server component in this protocol, and it's built it's a Julia package, and it's built on top of http.jl. So it only uses HTTP 1.1, but we have configured it with Nginx as a reverse proxy with TLS termination. And package servers again talk to something called the storage server, which stores everything. But I will not go into much detail here. So it, by default, has a couple of endpoints. So I've discussed the first ones here. You can look at the other ones are /meta, which is some metadata about the server itself. And there is a /metrics endpoint, which provides Prometheus metrics. And if you're curious about that, I have another talk on Friday about this. So what does it look like when the client requests a registry? So the first, we take it from the top left, the first thing that happens is that the package manager requests this /registries endpoint. The server then responds with, these are all the registries I know about, and the specific versions. And then if the client doesn't have this one, it will be another request to download this one. And then we need to check, okay, does this resource exist on the package server? So is it cached? And in the happy case, it is, and then we can just send it back to the client. Otherwise, we have to fetch this one from the storage server, and then we cache it, and then we send it back to the client, so that the next person that requests the same one we don't need this extra request to the storage server. And in the interest of time, I think I will go a bit fast here, because this is basically the same, but for packages, which are also cached, and same thing again for artifacts. So let's take a quick look at the infrastructure that is hosted on the Julia Lang organization. So currently, this is what it looks like. So we have package servers across the globe. So the red dots are package servers, and the black ones are storage servers. So currently, while you are here in Eindhoven, all of you probably connects to the one in Frankfurt, in Europe. So on each of these locations, the setup looks something like this. So we have an Nginx load balancer in front, and then we have a number of package servers behind, which actually does the caching and the work. And these talk to the storage servers. Yeah. So the Nginx frontend does some load balancing, and it hashes the resources in a consistent way, so that, for example, the example package version 1 always goes to package server 1 and so on, so that we don't duplicate the caching. So the package server has an LRU cache of the resources. So when the disk space grows too large, then the resources that haven't been requested in quite some time are deleted. So this is provided by another package, which is called File System Data Structures, which I recommend you to check out to do this caching automatically. And I don't have an exact number here, but the cache hit ratio is very, very big. And I would attribute this to, well, the cache itself is kind of large, but also most users are always on the latest patch version of packages. So nobody really requests packages from 2 years ago. So there's no point in caching these. So this used to be the setup when I submitted this talk, but some of you have seen this post on Discourse. So currently, we have changed it up a little bit. So the caching part have been moved to a different cloud storage. So the setup is slightly different, but the principles is the same. And the package server implementation still supports this caching. OK, so finally, I just want to show that you can run your own package server. So why would you want to do this? Well, it can sometimes be beneficial to do some local caching. For example, if you have a cluster or a company network or something like that, where you can set this up as a server on your own network and then point all of the PKG clients to this one, and then the latency should be almost instant. You can also configure if you're interested in providing more, for example, private registries or more packages and so on. And of course, because it's fun to do something on your own. So I will not go into the details here, but the PKG server repository contains examples for how to set this up with an Nginx load balancer in the deployment directory. And this is exactly the same setup that we are running on pkg.julialang.org. So finally, I hope I can show a demo here. Let's see if I can zoom in a bit. Yeah, clear. So I hope you can see, but basically I have just cloned the PKG server repository, and I've actually instantiated already. Let me just check. Yeah, OK. So to run this server, you just there's this file called in the bin directory run server. So this one will start up. OK, didn't work. This should start up. OK, did I misspell somewhere? OK, I will skip this one. But that should start your own server. And then you can point at it by setting the environment variable Julia PKG server. And then you will have a server running on your own machine. So then your machine will do all of the caching. Kind of stupid, perhaps, because the .julia folder already has all of this caching. But yeah, it's something I can do. All right, so that was my talk. And thank you for listening.
All right, any questions?
Hello, thanks. Beyond caching, there's a natural progression into differential updates. Is there any thoughts on that?
Yeah, so there is some ideas about not having. I think it's mostly for to serve precompiled files. I mean, a package itself is usually just Julia source text, so these are not really that big. It's not really a bigger deal to do this. But as I mentioned, the .compile directory is getting quite large because it contains the compiled code for all the packages. And right now, this is something that has to be generated on the user's machine. But there is some discussion on how to do this on the server side and then download like a diff of what you need. So basically, the PKG client would then say, OK, this is what I have, and the server side would compute like a diff and send that back. But I think it would be mostly useful for precompiled files because like the packages itself isn't really that huge.
So is the standard setup, does it work as a pull-through cache for the general registry if you set up your own registry? Like if you point Julia at it, will it download the general registry and just serve it with like a cache locally?
Yes. So by default, the only registry. Yeah. So in this, maybe I can switch to it. I think I have it here. So if you go to this repository, there is a deployment directory here, and the configuration that is currently here will just serve the general registry. So if you want to have other registers as well, you might have to do some configuration, and yeah. But that's the default registry. Yeah.
Any other questions? If not, I also have one. At what scale do you feel like it's worthwhile for organizations to deploy their own package server? Is there kind of a benchmark level at which you're like, this is a good time to do this?
I don't know. I think the main reason you would do this is if you have something private, basically. I mean, you are free to use the resources that are provided for free by the Julia Lang organization. So I think if you only use the general registry, there's not really a big point in doing something on your own, unless you have, I don't know, a very slow network or something like that. So for example, maybe we can go back to, so one thing that we didn't have to begin with was we didn't have a server in Australia. So it made a huge difference for the people living in this part of the world that we configured this one, for example. But I think it should have pretty good coverage now. Yeah.
And also, one quick follow-up. I forgot my question, so never mind.
OK.
Thank you very much. Let's have another round of applause.
Test.
Quick reminder while we wait, there are headphones available at the top if you're having trouble hearing the presentation, or if you just want to wear headphones, the audio is beamed to the headphones.
got just a URL. Could I present off your computer? Thanks. Cool. The demo won't happen, but that's okay. Pardon the delay.
You know the URL?
Sure. 22. Do you have Julia? Okay. It's okay if not. Oh, great. Perfect.
One at a time.
Cool.
Yeah, do you know the URL? I leave my phone here because it's using my internet.
Okay,
so
cool.
I don't know how long.
Sorry about this. Here we go. Ah, and maybe I can go full screen. Okay, hello. I'll be presenting the public keyword. If you want the copy of the slides, that's a QR code. Yeah, so I'm going to start with a little interactive bit. I've got two questions here. The first is base.isExpr part of the public API of Julia? Could I get a show of hands? Who thinks that base.isExpr is part of the public API of Julia? Who thinks it is not part of the public API? Okay, so we're split about maybe 40-60 with a slight majority saying it's not part of the public API. Love that. Great for that kind of ambiguity. What about base.printMatrix? Is that part of the public API? Yes? Is it not part of the public API? Ooh, it seems like more people think this one's not. Maybe it's like 80-20 not part of the public API. Okay, this is not particularly satisfying. We should know what the public API is. We don't have computers in front of us. We're just off the top of our heads. But how would you know? Is anyone really confident in their answers? I'll tell you the right answer is base.isExpr is part of the public API and base.printMatrix is not part of the public API. Is anyone, like maybe someone who got it right for one of them, how did you know? Yes. I heard we use the first one and we don't use the second one. That's, so tragically, we do actually define public API in some part based on whether it's used in the package ecosystem. We use package eval to run semi-breaking changes on Julia, test all the packages, see if it actually breaks things. And that really does inform a lot of how we decide whether something's too breaking or not, which is not ideal because we also want to be able to add internals and confidently know that they're internal and we can change them later. So yeah, yeah, and does anyone have an authoritative way of finding out the right answer to this? I heard ChatGPT, and that is an incorrect answer. So this is unsatisfying. And the solution, before we get into the solution. So a little bit of background here. We want to communicate to users, and this we is the Julia base, and it's also packages. Package authors want to communicate to their users what can be depended upon. And that is documenting the current behavior and also whether that behavior will change in the future. And it's pretty common to say this whole set of behaviors, the public API will stay stable for all non-breaking versions. If you release 1.0 and it has a certain feature, people should be able to upgrade to 1.10 and not have anything break. And to do that, we need to define what is that API, what are we promising won't change. It's really a matter of communication. And that communication allows people to upgrade packages without breakage, which lets people use the latest versions and not have to deal with, like, did you use base.print matrix and now it doesn't work anymore? Like, whoops, that's not fun. So the problem here is in public but unexported names. Base.isExpr and base.print matrix are both unexported. So you have to access them with a qualified syntax that is base dot. You can't just type isExpr at the REPL. And they both have doc strings. So if I try to demo this, ooh, okay. This is the So that's the doc string of base.isExpr, and that's the doc string of base.print matrix. So they both have doc strings. So we can't use either of those to determine which is which. And this creates an ambiguous API. And this is another, like a subtle side effect, is it discourages documentation of internals. If base.print matrix wasn't documented, then no one would think it's public because you would have no idea what it's doing. And that's bad because we want people to document internals because it's good to document things so that people who do decide to intentionally depend on internals can do so more safely. So the solution here is to decouple the API and namespace to allow people to mark things like isExpr or base.fix2 or base.fix as public without exporting it into the namespace. Because sometimes a lot of people use your package and you don't want to clutter all their namespaces. For example, PKG has the public symbol update and the public symbol add. And we don't want anyone who says using PKG to get update and add in their namespace. We don't want to export those, but they are public. And so we add this public keyword. And that lets you say that a symbol is public without making the symbol exported. And the syntax here is the same as the export syntax, but it's semantically a no-op, no impact on namespace. It's introspectable with base.isPublic, which is similar to base.isExported, which will tell you, given a module and a symbol, whether that symbol is exported from the module. And perhaps the most important part about this is it supports tooling. So those doc strings in 1.11, which, do you have 1.11 on this? Okay, we're not going to demo it. Or you can try. Yeah, great. In 1.11, we will have the ability to, when you ask for the help string, sorry, I'm being distracted. Is this 1.11? Okay, great. Would you get the doc string of base.isExpr and then base. Yeah, great. And then base.print matrix? Perfect. OK, so look at this warning. The following bindings may be internal. They may change or be removed in future versions. So you don't have to use base.isPublic. You just ask for the doc string. And right with this documentation of internals is a warning that these are internals being documented. And so now there's no risk. You can document all the internals you want, and people aren't going to mistake those documented internals for public API. They still might use them, but that's another problem. So yeah, this is all coming out in 1.11, which is around the corner. The way you interpret whether things are marked public and how that works is if it's exported, then it's automatically public. And the API of a package, you can kind of assume, it usually will be the documented behavior of all the public symbols. So if there's some sort of undocumented behavior of a symbol, you probably can't depend on it. But if it's documented and it's public, then you can count on it to stay the same in future non-breaking versions. And you can just read the doc strings, and it'll tell you all you need to know. So for a package author, so that's what you do as a user. It's just go about your life, and the information will be presented to you. For a package author, there's one action item that I'd request you do when you have public unexported symbols. It'd be great if you marked them as public. And for most packages, the public API is fully exported, so there's nothing you need to do. And if you don't do this, it's going to be OK. The only impact is that when folks query the doc strings of those public unexported symbols, if they're not marked public, they'll get this warning, which is not ideal, but it's not catastrophic. Nothing will break, and no warnings will happen at runtime. Only tooling will be a little bit misled, and the doc string query will contain a warning. If you want to support previous versions of Julia before 1.11, which is quite sensible, then you won't be able to use the public keyword, because it's not a keyword in previous versions, but you can use compat.jl, which is a package that is great for letting you use new features of Julia with old versions. And so you can just use the @compat macro and say @compat public XYZ. And that will expand to a no-op in old versions of Julia, and expand to the public declaration in new versions. An example is, this is an example from base. It's the iterators module, and we can see the export list and the public list right below it. And same syntax. It's actually, this was kind of tricky. I'm now jumping from how you can relate to this as a package author, as a user, and jumping into how it was implemented, the backstory here. It's a little bit tricky to create a new keyword, because keywords are reserved. You can't use them as variable names or as function names, and we're just adding this new public keyword. So we've explored several options for adding this in a non-breaking way. One of them is as a macro, the @public macro, which would be non-breaking, but it just doesn't, if you come to Julia and the syntax here isn't export public, it's export @public, that feels a little bit inconsistent. And I really, whenever possible, want to make these design decisions thinking about the future, thinking about folks who are going to be coming and Julia 1.12 is their first version that they ever see. I want it to seem cohesive. It could be an extension of export, and that has the added benefit of, or it could have been extension of export with a keyword like export scoped equals true or qualified equals true. But people found that confusing. That would have the advantage of you could it'd be even more extensible with other tags. You might want to tag exported things as, say, exported in a certain version. And so we might end up adding keywords there anyway, but that's a future talk. And so what we ended up settling on for making this practically non-breaking is public is a conditional keyword. It is only a keyword at the top level, and only a keyword when it's followed by a symbol, as in this list. So if you have something in your code that uses public not at the top level, it'll still be treated as an identifier. And if you use public at the top level as a global variable, like public equals 7, that will be treated as an identifier. And if you have a function like public of x equals x plus 1, that will be treated as an identifier. It's only in this specific case, which was previously an error, that it becomes a keyword. So practically not breaking. In fact, technically not breaking. And hopefully in the future, people will use public as an identifier less because it's a keyword. And it's kind of bad practice to use a keyword as an identifier. And then we use package eval to just double check that it's not breaking, and it's not. Then there's some technical details of how this is implemented, similarly to export. So this is getting into the Julia object model, which is very internal. Bindings contain a bit for whether they're exported or not. And now we add, and there were spare bits. There was an 8-bit field or 3 bits of padding. We took one of those bits and used it to represent whether something's public or not. The names function, we changed so that names of a module now just returns the public names instead of all names. And that practically is a non-breaking change and allows for better discoverability. This way, the auto-generated README, the auto-generated doc string of a package can include a list of all the public names, which is great for discoverability. And if you call names of a package, you get all the public names, which, again, great for discoverability. There's a lot of bike shedding about the specific syntax for this public, as there always is, and that's probably for the best. It's good to have a lot of people talking about which syntax we want, because these are kind of permanent choices. And that discussion happened on GitHub and is open to anyone who's watching the GitHub repository. And then we redefined Julia's official public API to be, instead of the documented behavior, it's the documented public behavior. So that's following that same intersection that I was talking about earlier. It's the intersection of public and documented. That is the API you can count on to stay stable in future versions of Julia. And finally here, there's an interesting technical detail of nested publicity. If you have a submodule, then the submodule can be marked public, and then symbols within that submodule, if they're marked public, then that symbol can be counted on to stay stable. And whereas if you have something that's, oh, computer died, cool beans, I will just wing it from here. Give me 30 seconds. Oh, maybe it's just timed out. Oh, great, perfect. Thank you, thank you. So if you have a non-public submodule, then anything within that submodule, even if it's public within that submodule, unless there's a continuous chain of publicity to it, will not be public to an outside user. Some future work in this domain of helping people communicate intent, helping people communicate APIs, are traits and abstract types and interfaces. It'd be great if we could have some sort of way of programmatically specifying those, possibly even formal specifications of the contracts of various functions. This is all far out, unclear if it'll ever happen, but things worth thinking about. Continuing to clarify doc strings, given how Julia communicates and facilitates communication between authors and users, clear doc strings are really quite an outstanding thing. So that's an ongoing future work. Marking symbols as public where appropriate is still ongoing. It'll be a bit before we've got all the public symbols that have accrued over time are actually marked public. So that's a lovely way to contribute. And behavior that's not tied to symbols. This is mostly the case with Julia, the language. Also the case a little bit with packages. If it's not tied to a symbol, then how do you formally specify that? I mean, you can just always tell people to read the manual, but if you have to read the whole manual of all the packages you use, I mean, go for it, I guess. That sounds like a great idea. But I think a lot of people want something more quickly accessible and more modularly accessible. You might want to know the public API of a part of a package, but you don't care about a different part. Marking fields of a struct as public is something that I think might be coming. Struct fields are private by default, but some struct fields are public, and it'd be nice to be able to programmatically specify that. And then this final point is the most, I would say, has the most potential to be changing culture, and that would be disabling access to internals by default. And then you could, so this would mean that if a symbol, thank you, is not public, you would need to specify that you depend on the internals of a package before you could use it. And what that would do is allow PKG to resolve versions with an awareness of what is public. I want to thank Claire Foster for inspiring this. At last JuliaCon, we talked about it, created this idea together. There's a lot of people who have had this idea before us, but in chats with Claire is where this happened. Code review and parsing. This is implemented in parsing. Thank you, Claire, for making the parser so nice to work with. And all the reviewers of the pull request and folks who have already helped by making symbols public. Thank you all. I think we have a bit of time for questions.
Yeah, so with tab completion hinting coming in, one of the questions is what we should do about completing things that aren't explicitly marked as public. And I guess a detail on that is if you have a package that hasn't opted in to flag anything as public, what do you do then? Do you just kind of treat everything as public or treat everything as internal?
Yeah, this is a tricky one. And this is not my decision. This is a consensus decision that we need to make as a community. I think that there is a class of packages that have a fully exported public API and should not be declaring anything public. And so I don't think we should special case packages that don't use the public keyword. I think that tab completion should still tab complete internals, at least for now, because I don't know about y'all, but I depend on tab completion. And that includes depending on tab completion for developing packages I'm writing, which means I need to tab complete internals. For the hints, the inline hints, I think those should only display for public things.
Yeah, that makes sense to me. I was wondering also if you do tab completion and see multiple things, whether we should separate internal and public, or maybe like color code them or something.
Yes, absolutely. Definitely worth doing.
So I was wondering, so the public keyword works on just the bindings, right? So I can imagine that there are situations where you actually have methods that are tied to the same function, that where some of them are public and some of them aren't. Was that something that was considered?
Yes, yeah, that is something that was considered. The answer here is please don't have public methods and private methods on the same function. It's terrible. As somebody who's inherited a code base that has that, and now I'm like, oh, this feels so icky. Yeah, try not to do that. However, it's only the documented behavior that's public. So if you have some undocumented method, then that's not public. Now, if you have documented methods that are private and documented methods that are public on a single function, this doesn't help you. However, I think that's not a viable way to define an API because of the way dispatch works. It's tricky to know which method you're calling. So, like, as a user, I know that I'm calling a function, and I might not even know what types I'm passing to that function, because I might be writing a generic function that takes type any and passes it on to your function, and so then I don't know until runtime if I'm depending on internals, and that's just not a good API. And so, yeah, for the most part, the answer is just try not to do that. Okay, in the back stage right.
So if you import a private module that declares public members, I'll use the word members. Say you're in the REPL. Are those considered public? So it's like a private submodule from a public package, right? You've got a public package, it has a private subpackage in it, and you import a public member from that. Is that considered public or private in your context?
Yeah, so publicity is based on the binding. So when you imported that private submodule, that was accessing internals. And if you asked for the doc string of that private submodule, it would give you that warning of that's an internal module, and the whole module might disappear. Once you have that internal, if it defines public methods, public functions, public symbols, those would be considered public. So if you're saying, if we've got a module A and module B is an internal module of that and it has symbol C in it, then accessing B.C is good, that's fine, but accessing A.B is going to be accessing internals. So if you manage to get your hands on B somehow, maybe through a different API, then accessing C within B is fine. Does that answer the question? Great.
Up here to the left.
Thank you. I just want to be sure of the interface that I'm getting. If I don't do anything to my packages in 1.11, I will get those warnings on my not exported doc strings for free, right?
Yes.
Okay. Thank you for that.
You're welcome.
Thank you very much.
I just want to ask, is there anywhere in a situation where it makes sense to have a binding that is that is public but not exported, or should public always imply exported?
Yeah, so usually public things should be exported. However, sometimes it's a really common name that you don't want to pollute people who are using your package's namespace with. So, for example, if you scoped values is a standard library that defines the method get, the function get, and it's a different function than base.get. And it's a key part of the API of that package, so it's public, but they can't export get because everyone's already using base.get. So when you're worried about a name conflict, a naming clash, or if you just think a name is too common, or you don't want, if you've got a lot of names, like maybe Unitful has a lot of names that, so many names in Unitful that are public, but you don't want to pollute the namespace with.
Okay, makes sense. And the other way around, that you have something that's...
No, you do not want to put your internals into somebody else's namespace without them asking for it.
No.
Yeah, export implies public. If you have something, export implicitly implies public. If you have something that's exported, of course it's public. You shouldn't be exporting internals.
But is it like technically implied, or do I, as a package author, have to make sure that everything I export I also make public?
It's automatically done.
Okay.
Export, the keyword, makes it exported and makes it public.
All right, thank you.
Yep. And I think you'll get an error if you do declare it both ways. So the compiler will remind you.
We have time for one more question up here. Tim.
Has there been thought of an intermediate stage before sort of disabling access to internals, of having a period where there's an automated pull request to submit a new badge to all of the registered packages about their certification status with which they are using or not using internals of other things? And do you think that badge would be sufficiently motivating to get the ecosystem marking things as public to speed the transition? I think especially since public isn't in 1.10 and that's going to be the LTS, I do think as a community we need to think a little bit about how we encourage adoption of this.
Yeah, I think, so to have any sort of badge or any sort of notion of whether a package depends on internals requires another big technical leap, and that is tracking whether people are using internals. And so that's the technical aspect. And then there's this social aspect of how do we use that. I think one option is an opt-in to say, a package could say, I don't use internals of my dependencies, and set a flag somewhere and then get that enforced. And then that could go with that could be a README badge. Yeah, I don't know. I think there's a lot of brainstorming to be done about this.
Yeah, basically you go into Aqua, right?
Yeah, it could go,
You just after lowering, you lower all the code in the package, and then you look and you see if it's accessing non-public things.
Yeah.
It doesn't sound that difficult to add as an aquapass.
Yeah, yeah, it could totally be an aquapass. It wouldn't be perfect, but it would be very reliable, I think. Yeah.
All right, that's all the time we have for questions. Thank you very much. Let's have another round of applause.
Oh, is this, yeah, okay. Thanks, everybody. And just for a quick reminder, we're going to have another keynote back here in 10 minutes, so please be back in time for that. And also, another reminder, you're going to get sick of hearing me say this, we have a poster session at 6:30. So please come and see all the amazing posters. If you are a poster presenter, you can start hanging up your posters now before the keynote. The stand should be set up. So see you back here in 10 minutes, everybody, for our second keynote of the day.
pictures when I got here. It was like, what exciting location.
Okay. Testing. Okay, great, we are up. So thanks everybody for joining us for the second keynote of our first day of JuliaCon. It's going to be presented by Dr. Michael Herbst and Dr. Rachel Kirchen on the topic of quantum chemistry. Obviously, they know a lot more about their keynote than I do, so I'll let them take it away in a second. Just another quick reminder that we'll have the closing ceremony after this and a poster session also at the end of this keynote. And with that, take it away.
Thanks so much, Katie. We're both really thrilled to be here and really honored to be giving what I'm given to understand is the first joint JuliaCon keynote, so hopefully this all logistically goes off without a hitch. And I also want to lead off by saying that we're definitely here representing a much broader community, some of the members of which I see in the audience, and some are maybe listening in online. And we'll shout out several folks by name throughout the talk, but I wanted to kind of lead off by thanking all of the folks who've been involved in the various Julia Molson packages and the sort of broader Julia for Materials ecosystem. And so with that, I'm really excited to tell you all a bit about materials modeling and how we can build bonds across atoms, code, and people. So I want to start, since this is not a material science audience, by saying a little bit about what is material science and engineering. So I myself am in a materials science and engineering, or MSE, department. And the kind of things that we think about really hinge on this nice sort of chain link figure that I have right here. And it's fundamentally about understanding on the scientific side and leveraging on the engineering side relationships between these kind of key attributes of materials. And so we can think about at the starting point processing. So what do we do to a material? How do we make it to be in some particular chemical formula, some particular structure? You know, it could involve various treatments and under different conditions. And these things all in turn affect the structure of that material. And another kind of key signature of MSE is that we think at a bunch of different length scales. So from the atomistic length scale, how are these atoms arranged? Are they ordered? Are they not so ordered? All the way up to, you know, through sort of mesoscale, up through kind of macro scale at the scale of something that, you know, we could hold or touch. And it's this structure that in turn dictates the properties of the material. So physical things that we can measure related to it. You know, for example, the melting point perhaps, or how well it transports heat or electricity or some other form of energy. And those properties then are pivotal in determining the performance of that material in some sort of application that we might then want to use it for. And so I want to motivate this. You know, we're here in the Netherlands, and hopefully many of us are also cheese lovers. So I'll motivate this as a concrete example by talking through it in the context of cheese. So if we start from the end of processing, you know, we start with milk from sheep, goat, cow, whatever. There's a bunch of processing that goes into it. You know, maybe we're mixing together different things. Perhaps we're adding something. There's often an aging process that might have to happen at certain conditions of temperature or pressure or other sorts of atmospheric conditions. And all of these things ultimately in some form or fashion determine the structure of that cheese that we get. And we can, again, think about this at these many, many different length scales. So on the left here, I'm showing a single casein molecule. This is one of the very important molecules that's found in milk. Casein does a really interesting thing. It forms these spherical micelle structures, and that's what I've shown in the middle here. Those micelles, in turn, will aggregate to form what we call cheese curds. And so I'm showing a microscopic image of a cheese curd on the right, and exactly how we process, what the inputs to this processing are and how the processing proceeds all determine the details of this structure, what different, allomorphs of casein are in there, and all sorts of other interesting things. Of course, this then determines the properties that we can measure. So we might think about mechanical properties, like how stretchy the cheese is, or what it's, how does it melt, at what temperature does it melt. We might think about other properties, perhaps olfactory properties that some of us might like or not like so much. But again, ultimately, all of these things combine to determine the performance of the cheese. How pleasant is it to eat? Does it have a nice texture? Does it have a nice taste? Hopefully we all enjoy, we might not call it this, but in some form, evaluating the performance of cheese, right? And so I've gone through this, and hopefully it gives you a sense, especially if you're not a material scientist, of the kinds of things that material scientists think about in a kind of relatable context. But if we think about the academic practice of material science, I'm sure there are some material scientists somewhere who talk about cheese, but many of us think about other things as well. And what do we mean by a material? So what's kind of the scope of this here? Basically, we're usually talking about something that's solid or solid-ish. Usually the sort of fully liquid or gaseous things, we typically leave that to the purview of the chemical engineers. There's lots of really interesting and important stuff there, but the scope of materials science is typically sort of solid or maybe like slightly squishy or goopy things. This includes a lot of different things. We typically think about 4 main materials classes: metals, ceramics, polymers, and then composites, which can be mixtures of those. They can exist in a lot of different kinds of states or phases. They might be atomically ordered or not so much. They might exist in different geometrical form factors, nanocrystals, thin films, bulk chunks of material. I've shown some representative examples at the bottom here. So wood is a really fascinating biocomposite material. We can think about coins. That's a classic type of metal that many of us maybe not so much anymore interact with, but certainly once upon a time probably did. Plastics we see all over our daily lives, the chairs that you're all sitting on, oftentimes drinking straws, all of these sorts of things. So we all interact every day with materials of many different kinds. And materials are also important to many aspects of technology and sort of moving the world forward. It's an extremely interdisciplinary field, so MSc relies and builds on concepts from physics, chemistry, engineering fields, as well as the biosciences. I mentioned wood and other sort of biomaterials as well before. It's extremely interdisciplinary. It's something I personally really love about the field. You get people with all sorts of different kinds of disciplinary trainings, and it often takes people from all those different backgrounds to really successfully tackle a problem. And these new and improved materials, we have solutions to many of the, we have existing solutions to many of the problems of this century, whether it's the climate crisis or access to clean water to improve global health, many other things. In many cases, the performance of those solutions and whether or not they're good enough is fundamentally materials limited. And so new materials have the potential to kind of unlock better, more efficient, more economical solutions to these problems. And that's a big motivating factor, certainly, of my research personally, and I think of the research of many folks who pursue materials for a whole wide variety of applications. So recognizing that we're at JuliaCon and kind of pivoting now from the extremely general introduction to material science into the computational aspects specifically. When I talk about computational material science, this is still a really broad term, right? So what we mean here in the most general sense is that we're modeling materials on a computer by using that computer to solve some set of governing equations that we believe that we can use to model that material or to describe that material. These so-called computational experiments can really offer valuable complementarity to lab experiments or to pencil and paper theory. We can often access length scales in a simulation that we can't necessarily see or measure in a lab. We can simulate systems that are far more complex on a computer than we could ever do with pencil and paper. So it sort of fills this nice niche in between. Often you'll hear folks refer to computational science generally as kind of the third paradigm of science. So you had sort of the empiricism governed by experiment and theory and computation, and now you start to hear talk talk of kind of the fourth paradigm of sort of data-driven ML and AI, and we'll talk a little bit more about that later on in the talk as well. This is really becoming integral to a lot of aspects of material science and has the potential to really transform what we can do or the scope of scale of what we can do. And relatedly, computational MSc in particular offers tremendous value for acceleration of that sort of materials design, discovery, and optimization process that I was alluding to on the previous slide that can be important for advancing technological solutions to all manner of societal challenges. So I'm going to get a little bit more specific now and talk about a few aspects of computational materials science organized on this plot here. And I'll preface this by saying, this is going to be a pretty high level and broad introduction, and I'm an expert in particular areas that I'm an expert in. If you are a computational materials scientist, first of all, if we don't already know you, come introduce yourself, because we want to meet more material scientists who are using Julia. But also, if I somewhat misrepresent anything that you particularly work on, I apologize in advance for that. Feel free to correct us or add something during the Q&A if you'd like. And so what I'm talking about here, when we're on these two axes here, we have the length scale on the horizontal axis. So this is what length scale of materials can we access or describe, ranging from nanometers or even angstroms all the way up to multiple meters, and similarly timescales from picoseconds up to seconds. And I'll note here that the timescale we're talking about is the physical timescale in the material. This is distinct from the runtime of the simulations, which will generally be many orders of magnitude longer. Certainly at the lower timescales, the runtimes of the simulations will be many orders of magnitude longer in general than the timescales that we're simulating. So that's an important distinction to make here. And so I have kind of four broad buckets of types of simulation that I'll go through briefly, and also include a little bit of, for those of you who are not already interested in these aspects, a few kind of motivating concepts of where ideas from math or numerics or CS come in and have really a lot to contribute and add a lot of richness to why these are sort of interesting, challenging, multidisciplinary problems. So starting from where I think both Michael and I spend most of our time thinking about with electronic structure. So this is, again, at those shortest length scales and time scales, ranging up to maybe a few tens of nanometers, perhaps, and then kind of up to maybe the nanoseconds in terms of time scales of processes that we can think about. We're typically thinking about order of 1 to maybe a few thousand atoms, so a very, very small number of atoms that we're thinking about. The core governing law, the governing equation, is the Schrödinger equation, so we're thinking about the wave functions or some approximation thereto of the electrons in these materials. There's a number of existing Julia packages designed for this, one, of course, being the density functional toolkit that Michael is a developer on, as well as Fermi, and a bunch of really fun math concepts come in here as well. So the Schrödinger equation is a nonlinear complex eigenvalue problem, and there's a bunch of interesting and often quite bespoke numerical methods that go into solving that in the kind of regimes that we're thinking about, which I've kind of summarized here. Moving up sort of one rung on this sort of length scale and time scale, we can think about molecular dynamics. And so here we're still resolving individual atoms or molecules. We're from maybe the hundreds to at the sort of most heroic scales, perhaps of the order of 10 to the 13 atoms. Here, we're no longer thinking about quantum effects and electronic interactions, but rather the governing law is now Newtonian mechanics. So if you remember just F equals ma from a high school physics class, we're basically just running that many, many times on many, many particles to simulate their motion. I see Joe is in the audience right here. Joe Greener is the developer of Molly, which is the main Julia package certainly that I know of for doing MD simulations. And again, a ton of really fun, broader math, numerics, CS topics. So we're fundamentally solving a massive system of coupled ODEs, and we need to do that in particular with symplectic integration in order to conserve energy. So there's a lot of fun numerical methods that come in there. When you're thinking about simulating under different particular thermodynamic conditions, there's lots of interesting control schemes and constrained optimization problems that come in. When you think about how to parameterize the various potentials that we use in actually computing these forces, a lot of other interesting stuff comes in. So now we're verging into the territory where I'm certainly less of an expert, but I think it's important to mention as well. So at the sort of mesoscale, now we're no longer resolving individual atoms, but we are sort of solving equations that somehow are aware of the existence of atoms, let's say. So we can think about reaction diffusion or various phase field laws, the Boltzmann transport equation, And I'm not actually aware of a Julia package that's a specialized package for these types of problems. That being said, however, these are all generally partial differential equations. So any of the numerous wonderful tools that are capable of handling partial differential equations are certainly a good place to start for this. As in many different fields, with materials, there's certainly specific things, and one could imagine making a sort of specialized package that builds on those things. But not currently aware of one. Feel free to correct me if I'm wrong. And then finally, up at the longest length scale and physical time scale, we can think about continuum modeling. So now think about finite element or finite volume approaches, and the governing laws here are basically various continuum descriptions of matter, which depending on the problem of interest might include mechanics, electrostatics, transport of various quantities. Those are often coupled together in various ways. We might need to explicitly impose thermodynamic constraints because those are no longer going to be emergent if we're not explicitly resolving particles. There's a number of packages that are well suited to doing this in Julia. And again, a bunch of fun math ideas that they build on as well. Okay, so having sort of given that basic setting, and hopefully even for those of you who may not be materials scientists, convinced you that this is somewhat interesting and has some interesting technical meat to it, we'll come back to this kind of chain link thing. So you can now maybe see that if we think about materials science, we're kind of going up the chain in a way, understanding how processing affects structure and in turn how that dictates properties. From the engineering side, we often want to go the other way around. So we're interested in designing or discovering a better material for some sort of application. We ultimately want improved performance, and that necessitates the improvement of particular properties that we may know or suspect to be limiting that performance. So we'd like to be able to design materials kind of going this other way around. And computation here has a really key enabling role to play in that process because it enables us to save a tremendous amount of time, money, and energy compared to experimentally screening many candidates in the lab. And just to give you kind of a sense of scale on the energy piece here, one fume hood, which would typically be one very small part of an experimental lab. A lab may have multiple fume hoods, a lot of other large and energy-consuming equipment. Just that one fume hood has a typical energy usage on the scale of 2 to 3 average households. So this is expensive, as I mentioned, in terms of time, money, and energy. And we want to use those resources as efficiently as we can. And if we can use computation to kind of pre-screen, then that becomes really valuable. So let's talk about what the actual sorts of computations we're doing are in a little bit more detail. So if we're thinking about going again back to the bottom of that sort of length scale and time scale, if we're thinking about doing an electronic structure calculation, perhaps as I spent much of my PhD doing, trying to identify promising materials for solar cells, we would basically set up the sort of unit cell, the crystalline repeating unit in that material, use something like DFTK to solve Schrödinger's equation for those electrons and interrogate the results of that in order to compute certain properties that we might know are important related to light absorption, charge transport, various important things in these materials. And this can give us a sense of the material's suitability. And I'll say a little bit more detail about that in a moment. But the key point here is that this one calculation is of a sort of modest to moderate computational cost. It would run on the order, depending on the size of the material and how detailed a calculation you want to do, it could run on anywhere from a handful to maybe a few tens of cores. And we usually run these things on supercomputers not because we don't have local machines that have access to that scale of resource, but because we fundamentally want to do this at a very large scale so that we can screen many, many, many materials. So we can automate this process by screen many different structures, many different chemistries, different sorts of materials in this kind of embarrassingly parallel way, at least at one pass here, right? And this is the kind of HPC we're doing. So it's a little bit of a different, a lot of times people talk about HPC. I think it was Valentin who was earlier talking about a Gordon Bell attempt. These are like basically single jobs that take up an entire supercomputer. That's not really the regime that we're in. We're talking about sort of single to couple of node jobs, and we run many, many, many of them. So that's the sort of scale of HPC, the form of HPC that we're in. And a typical kind of workflow here in a computational materials discovery context, we often have these sort of funnel graphics. So we might start with a large list of candidates drawn from some online database. There's many and more every day, kind of wonderful online databases of different sorts of materials. And we start with sort of the lowest cost filter. So whatever the cheapest thing we can compute is, we use that to eliminate some candidates. And then we sort of apply progressively more expensive computational screens on the remaining ones until at the end we hopefully have like an experimentally tractable number of materials candidates that we can hand off to our experimental colleagues, and hopefully they have a decent chance of a good hit rate at finding something that's interesting or promising for whatever application we're thinking about. So this is a typical kind of workflow or paradigm that these things will be set up for. And it's worth noting that these types of calculations, MD, DFT, other types of quantum simulation, already take up a noteworthy share of the world's supercomputing resources. So as one example, on Archer 2, which is a machine that we have the capacity to get data for, you can see that in the blue here, these things are routinely taking up of the order of half of the resources of that particular supercomputer. And another thing I want to highlight is that this approach, and computational MSE more broadly as just this kind of set of techniques, whether or not it's specifically used in this high throughput way, is used extensively in industrial contexts as well as academia. So this is an extremely non-exhaustive list of companies that I'm aware of that do some form of computational materials science work. And so this is quite pervasive in a number of different industries and types and scales of companies. So this is a thing that is out there that folks in this audience may or may not have been aware of previously. So with that, I'm going to hand it off to Michael to start making things a little bit more concrete and a little bit more Julia-specific.
Yeah, thank you very much, Rachel. So I'm indeed going to talk about how to actually compute complex properties. And the guiding example that I have in my head is two things. So for example, here, if I want to compute a melting point of gold, so this is gold which is melting, or for example, if I want to understand how ions actually move in a lithium-ion battery, then what I'm after is dynamics. So I want to understand how these things move around here. And just to make it a bit more concrete and to get it to a scale which is sort of doable on the sort of simple HPC systems that I have in my lab, I'm looking here at a lump of aluminium, right? So this is just a lump of aluminium, and I'm interested in, as you see, simulating here the thermal motion of the aluminium as it sort of, just naturally vibrates a little bit. And this dynamics is really important indeed to just from sort of analyzing the so-called trajectories that come out of such a simulation, we can indeed understand like the melting point of aluminium, or for example, how like a lithium ion could transport through the aluminium, okay? So that's the sort of setup I have in mind. And how do we do this basically in a step-to-step guided fashion? So one time step, so sort of one frame that you saw in this video would be that you start from some structure. You do indeed invoke something like this density functional theory, this lower left tier of computation that Rachel has been talking about. And then you get the energy E here and some derivative of the energy with respect to the positions, this grad E, the forces. And with this, indeed, you solve Newton's equation, and then you propagate a little bit the structures. And so things change, and you really have done some motion, right? So we do this in the video for 1,000 time steps. And as Rachel has already mentioned, really doing this for 1,000 steps using the sort of the standard, the most accurate theory, one single time step takes on the order of hours, right? So 1,000 times 1 hour, let's say, is a considerable amount of time. And I didn't actually spend that much time making the video. So what did I do? And this is where the machine learning comes in. Actually, I didn't use the underlying density functional theory, this high-level method, to do my simulation. Instead, I used a machine learning surrogate. And this surrogate can be evaluated in typically under a second, right? So now I'm all of a sudden in the regime where I can actually do something reasonable, like making up such a nice video that you saw here. But then, of course, this raises the next question: how do I actually get the surrogate? Okay. So, of course, the general idea for surrogate modeling is you generate some data. So in this case, data generation actually, again, invokes a lot of computation, right? So we are still in this HPC regime that we have been talking about, that we need to run maybe tens of thousands of data generation steps. And then in the end, I can sort of, maybe do a linear system solve or something. And then I get my trained machine learning model. And that I can then replace by the actual DFT computation. Now, the thing here is, though, which model should I choose, right? Even on the machine learning model side, there's really plenty of them to choose and to try. And just to give you some ideas, the typical questions people ask is, how expressive is my model? Meaning, like, can I actually even represent all the physics that I'm interested in? How accurate is it, right? Like, how much does it actually reproduce the high-scale wave function system, the wave function method that I have been using? And then, of course, data requirements, right? Some machine learning models, I do maybe 1,000 calculations, I'm done. But for others, like neural networks in particular, I might need much more data, meaning that I actually have the cost of generating this data, right? So there's really a lot of considerations to take into account. And the point really I want to get across here is there's no one size fits all. And so the flexibility to in your workflows, swap this out, swap this in, play a little bit with the different machine learning models. This is really something that we need in order to make progress in this kind of research field. Now let's talk about how this looks in practice. So this is just some input files. So actually many codes in this field still use text-based input and output. And this is some standard input files that people would traditionally use to run these kind of calculations, this aluminum simulation that you've seen. And just even by looking at the parts that are highlighted, you see the structure and the formatting is very different. So every code has sort of their syntax, and in particular, this is not very well standardized and changes sometimes between versions, okay? So you can imagine what kind of a nightmare it is to sort of flexibly, or rather non-flexibly, swap in and out different codes. So what's the solution? Of course, the idea is to invoke the power of abstraction and to say, well, I mean, some structure sort of is some abstract object I do want to somehow represent, and some, calculation object that just uses the structure and gives me back some energy and some force. That's also some standardized object that I can somehow abstract, right? So let's just do that. Now, that's exactly sort of what we have done in the ecosystem. And in fact, we are now at this point where this aluminum video that I showed you earlier has indeed been completely generated using Julia tools. So with this script here, I use DFTK to generate the underlying DFT data. Then with the second script, I use this package called ACE Suite. So ACE is one kind of machine learning model that is used in the field. I fitted such ACE potential, as they say. So basically, I fitted such a surrogate for the DFT calculation. And then I used Molly to run the calculation and eventually produce the video that you saw. So the point here is that we already pass the structures around as abstract systems, so I don't really have to worry about, changing units or converting things between the conventions that the different codes are using. And of course, I also, well, that's at least the plan in the near future, to also use really calculations, abstract calculator objects, as we call them, to swap in and out the kind of, computations that is underlying for example, the dynamics here. Okay, I mean, this sounds like an obvious thing to do, and indeed we have not really been the first to do this. So in the ecosystem, in the material science and computational material science ecosystem, there's really a number of people that have worked on this kind of idea of abstraction. The one that has guided our thoughts most is the so-called atomistic simulation environment. And indeed, the point I want to get across here is that these codes exist and they work reasonably well in practice, but there are some issues. Like, for example, in fact, they're usually just wrappers around this text-based I/O. So they just drop an input file, they run the computation, they pass the output. Okay, and this actually means that whenever I want to get a new calculator working, meaning I want to try a new model or some new idea, actually this is non-trivial. I always have to write this parser and I always have to write this generator for the input. There's sort of usually not a standardized API. And it's actually not just a 2-language problem, it's typically even a 3 or 4-language problem, right? So I can have some Python part that is actually the workflow management system. Then I sometimes have like a Fortran part that is wrapped via C to something else. And I mean, this is really a bit of a mess. And that actually means really also the amount of effort people have to put in to be able to really write these calculators, right? This is really, a PhD first has to understand all these languages. So this is really not in line with the opportunities and strengths of Julia, clearly, and basically it's not so able to export some of the flagship features that I'm going to present to you on the next slide that Julia is really able to do. And so this is our motivation to sort of try to give a Julia-based approach to overall this whole material science and ecosystem abstraction problem. So now let's talk about some things that Julia tools can do right now, which are in fact actually not so easy to do in some other standard tools. So one aspect I want to get into is inverse design. So let's say you actually have such a whole simulation that I showed you, like these 1,000 time steps, and now you're asking yourself the question, I know that aluminium has this and that melting point, okay? Can I actually train my machine learning model such that it reproduces the melting point? Okay, so I'm not what is traditionally done, I'm not using so-called proxy quantities, right? So I'm not just using the machine learning model, I'm not training it to reproduce the energies and forces, but I'm actually training it to directly reproduce the physical observable. So this is actually really tricky, and it's hardly done in practice, because it's actually a typical case where you want to do end-to-end algorithmic differentiation, right? In the end, you somehow want to have a loss function, and you want to backflow your gradients until you can update your machine learning parameters. And this is, however, something that needs to be exposed. And traditional interfaces, in particular when you think about file I/O, it's really tricky to do these things. Now, Joe has indeed actually done this, and so this is one of the cases where Julia is really like pushing the state of the art, and of course that's something in our implementation that we want to keep. Some other examples now from the people of the ACE suite is that something called as active learning. So the idea here is that if we train such a machine learning model, it only knows something about the structures or the vicinity of the structures that we gave it. So if it's somehow not confident, meaning that we're not really able for a particular structure to reproduce the exact energy and forces, then we need to run additional underlying data generation steps. So what does this mean from the point of view of a workflow? Well, it means that while you're actually running your simulation, like producing this nice aluminium video, you're always changing between running the high-level ground truth, running the machine learning model, running the dynamics, updating your machine learning model with extra data, and so on and so forth, right? So it's not just a simple linear workflow, but it's really starting to become a more complex and much more involved procedure. And this is something we would like to do. The other thing we would like to do in DFTK, we've worked actually quite a lot to come up with more robust algorithms, which we want to test, of course, in practice, but also we came up with ways to quantify errors. So this is a band structure, a really important quantity in material science, and we are actually able, in some settings, to predict the error that the numerical procedure makes. Now, of course, this kind of error we would like to use in our simulation. Or similarly, what we worked on in DFTK is being able to forward diff and compute sensitivities, again, of quantities of interest. So again, the same idea is if we have all of these sensitivities and we have all of these gradients, can we use this in our simulation? Can we propagate this forward? Right? So this is essentially something where we again need to augment our workflow. And here's going to be a talk by Niklas actually on Thursday, who's going to talk a bit about some issues of AD in the context of DFT, because actually it's not as simple as I make it sound here, but well, anyway. But the point is we want to exploit these things, right? We have it now and we want to exploit it. So essentially this leads to a shopping bag that we came up with when we were starting to design this interface of abstract system and basically atoms calculator. So in the end, we really want to improve the composability, right? So all of these tools are out there. I showed you some flagship examples, but actually what's definitely missing is good integration between them, right? Really exploiting this in a holistic way. And being able to use error control, these new machine learning models and AD in a whole Julia workflow from front to back. Then, of course, the next problem is that in this field, there's thousands of methods. We will not be able to implement thousands of methods in Julia within the amount of time and energy and people that we have. So we really need a two-way communication with existing tools. And that's not just necessary for us to sort of test what we're doing, but it's also important for adoption, because people need these different methods. They need this whole selection of methods to be able to do the physics and the chemistry they want to do in practice. Next question is, I talked about active learning, I talked about on-the-fly data generation. This leads to a problem which I would call dynamic and heterogeneous modeling, okay? So the issue is, if you think about like an active learning pipeline, what happens is that in the beginning, you need to run a lot of ground truth density functional theory simulations. That typically works well on CPUs. But then, as you're basically training your surrogate, this is something you do on the GPU. As you're sort of using your surrogate more and more, and you're using less of the DFT, the balance between running CPU and GPU is dynamically changing throughout your simulation. Somehow you need to dynamically schedule these jobs on a big cluster, right? We talked about tens of thousands of jobs. Somehow this needs to work. This is not so trivial. And then the next question is, of course, how can we integrate across communities, right? So mathematicians, they work really on the hot loops to come up with new algorithms, new ML kernels, and so on. They need to be able to do this without really worrying about all the HPC business. But still, they need to be able to test in practice their algorithms, because some of the algorithms that look nice on paper, they might not actually work. So again, for testing and also for adoption, because people will not use algorithms if they're not push button available in their favorite simulation. And so here I want to quote Alan, people compose of software composers, and I really think this is something where Julia can make a crucial difference. Okay? So with this, I hand back to Rachel. We'll continue.
Yeah, thank you very much, Michael. And so I want to so we've talked a little bit about some of the specific stuff that we've been developing within the purview of JuliaMolSim. So this Atoms base, which is meant to be a sort of interface for specifying structures. That's been around for a couple of years. Atoms calculators, which is a bit of a newer effort for these sort of abstract calculator ideas. In the broader Julia materials ecosystem, what can we do today? So you can interact with these abstract systems through a number of packages, including Atoms Builder for building some of these structures, Atoms.io for reading and writing to a wide variety of the various standard structure files that are used, structure representation text files that are used in different contexts. Some calculators that are out there. These are not all implementing the Atoms calculators interface yet, although they hopefully will sometime soon. So there's DFTK, of course, and there's an update talk on that on Friday that Michael will be giving. Interatomic potentials, which specifies a variety of potentials for interaction between different particles. ACE suit that was mentioned previously, that's developed by Christoph Ortner and his team at UBC. A number of different active learning tools, and there's some talks coming up later in the week on those as well. One we don't have a bullet point for here, but I think Joe has a Mali talk like right before Michael's on Friday, if I remember correctly. Oh, that's in the next one, sorry. Dynamics. We can do dynamics using these potentials, and Mali is great for that. There's also Vannier for localization of electronic structures, so that's more in that sort of wave function space, as well as a bunch of packages for integration with external ecosystems. So we mentioned ASE. There's LAMPS, which is one of the major MD codes that's in use in the broader community today. SPGlib for interacting with certain kind of specifications of crystal structures and symmetries. So there's a variety of things out there. They don't all talk to each other yet quite as well as we might like. There's also a bunch of other cool stuff that didn't quite fit into this talk, but we wanted to get a few shout-outs in there. So there's Cell List Map, which is developed by Leandro, and that's what's currently used for neighbor lists in Mali, I believe. Freebird.jl, developed by Robert Wexler's group for implementing these interesting nested sampling approaches for developing phase diagrams. I'll plug some of my own stuff a little bit. So during my postdoc, I worked on both developing new models for kinetics, or basically how fast electrochemical reactions proceed under different kinds of settings. So this is really important to understand. For example, if you want to charge your electric car really quickly, a lot of the models that we have now don't work very well at extremely high reaction rates, high currents. So we developed a model that works a little bit better for that, as well as in some slightly more exotic circumstances, like the twisted trilayer graphene that I'm showing in the figure here. And this is all implemented in a Julia package called electrochemicalkinetics.jl that can, makes nice use of multiple dispatch for computing these rates according to different models that allows you to easily compare them. Shout out especially to Daria Gandhi from Julia Hub, who helped with making the AD work nicely with this, so that I can now optimize backwards through these for things like parameter estimation or doing other sorts of introspection to build up these kind of electrochemical phase diagrams, which is what the third paper is here. And of course, other types of simulations that we didn't mention as well. There's a neat package out of Reinhard Maurer's group at Warwick called NQC Dynamics. So this can do these sort of mixed quantum classical dynamics. This figure, I believe, is electron dynamics at metal surfaces, so sort of interesting things that happen at interfaces between different materials. So, and this is also not an exhaustive list. There's a bunch of cool stuff out there, and we're happy to talk more about this and anything else in the Q&A, during the poster session, et cetera, et cetera. Current state of JuliaMolSim, we've alluded to some of this already. To date, as things tend to go in academia, and package development is driven primarily by the research questions that we want to tackle, right? So the ecosystem is sort of co-evolving with the things that we're working on, that we have funding to work on. And as a result, these packages often kind of lack breadth. although they have been becoming more mature recently. And Julia tools, as we've hopefully convinced you, have certainly been a key ingredient in many, many cases to push the state of the art in terms of what's possible. And there's been also some community recognition. So Joe and Michael and myself both all relatively recently started junior faculty positions. And I think this is, of course, great for our own career progression, but I think is a recognition also of Julia and what it's able to help achieve, that it's contributed to that sort of career advancement. Unfortunately, interoperability and collaboration have largely been unfunded side projects thus far. And I think many people are familiar with this kind of quandary. The Julia Molson organization has been around for maybe about 5 years. Atoms Base was started after I think it was a BOF that Michael and I ran at JuliaCon in 2021. And then Atoms Calculator started a little bit more recently, just in the past half a year or so. And we've been having somewhat more regular discussions and working to collaborate and build kind of consensus on what these interfaces should look like. But a lot of this is still, relatively early stage. I think we're certainly both here extremely optimistic about the potential for Julia in this space, and I think there's a lot more to be realized than what we've shown you today. But this full integration is definitely in early days, and of course funding is always a challenge, right? If you can get funding, that contributes tremendously to kind of the stability and maintainability of all of these things, and this is an issue that is absolutely not unique to our community. Okay, some ongoing projects. So kind of, again, in the same theme, increasing internal interoperability and collaboration. So we've been actually undergoing a pretty substantial redesign of the Atoms-based interface and working to finalize what the interface for Atoms Calculator will look like. Putting these two together will allow us to build geometry optimization. So this is a really common kind of task in atomistic simulation, where you basically start with some initial guess of where all the atoms ought to go, and you want to find what the lowest energy configuration of them is. And so you typically will compute the forces and sort of scooch all the atoms over in the directions of the forces. And this, of course, requires a representation of the structure and a way to compute those energies and forces. And it's nice to be able to swap in and out different representations and methods for those things. So these abstract interfaces combined into this will provide a nice platform for doing that. We've also been talking about a sort of broader redesign of how we do neighbor lists that's more amenable to implementation on different types of hardware, which again will increase this kind of portability and interoperability. And then again, these kind of cross-ecosystem integration pieces. So Michael has been working to integrate DFTK with AIDA, which is a pretty widely used workflow manager for DFT packages, and has really good kind of support and infrastructure for these really high throughput workflows that can have different kinds of complicated interdependencies to them. There's, I believe it's Temu, who's been working on getting Atoms Calculator to work with ASE, this Python-based package we mentioned before, as well as some other things. And generally, the goal here is just to improve testing, improve adoption of these things. A lot of things don't yet necessarily have sort of fully stabilized interfaces or entirely complete testing or documentation, and we're aware of this, and we are working towards it. And plug if you want to join us at the hackathon and try to help with any of that this week, perhaps. And I think another thing that's really important to acknowledge, right, is not everything is rosy, right? There's challenges along the way with all of these things, and it's important to be transparent about that. So I'll hand it back off to Michael to summarize some of the gripes and challenges that we've come across along the way here.
Yeah, and I'm going to be quick. So basically, I think the biggest issues on sort of the Julia adoption side are that people perceive Julia as a language that makes overly ambitious promises. So I think it's something where we as a community have to be very careful when we make promises, because if people see them not satisfied, and that can mean just, Julia didn't download properly, that is a problem. So we have to be very careful in documenting and making sure that the promises we make can actually be achieved. Other issues that we have already been talked about in this conference is binary support. I hear that's going to improve. I'm very much looking forward to this. This is a big deal in integrating our code with the other ecosystem that, as I explained to you, is really important and necessary. Then on the Julia Molson side, there's sort of the standard stuff of not having all the methods, but there's also things like, documentation and performance. So documentation definitely is on us, but performance, I think, is something where I'm sure there's many low-hanging fruits, and if you guys who are probably much better at performance engineering than some of us are, can take a look at some things, this would us as an ecosystem really push forward. Then there's some other things like lack of some utility packages. Again, we're trying to do some of this at the hackathon. Please reach out if you're interested to help. Now, overall, for the shopping list, I think we have made a good start at many things. One thing that we really haven't tackled is dynamic scheduling. And I think, again, this is something where Julia can shine. And so this is something where, again, we would be very interested if you have some ideas and some ways to sort of get started on this topic. All right, so how can you get involved? We already mentioned it a few times. Yeah, try it, right? Try our stuff and tell us what breaks, right? Because I'm sure there will be things breaking. Otherwise, we have a nice Zulip server where you can basically connect with the overall community. And here at JuliaCon, we plan to go and have a nice chat after the poster session. And at the hackathon, as I mentioned, we have some projects, some ideas. Feel free to reach out if you want to help. Particularly if you're a graphics person. We need graphics people. So people can make nice illustrations and so on. All right, so a bit of advertisement. I have an open postdoc position at the edge of Bayesian inference and learning and inverse materials design. If you're interested in that, there's a link to check out. Then we are going to organize a nice Julia-based workshop here at EPFL towards the end of the year. Some of the people in the audience are already coming. Julia for numerical problems in quantum and solid state. And Rachel is also doing something.
Yeah, so I also am organizing a workshop that'll be at my campus at Carnegie Mellon in Pittsburgh. It's funded through the Molecular Sciences Software Institute, which is a really awesome organization out of Virginia Tech. And that's going to be basically on the same topic of what this keynote was about, Julia for computational, molecular, and material science. That's going to happen towards the end of October. We don't quite have a registration page up yet, but if you hit that QR code, which we're happy to go back to, that'll put you on our Zulip, and I'll be posting details there as soon as we have them. So we'd love to see you there if you're interested in playing around with this stuff, and we're really hoping to attract folks from the Julia, from the Julia MolSim community, of course, but also from the Julia and not material science community, as well as from the material science but not Julia community. So kind of bringing all these people together to really talk about, best practices, potential pitfalls to avoid, and all of these things as we continue working towards making this ecosystem more mature. OK, so to kind of wrap things up, I won't read every word on this slide, but sort of to give you a kind of summing up of what we've talked about. Hopefully, we've convinced you that computational material science is interesting and has interesting problems for people, even those who are not specifically interested in material science or physics or chemistry. There's a lot of interesting computational problems, like the importance of these dynamic and heterogeneous workflows that Michael was telling us about. The Julia MolSim ecosystem is something that we're really excited about pushing forward. It's relatively early days. There's a lot of things that have a lot of maturity building to do, but I'm certainly extremely optimistic about the potential for Julia and for these tools to contribute to this field in the future. And of course, that doesn't mean that there aren't other challenges we're moving forward, both on the sort of human side as well as on the technical side. And we're excited to kind of keep charging forward and addressing those and improving all of these tools. So with that, I'll acknowledge this is a very, very limited list of folks. On the left, folks who've been really involved in the Adams Base and Adams Calculators efforts, particularly in some detailed conversations that have happened over the last several months leading up to this, putting together the little demo that we showed, and all of that. And of course, both Michael's research group, my research group, and I want to particularly shout out the SESMICS team at MIT. And then, of course, various institutions and funding sources that have supported both Michael's and my groups and our research more broadly. And with that, I will put up all of these various ways that you can reach us. And I think we do have a bit of time left for questions, so we'd be happy to entertain some questions. Thanks so much.
Questions? You mentioned fairly simple sounding properties like melting points. How about more advanced properties like environmental behaviors? Do materials bioaccumulate? Do they biodegrade? How far can computational material science help?
Yeah, so that's, I mean,
like
you're getting
carbons accumulating in the environment. That's
yeah, absolutely. You're getting at some of the really, I think, kind of cutting edge problems in, material science generally and computational material science in particular. I was just a few weeks ago, I was at a photovoltaic, the IEEE Photovoltaic Specialist Conference. This is something people talk about a lot related to, how do these materials degrade? How can we recycle them? These things fundamentally, these challenges come, I showed that plot of the length scales and time scales, right? And if you're asking about a time scale that's much, much longer than what we're able to explicitly resolve in our simulations, that's inherently going to be a challenge, right? You're sort of off the Pareto front of what we know how to do. And so you're then pushing forward both the kind of science and the methods for solving and simulating the science at the same time, which means that there's kind of large uncertainties there. I think that's something that material science broadly is working on, and that certainly Julia has potential to contribute to, especially when it comes to some of that uncertainty quantification. I think AutoDiff and all of these tools are going to be really valuable there. But yeah, I mean, broadly, I think some of those things we know how to answer, at least in a sort of heuristic sense, thinking about the thermodynamics and maybe to the extent that we can quantify kinetics. But it's something that I would say is an open problem in the general sense. There's kind of bespoke solutions for individual contexts, but maybe not generic answers to all of those kinds of questions at this point.
Oh, sorry. You were talking about the integration with LAMPS for molecular dynamics, and I was wondering, do you plan something similar for big quantum chemistry packages like QChem? I think they were also doing something at MOLSI at one point. So,
Yeah. So QChem, I don't think anyone has written an interface there. But I mean, if you're just looking at the text-based I/O, or I think the API they offer, I think this shouldn't be too hard. I think somebody's written an experimental integration for Orca, so that would be an example of a Gaussian-based quantum chemistry code. So yeah, there is of course work in this direction because these things are out there and they work. But actually, maybe let me emphasize. So I was talking about cross-ecosystem integration, and actually the point is that we don't need to integrate with everyone. We only need to integrate with important people. So for example, what I mean is we need to integrate with sort of other interfaces. So ASA and ASE and IPy, for example, they have integrations with, for example, QChem. So if we integrate with ASE, we're done, right?
I've never used this.
Yeah, so that's basically the idea here, right? So we don't want to redo all the work that others have done. That's what I meant by ecosystem, cross-ecosystem integration, right? I don't want to replicate that. I want to use that. So that's, yeah.
Yeah, thank you a lot. I wasn't aware of that.
Package that integrates a lot of diverse external tools extremely well is JUMP. Have you compared sort of what level challenge they faced in getting a working ecosystem versus what you have to do? I would worry that yours is even more diverse in terms of the tools and the inputs and all this kind of stuff.
Yeah, I worry too. The honest answer is no. Right, so so we definitely wanted to look a little bit into other ecosystems, but to be fair, it didn't get fully across. But right now, just us, the few people who are talking to each other, us agreeing on an interface and one way to communicate, that's already a problem. It takes a lot of real honest work, and I think we're simply not at the stage where it makes a lot of sense to start looking at these things. But I agree with you that we should do that.
Yeah, and I'll maybe just add briefly, I think that's another place where the funding becomes a challenge, right? Because we kind of have to some extent, focus on the things that we have funding to work on, and we can sort of expand the scope a little bit beyond that. But these much more ambitious kind of interoperability and compatibility projects I think are something that you kind of need a more firm sort of financial support where you can put someone on that as basically their full-time job. And we're not there yet as a community. Hopefully we will be someday.
All right. So thanks again to our awesome afternoon keynote speakers for the first day of JuliaCon. We have a small gift for you both. Thank you, Jorge.
Julia's Vineyard and Chateau nice. Julia. Look at that.
Amazing.
Very cool.
No.
So we have a few quick announcements for the closing ceremony, which is going to be like a little bit bootleg because I don't have any slides. So again, thank you both for the awesome presentation. I'm sure they'll both be around in the evening and during the rest of the conference if you think of some more Q&A you would like. So the first thing for the closing ceremony is if you are a poster presenter, please go set up your poster now. If you're not a poster presenter, ignore me. But if you have a poster, now is the time to go set it up before a swarm of 300 people go up there to see your awesome poster and you can't get to your stand. Thank you. Sorry. With that, my name is Catherine Hyatt. I'm the program chair, so if you're really mad about when your talk appears on the schedule, now is the time to throw a water bottle at me. So we just have a few quick logistical announcements. First of all, we really want to thank everybody for their patience dealing with the unexpected noise we've had during the talks today. We understand it's not the ideal situation for the presentations. So again, we want to thank everybody who's been attending and especially presenting talks. We're working with the venue to try and resolve this situation. We definitely want to thank you for your continuing patience with that. And a couple quick logistical announcements for tomorrow. So probably our biggest one is that tomorrow we are presenting jointly with PyData, which is awesome. So let's all be sure to give PyData a super warm welcome. If you have a JuliaCon ticket, you're more than welcome to attend the PyData talks. Just please keep in mind if the room is really full, let the PyData folks in first. They're going to have their own 2 parallel tracks of talks, and we'll be doing keynotes together. And having 2 conferences in one spot is awesome, but it also means we're going to have a lot of attendees. And you might have noticed today at lunch that there was a really long line for lunch. And we were at some risk of running out of sandwiches. So again, please for tomorrow, just keep in mind, when you go up to get your first sandwich, just try and grab like 2 or 3, not more than that, just so everybody has a chance to get a sandwich and everyone will have a chance to get lunch. Also, if you have a special dietary need, like you're vegan or gluten-free, please send somebody from the organizing committee a DM in advance. We'll be able to make sure you get the sandwich that's meant for you. And a couple more things. So now that I've sent the poster presenters away, I can tell you again, please go to the poster session, which is starting right after this. It goes till 8. We have a lot of great posters. We've included the posters on the schedule just so you can see what they all are, but all of the posters are going to be on the 3rd floor where all the lunches were. So go to the 3rd floor if you would like to see the posters. There will be snacks and see some of the awesome stuff people have been working on. And then also a quick reminder that tomorrow evening is our diversity dinner for which you can purchase a ticket. We'll have lots of great panels and speakers for that. That'll be on the 4th floor tomorrow, Thursday. And then one quick last thing, sort of circling back to the program issue, we've had a couple instances of talks having to be shuffled around, for which I really apologize. This is mostly because people are having travel or visa issues. It's obviously not ideal. So everybody who's a speaker is going to get an email tonight from the JuliaCon committee with your talk time. If it doesn't work, just let us know and we'll do our best to accommodate you. But you'll get a reminder email, again, just saying, hey, your talk is at this time, so hopefully there won't be any more unpleasant surprises. And if there are, reach out to us as soon as you can and we'll do whatever we can to accommodate you. With that, that'll be the end of our main tracks for the first day of JuliaCon. Thank you all for attending. Thanks again to our amazing keynote speakers. Yay! And we'll see you bright and early tomorrow morning at 9.